Data science has been a trending field of study in recent times. This is because of the amount of data that we create constantly and the computing power that is available with advancements in technology. But what is data science? Think about what happens when you book a ride on Uber. You open the Uber app on your phone and tell the app where you want to go. Uber tries to find the nearest cab, sends them the directions to come pick you up, and take you to your destination. That was simple. But in the background, the seemingly simple task is carried out by collecting mountains of data from various sources, like the phones, the map, and historic trends of traffic and demand for rides. With this data, modern-day computers are programmed to calculate the nearest driver to you, the best route to your location and destination, the time it will take, and what you should pay. In other words, this is made possible with data science. Data science has countless other applications as well, and is at the intersection of statistics, data analysis, and machine learning. It is a combination of scientific methods, models, and algorithms working together to extract actionable business insights from data. The U.S. faces a shortage of 140,000 to 190,000 people with deep analytical skills, and 1.5 million managers who can analyze big data to make effective decisions. The average salary of a data scientist is around $118,000. So, still interested in data science as a profession? Continue on to learn more about who can become a data scientist, why data scientists matter, what is the data science life cycle, how big data is driving the data science revolution, the career prospects for data science. Data is the oil of our generation. Data science is becoming indispensable in today's digitally driven world, helping businesses understand consumer behavior, fine-tune its messaging, and capture new market share. To become a data scientist, you don't need to have a technical background to be a data scientist. What you do need is in-depth knowledge in mathematics, analytical reasoning, the ability to work with large amounts of data. It would also help to have a strong intellectual quest, knowledge of data engineering, visualization ability, and excellent business acumen. If you do come from a non-technical background, you will likely use R. If you are from a technical background, then you could use Python and R. It is all about understanding the possibilities and asking the right questions, all in the search for the best answers. Every company is flooded with data, and they have more data than they know what to do with. So, regardless of the industry vertical, data science is likely to play a key role in your organization's future success. Data scientists help find new ways of reducing costs, entering new markets and customer demographics, and launching new products or services. Data science also has found social and medical applications, such as child welfare and predictive diagnosis as well. So, what does the typical data science lifecycle look like? The data discovery step includes the search for different sources of relevant data, structured or unstructured data. Then, you make a decision to include specific data sets into your analysis. The data preparation includes converting data from different sources into a common format. You will standardize the data, look for anomalies, and make it more appropriate to work with. The data science models are built using statistics, logistic and linear regression, differential and integral calculus, among other mathematical techniques. You could use tools like R, Python, SAS, SQL, Tableau, and so on. Getting things in action phase includes checking the data models for its effectiveness and ability to deliver the results. You will have to verify the model works. If not, you have to rework on your model. A data scientist needs to liaison with the various teams and be able to seamlessly communicate his findings to key stakeholders and decision makers in the organization. Another critical element of data science are algorithms, which are a process of set of rules to solve a certain problem. Some of the important data science algorithms include regression, classification and clustering techniques, decision trees and random forests, machine learning techniques like supervised, unsupervised, and reinforcement learning. In addition to these, there are many algorithms that organizations develop to serve their unique needs. Big data is driven by the data science revolution. Big data is the engine propelling the rise of data science. Hadoop is a popular big data framework used by most organizations. Hadoop works in a distributed manner wherein both the processing and storing of data is distributed on commodity hardware. Hadoop is easily scalable, highly economical, fault-tolerant, and secure. Hadoop consists of Hadoop Distributed File System, or HDFS, for storing data and uses MapReduce for processing data. Another emerging framework is Apache Spark, which is touted to be up to 100 times faster than MapReduce. Spark stores the data in the RAM, so iterative processing is fast and efficient. It also deploys Direct Acyclic Graph, or DAG, for processing of data. There is a huge demand and supply mismatch when it comes to data scientists. Due to this, salaries of data scientists are among the best in the industry. Top companies like Amazon, Google, Facebook, Microsoft in the tech space, to others like ExxonMobil, Visa, Boeing, General Electric, and Bank of America are actively hiring data scientists. Now that you have learned about data science, why data science is indispensable, the data science lifecycle, how it relates to big data, it is time you start your journey in this promising domain and see your career soar.
Hello everyone and welcome to this session on Data Science Full Course. Data science is one of the most popular emerging domains and most sought after career options. According to a report by LinkedIn, data science dominates its emerging job ranking with a whopping 37% hiring growth over the past 3 years. Data science is revolutionizing almost every industry and gaining popularity day by day. In this session, you will learn data science from scratch. So let's check the agenda for the session. First, we'll be talking about what is data science and why do we need data science. And then we'll be talking about different components of data science like data processing, data analysis, data gathering, data extraction, data cleaning, and data visualization. And then we'll be talking about some Python libraries like Numpy and Pandas. After that, we'll be talking about one of the major components in data science, which is statistics. And then we'll be talking about sampling, correlation, standard variance, and standard deviation. And we'll be also talking about the different types of visualizations. After that, we'll be covering machine learning. And then we'll be talking about logistic regression, linear regression versus logistic regression, confusion matrix, and decision tree. And then we'll be covering Gini Index and regression tree as well. To top it all, we'll be also covering some data science interview questions which will help you to excel into your interviews. So that's all with the agenda. Now let's start the session.
Let's get started. So, for example, when we talk about the data science as a process, typically what happens is, let's take a simple data science example. Even before we speak about the problem, even before we speak about the process, let's actually take, for example, a specific data science problem. Let's say that let's take, for example, we're Uber, or let's take, for example, we run, let's say, a food delivery service like Swiggy or DoorDash or any of these food delivery services, Uber Eats, for example. So Swiggy, or let's take, for example, Uber Eats, right? Uber Eats doesn't exist in India anymore, but yeah, it's a global product. So I'm just taking Uber Eats as an example. So Uber Eats would like to basically, Uber Eats as a product is a product is a service that is being provided by Uber, wherein the company sort of picks up food from specific restaurants and delivers that particular food to your door. And it's sort of pretty simple. From a process standpoint, it's pretty straightforward. But if you sort of take one problem that they solve, right? So the moment you place an order from a restaurant, right? Let's say you placed an order for a pizza from a restaurant. The moment you place the order, Uber Eats or Swiggy, for that matter, or any of these companies, what they give you is they say that your food will arrive in X minutes, right? Your food is going to arrive at your location in X minutes. How do they come up with this number? And if you actually observe, more often than not, right, unless something extremely unexpected happens, this X minutes is very, very correct. I mean, they're more often than not, they're actually quite, they're spot on with these X minutes. So my question is, how does Uber Eats or let's say Swiggy or any of these companies, how do they actually come up with these X minutes? How do they come up with the estimated time of arrival of food to your, or even when you, let's say, book a cab, right? The moment you book a cab, a taxi via Uber or Ola, or let's say Lyft or Grab or any of these cab aggregators, they sort of give you these, they say that your cab will, or your ride will reach your home in the next 15 minutes or 16 minutes. How do they come up with these estimates based on previous orders for that particular location? Okay, Paramraj, good point. Rahul has a point. It says fleet management history plus time given by the restaurant to prepare food. Okay, makes sense. Yeah, these are all spot on. So, but logically speaking, there is a little more to it than than a simple mathematical formula. Of course, when you say based on previous orders for that particular location, and when you say based on history, how do you get there? How do you get to that particular number? Does somebody actually, are you going to put a mathematical formula together? How do you actually end up getting to that particular number? So the way it happens, yeah, you build an algorithm, exactly. So what kind of an algorithm do we build here? So let's actually go through that process once. Let's actually understand how this happens. So first things first, whenever you solve this problem, the first thing that we have to do is identify, right, factors that that contribute towards the ETA. I'm calling it ETA, estimated time of arrival, right? So identify the factors that would contribute towards computing the ETA. So in your opinion, what are the factors that would contribute to the time of arrival of food at your home? So the first thing is simply distance. Is one example. What are the other factors? Can you name a few? Traffic, speed of the vehicle. Okay, the average speed of the vehicle. Basically, if you know the distance and you assume a constant speed, time is sort of self-explanatory. So you could assume a certain kind of a speed. Let's put that in as a factor, speed of vehicle. Okay. What else do we have? The order size. Very good, right? So order size. What else? So there are, let's actually, what? Let's break this down into two parts. Let me actually break this whole thing down into two parts. There are actually even more, but let's start with something simple. So one is the food in itself. The other is, or the food, or basically restaurant is one of the stakeholders, and the other is delivery person is the other process. So from a process standpoint, there are two primary things. One is food and the other is delivery, right? From a food, when you talk of it from a delivery standpoint, first things first, distance is a critical factor. Speed of how fast is that person going to drive is a critical factor. The third thing that we're going to capture is, or that could contribute, as somebody mentioned, is traffic, right? So from point A to point B, what is the typical traffic? We're going to capture that. Then four, we can also think of what else? Road conditions, good point. Right, we can think of some conditions of that particular road, fair point, all of these. There's one more, weather, exactly, time of day, right, and so on and so forth. So time of the day, basically calendar related features. Day of the week, right, day of the week, month, and so on and so forth. All of these are super important. Of course, there are many more. I mean, just not these, many more. From a food standpoint, yeah, good point again. See, right, is it like I'm just gonna call it, special events? Actually, you know what, that would basically be the restaurant related stuff. It'd actually be both, um, but yeah, let's go to the food related side of things. First things first, the size of the order, right? The type of food, right? Third is the restaurant might typically give an ETA, right? The restaurant would probably have some time food preparation time that they think they would take, right? So fourth is the demand of the demand of at the restaurant, right? Fifth is simply the size of the restaurant, right? Sixth is number of other orders, other pending orders, and so on and so forth, right? So these are a few interesting factors. So all of these, of course, these are not the only factors. There could be many other factors also that could lead or that could drive the delivery. For example, when you talk about the delivery, right, the type of vehicle could also be a critical reason. How good is the vehicle could also be a critical reason, because if that guy is delivering over a motorcycle or a bicycle for that matter, as opposed to a motorcycle, then of course it's going to take a little longer. So these are some examples. I mean, in India, of course, we don't have delivery done via bicycles, but in the Western world, of course, a lot of other markets, bicycle delivery is also sort of allowed. And folks actually deliver via bicycles as well. So that is okay. So the type of the vehicle would also matter. These are some examples, so some features or some factors that could drive your outcome. Now, what you do is then based on this is all great, right? This is all good. Additionally, what you try and also identify is for your historical orders, you capture all of this data, right? So you basically take all these factors, and for all your historical data, order ID, let's say the order ID is 123, 122, or 123. For order ID 123, which happened in the past, you capture all these features, right? You capture all these factors. So it could simply be like order ID 123, somebody, let's say, ordered 5 items, and the type of food was, let's say, Indian. The cuisine was Indian cuisine, or let's say South Indian or North Indian, whatever. And then you capture your food preparation time by the restaurant was, let's say, 15 minutes, and so on and so forth. You capture all of this, and at the last, what you would also capture is how much time did they actually take to deliver this particular order. So you capture all of this, and in addition, you capture how many minutes did they actually take to deliver this particular order. So now, based on this data set, I would typically have, offers. Yes, for sure. I mean, there are many other features which I've not considered over here, Rahul. You're absolutely right. So offers, and there could also be other factors, like, for example, again, there could also be other factors. For example, the state where this particular food was ordered. It's quite likely that the city where this was ordered is probably a tier 1 city as opposed to a tier 2 city. I could also take, for example, Swiggy or Uber. What they also do is they also capture information around locality, right? Because what they do is they tie up with, let's say, a Google, and every time an order is placed from point A to point B, they request from Google or Google Maps how much time would it take for somebody to get from point A to point B, and they would basically use that information as well. So yeah, type of restaurant. Is it a cloud kitchen, single restaurant? Yeah, correct. Is it a chain? Is it a franchisee? Blah blah blah. And if it's let's say a franchisee, then in that case, do they have how are they doing with other restaurants in their other branches? So on. These are just the million other things that go into it. This is just as an example. So factor 1, factor 2, factor 3. I'm just putting it as whatever factor n factors, also called as features. You capture all of these, and then you have the last variable, which is the variable that you would, or your estimated time of arrival that you would like to understand. Now, the thing that we need to do with all of this information is using this data, right? You need to come up with, given all of these features, given this information, you should be able to identify or predict what the ETA really is going to be, right? Given all of these features, or given some of these features, you should be able to predict all or some of these features, you should be able to predict the ETA. So the way it would turn out to be, and just to give you a simple example, the way it would turn out to be is it could actually, so once you collect this information, the first step that actually solve the problem is we do some data validation. Right? We do some quick data validation. What do you mean by data validation? Data validation, or it could also be data quality check, data cleansing, or whatever. So this step is responsible for ensuring that this data that we have over here, if it's of the highest quality or not, or if it's the best possible quality or not. What do I mean by that? So take, for example, distance. So what it might so happen that for a few observations, that means for a few historical orders, let's say the distance was captured in kilometers, and for a few others, it is, let's say, captured in meters. For a few orders, it's captured in kilometers, and for a few, it's captured in meters. And similarly, for a few, for let's say traffic related information, for a few, let's say data is captured in in minutes, and for a few others, it's captured in seconds. So maybe the data is not standardized. So firstly, we may have to run some kind of data cleansing. So under data validation, we do some basic data cleansing. At times, it might so happen that certain data fields might not be properly filled. You might not have information for certain data points, meaning you might not have enough information about what that particular locality is like. So you might have to do some, handle, missing values. You may have to do some missing values. Yeah, basically, some other data cleansing related activities will have to be done over here. Once this is done, then what we do is we perform something called as exploratory analysis. Right? What is exploratory analysis? Exploratory analysis is a process where we try and visualize, where we try and explore through this data set and verify if this data is, while it might probably have the right kind of numbers in them, but do these numbers from a business standpoint, do they actually make sense or not? So you will explore through that data and you will try and form some kind of a business sense in your head. So you might actually end up creating charts like these, right? So something like time of the day would be on your x-axis, and then you may have estimated time of arrival, and then you may have something like, your ETA could be very high in the beginning of the day, and then it might slowly go up by the end of the day. And this might actually, from hours 0 to 6, 12, 18, and 24. Let's say throughout the 24 hours of the day, you might have something like this, a behavior like that looks something like this. So you basically will do some kind of exploratory analysis, run some checks and balances on top of your data, and ensure that your data actually looks good. So once this exploratory analysis is a step which is really useful, because what it would help us achieve is it would help us understand the data better, because at the end of the day, the moment you're starting to do some of this analysis, if your data is not of the best quality, then unfortunately your analysis is not going to be that good. So you need to ensure that the data is of the good quality. And when you do your exploratory analysis, you are going to find some interesting insights, which you can then take them back to the business, meaning take these insights back to somebody who runs the logistics and delivery department and go and tell them, hey, this is what we're seeing within the data. Does this make sense to you? If they say that it makes sense, then that's wonderful, because that means then your data is a decent quality data. That means the people who the businesses are validating that for those kind of insights. It is a good validation for you as well. It sort of establishes credibility to the quality of the data. So that's like the most important step. Once this is done, so you do exploratory analysis or visualization, that's when you actually start leveraging some machine learning or statistical techniques to build some kind of a model. So what is this model going to do? What is this machine learning and statistics over here going to do? While using your exploratory analysis, you are trying to explore data manually. Your machine learning and statistics techniques will help you automatically extract these insights. So how will that happen? So the way it's going to happen is, so the way that's going to happen is you will basically end up creating, something which basically looks like this. So you might end up actually creating an equation that might look like this. So it might say that, hey, your ETA, your estimated time of arrival, is equal to 10 plus 5 times your size of the order minus 2 times, or rather plus 2 times the distance, right? And plus 4 times, number of, or rather, let's say, rainfall, and so on and so forth. So you might actually end up coming up with an equation that might look like this. It's not always going to be an equation. It might be an equation that looks like this. In certain scenarios, it could be an equation. In certain scenarios, it could be something else. But long story short, what will happen at this particular step in the modeling phase is you're essentially going to transform this data into an equation that looks like this. So now this equation essentially is nothing but your model. What this equation has is it has a collective intelligence of all of this, all the patterns within this particular data has been sort of transformed into just this small equation. What can we do with this equation? So what we can do with this equation is now you can disregard everything else that has happened before this. So what we're going to do is based on this, on any given day, if I know the size of the order and the distance and let's say the rainfall and let's say whatever others, I can simply compute the estimated time of arrival. So when I get a new order right now, so now what I'm going to do is the moment I get a new order, I'm going to quickly capture all of this information, pass them to the model, and the model is simply going to generate a prediction. The model will predict for that new order what the ETA is. So every time I get a new order, I send all the features that are associated with this particular model to this, with this particular order to this model, and then this model will generate a prediction. It says 10 minutes is what this is going to simply return back. That is how your ML models typically work. This is basically the typical process. Now, if I were to sort of put this a little more formally, this is how it would look like. So the first step is trying to understand the business problem. So in our case, the business problem was to basically use some data-driven techniques to identify the estimated time of arrival. So how did we solve it? We gathered all of the required data. Then we have a step called as data processing. So what do we mean by data processing? Data processing is, so if you observe, so we first captured all of the data and then we converted this into this data frame or into this table over here. How did that happen? So what that would need is, mind you, that these data is not, all of this data is not going to be readily available, waiting for us to consume, easily consume somewhere. All of this data is going to be available, but it's up to you to actually take this data and generate these, and build this particular data set. So the data processing step is where we are combining multiple data sources, and then using those multiple data sources, we're going to create this one single representation of all of this data. So that is exactly what this data processing step is about. Data processing step is where we're going to combine data sets and then bring them together. Once that is done, then we'll run some preliminary data analysis, meaning data analysis as in just run some quick data statistics, perform data visualization, which is nothing but your exploratory analysis. Your exploratory analysis might give you some insights about certain data sets, certain data points which are probably not correctly, or certain columns which are not correctly filled. So you may have to actually cleanse the data a little more. So you'll basically do a lot of back and forth between the 5 and 6 steps. And then from the 6th step, you actually build the model, right? 6th step to 7th step, or the 7th step, you actually build the model. Now, once the model is built, by the way, all of this, we'll learn each step how this is going to be done, right? So don't worry about how are we going to do data processing, how are we going to do data analysis. We're going to learn about each of these steps. So once the model is built, then that is where another interesting challenge starts. which, mind you, is not mentioned in this slide. But the moment you actually build the model, then how do I make this model available for my Swiggy app? How do I make this model available for, let's say, my Zomato app, or let's say for my whatever DoorDash app? How do I make this model? How do I embed this model into the complete process? That's another challenge altogether. That's an engineering challenge, and we call that particular field as ML engineering. ML engineering, because while the data scientists are actually going to build the models, ML engineers are going to take that model and make that model available for the app to start using it. So they are the ones who are going to take the model and embed that intelligence into the application. So it's a much more interesting challenge to have, but definitely something that is something that would definitely require a different kind of a skill set, so to say. Okay, that's as far as the data science process is concerned. So yeah, I'm not going to dig into each of these in depth, but what is it that entails each of these processes? So let's actually understand. So from a tech standpoint, what is it? What are the concepts that we will have to learn under each of these? So let's understand that. So the first step is data gathering. Just going to call it data gathering. So data gathering, right? Data gathering is a step, of course, for sure. But if you look at data gathering, right? Data gathering could involve us to actually extract this information from databases or from internet, right? And it could databases, internet, actually, you know what? When we talk about data gathering, data could actually be gathered from multiple data sources. One is the internet. The other could be one is internet. The other is databases. The other could be flat files, right? When I say flat files, I mean Excel sheets, right? Or it could also be, data can also be captured via some kind of, in its most raw form, right? So there are, let's say, some applications, and you need to sort of transform that data, which is into an application, which is a handwritten application, into, let's say, into actual data. So converting data which is of their most raw form, like I'm just going to call it raw data or unstructured data, meaning you have audio, video, images, text, right? Raw form data in the most raw form. You might actually have some of that data. You might actually have to use that data and convert that into something. Then you might actually have data from, data that's also being generated from, from some source systems, meaning you probably need to capture this information from, let's say, something like an API. What do you mean by an API? So take, for example, Google Maps, right? Google Maps is free for us. How does Google Maps make money? Google Maps makes money by selling that information to companies like Uber, like Ola, right? So how do they make money? So every time I make a request, or every time I place an order, what Swiggy does in the background is they identify my latitude and longitude. They anyways know the restaurant's latitude and longitude. So based on my latitude and longitude and the restaurant's latitude and longitude, they send this information to Google Maps, and Google Maps sends a response back saying, hey, with being before these two places, if you want to, let's say, gather some kind of information from these two, or if you want to deliver from point A to point B, then this is how long it's going to take. The same information which is available in our app will be available via an API. So API is basically nothing but a more sophisticated way of delivering that information. So long story short, the point is that this data may need to get captured via various data sources. The most preferable form is, of course, going to be in databases, because if it's in a database, that means all of this data has already been, all this raw data has already been processed to some extent, and it is already being stored in a database. But if that's not the case, then there's a lot of work at your hand as a data scientist. We might actually end up doing a little more, work on the data side of things before we actually start doing anything. Yeah. That's number one, step number one. The next step is data processing. So what do you mean by data processing? Now, let's say all of this data has been gathered. So data has been captured and it is now being stored in a database. Now, what do you need to do? So now you need to start using that data, and you need to, let's say, combine multiple data sources and then build your final data set, right? So you might have to combine multiple data sources and then put them together. How can you do it? There are two ways of doing it. Actually, a lot of ways of doing it, but for the purpose of this classroom, there are two major ways of doing it. One is you can sort of do this using you can sort of finish this inside the database only, meaning a database is basically a large storage of data. So you have all of your data being stored within your system on itself. But if this data is already getting stored there, and if I need to start processing it, there are two ways of using it. One is within the database itself, I have many tables. One is, let's say, the customers data. I have location data. I have, let's say, the restaurant data, and I have orders table, and so on and so forth. So I might have data being basically stored separately in different tables. So within the database, I might have to run some SQL queries, SQL queries, and then merge all these data sources and build one single data snapshot. That's one way of doing it. Or the other way of doing it is you can do this inside Python, or let's say any other programming language. So inside Python, we will read these raw files into Python or raw tables into Python, and then merge, do the data processing within Python. So how do we do it within Python? In Python, we have something called as, by now you must have realized, right? You've done your preliminary Python session. So all of you know that within Python, we do not have a tabular structure. So we would then have to use some kind of a tool called as pandas, or also NumPy. Pandas is nothing but a Python way of basically representing a table. And you also have NumPy, which is reference to numeric Python. So you could use any of these tools to merge data sets within Python. So that is basically where data processing becomes super important. So data processing can be achieved either via running this within the database, or you could bring the raw data into Python and then do your data processing, meaning merge all of your data within, do any kind of joins within using pandas or NumPy. The next step is, once the data processing is done. So yeah, as I said, you could do joins. You could do, as I said, you could do, basically you can start visualizing data as a table. You could basically look at data as a matrix and stuff like that. So all of this is what NumPy and Pandas is going to help us achieve. Pandas is like a two-dimensional tabular structure. So by default, in Python doesn't have a data structure which can store data as a table. You must have learned about dictionaries. You must have learned about lists. You must have learned about sets and tuples. None of those are by default useful for our data science related work, because we work on tables, or Python doesn't have a way of representing tables. So how do you do it? So you need an external library that will help us. That's what Pandas and NumPy come in.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Pandas are like, Excel sheets, while NumPy is a more raw form of this. NumPy is like a matrix, right? It's the same thing, but NumPy is more to do with matrix operations, while Pandas is more like an Excel sheet. So yeah, Pandas is like a slightly more sophisticated version of NumPy. The next step is the data analysis step, wherein we are actually going to do some quick understanding or quick analysis about some of the data. We are actually going to look at the data and then do some quick high level analysis, like counting your data, describing your data a little more, running some preliminary statistics around your data. It is basically at this step wherein we are going to run some statistical inferences on top of your data to validate if your data is good or not, or if it has the power, or if it has the explanatory power to let's say predict your outcome. In this case, ETA. In certain other problems, it could be something else. So we're just going to try and run some statistical tests over here to validate some of that. And then once that is done, we might end up doing some data cleaning, because if we realize that our data isn't of the best form, we might actually end up doing some data cleaning, like you might drop a few columns, you might fill missing values, you might actually change the data type a little. We might actually see that two columns are exactly giving the same information, so we might end up dropping one, keeping the other. And basically, again, it's data cleansing only, but a more sophisticated way of cleaning your data, a more a smart way of cleaning your data without actually losing the sanctity of it, and without actually manipulating that data, without actually fudging that data, right? So you have to be very careful when you deal with data cleansing, because it is borderline data manipulation. So you have to be very careful when you clean your data. Once that is done, then you might actually want to do some exploratory analysis, like I had mentioned. You might want to do some visualization, right? So you might want to actually create some of these charts, some good looking charts. So for that, there are actually a lot of libraries which are available. Some of the most popular libraries in Python that will help us perform these charts are Matplotlib and Seaborn. That said, those are not the only two. Yeah, so when you talk about visualization, right, there are a bunch of tools that are available in Python. Mind you, the reason why we do visualization is not that we would want to sort of make the charts available for businesses. Understand that we don't do visualization because we need to do reporting. We do visualization because we really want to understand data. So we are not going to be overly focused on the beauty of the charts. We're going to be focused more on the technicalities of what your data is. So you might actually end up creating some frequency distribution charts. You might end up creating some density charts and some other complex charts, and some very simple charts as well. So, but the primary reason that you have to understand why we create these charts is not that we want to actually report these charts to executives, but because you're creating these charts just for your understanding. So the libraries that we use, if you'd want to create charts for businesses, there are different tools, and we'll talk about that. For our exploratory data analysis purposes within Python, we use tools like, firstly, Seaborn. Matplotlib is like one of the oldest plotting libraries. It is actually it is a plotting library that was originally built for MATLAB. I don't know if you're aware of a tool called as MATLAB, but this was a plotting library that was actually created for MATLAB, and then they realized that this could be adapted for Python as well. So that's how it landed up in. But yeah, it's one of the oldest. There are a couple of others as well. Like you also have something called as ggplot. ggplot is built by a person by name Hadley Wickham. Again, this originated in MATLAB. This originated in R, and then it made its way into Python. So yeah, and then there's also one more library called as Plotly. This is again, Plotly is a library that again helps you create slightly more beautiful charts. That's it again. We're not creating charts for beauty purposes. So all of these, mind you, are libraries in Python. Our ggplot was created for R. We can actually use it in Python as well. So there is a Python variant of ggplot as well. But yeah, these are some examples of some plotting libraries. So once you create these charts, they'll help us. There's some explanation over here. Again, we're going to learn about data visualization in more detail in one of the sessions. This is how basically a chart you want to create histograms, heat maps, bar charts, line charts, and so on. So you could create multiple charts as well. And then once your visualization is done, that's when we actually start building a model. That's when we actually start building a machine learning model. So how are you going to actually build this model? So you take your raw data, right, and then you pass this into an algorithm. And what this algorithm is going to do is it is essentially going to sort of try and build an equation like this. That is essentially what this algorithm is going to do. So that is what is going to be your model. So your algorithm will be responsible for using your training data set and your desired output. So what is a training data set? This is your training data set. And in this data set, you have an output variable. So your ETA is an output variable. These are your predictor variables, right? Your F1 to Fn are your predictor variables. And this is your output variable or your target variable, because that is the variable that you like to use to generate a prediction. So your desired output is that. So you use that and then you build an algorithm, and based on that, essentially extract an equation, and that equation moving forward will be capable of predicting if a particular image is a cat or a dog, or it will be able to predict if how long a particular order is going to get, or predicting the ETA for a particular order, and so on and so forth. Multiple problems that you could solve. And once that is done, that is when we'll have to do some kind of testing of your model. Just because you built your model doesn't necessarily mean it is the best of the world, best in the best, right? So you still would want to validate if that particular model is good or not. So for that, there are some techniques that we will learn called as confusion matrices, for classification problems, and also for some regression, different types of problems that we have, different types of testing mechanisms that we'll have in place, just to make sure that the model that we built is of the best quality or not. Once we identify that the model is of the best quality, that's when the last step starts, which is the deployment phase, which is not discussed in this slide, in this deck anywhere, but it's one of the most important processes, so to say, right? So what that basically means is, in most of our projects, whenever we actually solve our projects, when we report status, right? When we report status to our businesses, we report status using these 5 statuses. We say, which phase are you in? First things first, business understanding, right? That's the first phase. The second phase is data exploration, or actually, you know what, data gathering. The third phase is exploratory data analysis, EDA. Fourth is modeling. Fifth is modeling, and fifth is basically experimentation. And sixth is, you could call it deployment, or we also call it operationalization. The term could be a little confusing, but that's basically like the 6th phase. So you can think of a particular project going through these 6 phases. So understanding what our features are is the business understanding phase, gathering the data, doing some exploratory analysis. We actually build the model. What is the experimentation phase? We haven't spoken about this. The experimentation phase is once I build the model, and let's say I test the model, modeling, and actually we call it testing. The experimentation phase is where, now let's say I have built a model which is able to, let's say, predict the ETA of a certain order, but I want to test this out. I want to really test if this works or not. There are 2 ways of testing. I can test on some dummy data, or I can test it offline, or I can do something called as an A/B test. What is an A/B test? We call it experimentation, or we also call it A/B test. What is an A/B test? So A/B test is a very popular phenomenon that is used, a popular approach that is used in the industry, wherein what we do is, so many a times you might have observed this, right? So when you open your Facebook, or let's say Instagram, at times you may see a different UI, and your friend might actually see a different UI, or a new feature. And whenever there's a new feature, it's never rolled out to the complete population at once. They run a small control group testing first. So they first do some beta testing. If you remember, they often call it as a beta testing as well. So what they actually do is they deploy this for a small group, and for the other group, they don't make any change. So the new algorithm is deployed here, and this is the old approach. Now they start seeing is this group actually doing better or not. Because I have a new model in place, because I have a new model that is predicting the ETA in place, I would start seeing, I would start capturing metrics like, am I getting lesser number of calls because of the ETA, because of a better ETA prediction algorithm? What is that ETA prediction supposed to do? If it says it is going to reach in 23 minutes, I should ideally see that my customers should be ideally calling me lesser and lesser, because the right kind of status is being reported back to them. I should also see that my orders are getting delivered on time, right? The order delivery rate should actually go up, or on-time delivery rate should actually go up. So certain metrics should start performing a little better. So then I would compare between these 2 groups. I would see that this certain metrics are performing well here. And that's not the case with the other group. Now, once I identify that this experiment is a success, then I go for a full rollout or a full deployment, meaning everybody will now start using this new algorithm. So these are like broadly the 6 phases that we would typically use whenever we build a data science solution or AI solution. And mind you, once I make the deployment, that's not where it ends. Then we redo this process, because over time, what may happen is the model that I might have built probably will become old. It might become obsolete. So again, I might have to build a newer model. Again, I might have to run a new experiment with the new model. The old model might be kicked out. The new model might start actually doing better. Then I deploy the new model. It's a continuous process. So this is more like a process, right? So that is how AI solutions are actually put into production. That is how AI solutions actually see the light of the day. Many projects, many models actually, you know what, don't go through this phase because they don't have the right data. Even if they go through this, many models actually don't go through this phase. Almost 80 to 90% of the projects don't go through the A/B test phase. They fail here. So long story short, what that does is that it makes our job as a data scientist very research oriented. So you are somebody who's going to get into a more, you're supposed to have a research mindset. Don't expect results every day, because you're going to start building models, and then which might not even actually see the light of the day. It might actually not even get deployed, so to say. So get ready for it. So yeah, this is how things actually work in reality, and this is basically what this slide is trying to tell you. Okay, we'll get into more subtleties when we actually solve this problem. I'll give you an exact example in a minute. Let me actually give you a problem. It's a very popular problem, and there's a lot of goodness baked into this particular problem. This data set that you're seeing is called as the Titanic data set. You ask any data scientist and ask them what their first problem is. I'm sure 60 to 70% of people would say their first problem that they solved using, their first problem that they got introduced to is the Titanic data set. This is basically like that training bicycle, right, that everybody learns with those 2 wheels on. So this is like there's a lot of goodness in this data set. It's actually real world data. When I say real world data, this data set was actually open source. It wasn't owned by any company. So sort of open sourced for people like you and me to actually go and try. So Anita, to your point, this is actual data. This is like real data. So, but that said, it's very small. So what this has is it has information about passenger class. So by the way, all of you all know what happened with the Titanic, right? So all of you all have watched the movie Titanic, or at least have heard about the ship Titanic. So the data set is basically about passengers who've traveled through the Titanic, who've journeyed in Titanic. A few of them have survived and a few of them didn't. A few survived, a few did not survive because of various reasons, right? We don't know what reasons exactly caused that, but what we are going to try and do is we're going to basically use some of the data that is available over here to try and identify which customers, if there was a new customer or new passenger who.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Traveled through this particular ship, would have they survived that particular incident or not? So stuff like, I have information about passenger class. P class is nothing but passenger class. So I have values like 1, 2, and 3, wherein 1 means passenger class 1, passenger class 2, and passenger class 3. I don't know if 3 is better or 1 is better. We don't have that information with us. But yeah, I think what we have over here is essentially a representation of the same data set. But we need to figure out, is 1 better or 3. The second is the survived column, which gives us information about 1 means people who have survived, 0 means people who did not survive. So all zeros are basically people who unfortunately had to die because of the incident, because of the accident. This is the name of the person, sex, male or female. You have age of the particular person, siblings. This is age in years. SBISP stands for siblings and spouse. How many siblings and how many number of siblings and number of siblings and spouses or spouses on this particular board. So 2 over here basically means that maybe this person has 1 sibling and 1 spouse on board, or maybe 2 siblings of this particular person are on board. So we don't know. PARCH is nothing but number of parents or children on board. Ticket is nothing but the ticket number. Fare is the amount of money that they paid for that particular ticket. Cabin is the cabin that was allocated for them. Embarked is these people have embarked at 3 different places. SC, these are basically indications of PQ and S are basically places where they actually had boarded the ship or embarked the ship. Boat is once the actual incident happened, meaning once Titanic started to sink, then there were a few people who survived and a few did not. So the ones who survived were able to get onto a boat. As you can see, there's a boat number. The ones who did not did have zeros against them. So basically, if you look at people who did not survive, they don't have a boat number. People who have survived have a boat number. So it's basically boat number essentially simply represents what boat did they get into from the actual ship to get to the shore. How were they rescued? And body is basically there were certain locations where the body was identified. So this basically is the location where they found the body. So that is basically what this body was about. And of course, you're just going to have these fields only for people who survived, who did not survive, unfortunately, who passed away. For the others, they're not going to have a value because they all survived, so you of course wouldn't find their body. So this was some of the data that is available for us. Now what we're going to do is we're going to try and use this data to identify which passengers have survived and which passengers haven't survived. So what do we do for this? So what we're going to do is first things first, use this data, and then let's actually import this data into Python. How are we going to do it? So as I said, there's only one way of reading tabular data into Python, or in many ways, but most popular way is of course using Pandas. So I'm importing a library called as Pandas, and then I'm going to load the data set. So Titanic, so I'm just going pd.read_csv of, there you go. So I read the data set. It's called as data. I'm calling it data here. pd.read_csv is a function that is used to read the actual data set. By the way, I'm just giving you an example here. I'm not saying we will learn about each of these functions in detail when we actually look at the Pandas session in more detail. This is just an example for you all. So what I'm going to give you all right now is like an end-to-end walkthrough of what it actually means to build a model and how to actually evaluate that particular model. So it's just an example session. So don't worry about not knowing a few things here, because in my opinion, you wouldn't know a lot of things, and that's fine. This example is just to sort of show you that these are the things that we're going to cover in more detail later on. Okay, with a hands-on example is what I want to show you. Okay, so the same data set, we've read the data set here. But how do I know if this is, firstly, how do I know how big this data set is? So I'm just going to quickly do some check data.shape. The moment I do a data.shape, what does it tell me? It tells me that 1309 rows are there and 14 columns is what I have in this complete data set. Wonderful. Okay. How do I now, let's say, for example, I'd want to identify how many people have survived and how many people haven't survived. So I'd want to do some data exploration. I'd want to identify how many people have survived and how many people haven't survived. So I'm going to do data.survived, or I can also do it data. So as you observe here, it says data of survived. Basically, this is my data set. Of survived is basically this column. So, and I did the count of the values, and it says 809 people haven't survived. 500 people have survived. That is basically in distribution. So 809 plus 500 is what the whole data set is about, which is good. I could also actually quickly convert this into a chart but this is plotted like a line chart. But if I want it to be like a bar chart, I can simply say kind bar. There you go. So I have a bar chart simply plotted here. Okay. So I know the counts. I'm able to do this as well. Wonderful. Okay. What next? Now I want to identify how many men are there and how many women are there. How can I do that? Same thing here. I'm just going to do this instead of this all the time. So I see 843 men are there, and 466 women were there on board. Brilliant. Okay. Now I want to identify how many people, how many men have survived and how many women have survived. So basically, I want to do sort of a cross-referencing of or cross-tabulation of this column with this column. So I don't know. My assumption is that maybe it might have so happened that men were being good and they let the women survive. And just kidding there, by the way. So it could have happened. We don't know if that is what it is. But yeah, generally in such cases, what happens is that's how it was at least back then. We let the women and the kids alone, and men try to be like the heroes. So what I'm going to do is I'm just going to do a group by of. What do I want to group by? So let's say I want to group by gender. Okay, let's group by gender of, and which column do I want once I group by? I want the sex. Sorry, I want the survived column. There you go. Python seems to be not responding. Just a second. Why is it that this is not responding? A small change that I may have to make because I need to group it by two columns. Right? Then I need the count. So now if you look at it, so you have females under the women. There were 466 women, and out of the 466 women, 339 have survived. But out of the 843 men, only 161 survived. What does that tell you? You could sort of do the, right? You could also do the unstack. So yeah, this is basically the same representation, and it's the same thing. Basically, if you see this, if you look at women, a few of them have survived and a few of them haven't survived. But men, most of them did not survive. Only a few of them survived. So what does that tell you? If you actually do the proportions, you would realize that. But what does that tell you? Do you think gender has an impact on the survival rate? Let's understand one more thing. Let's actually see if this holds good even for young kids, for children, right? So how do I firstly identify children? So in my data set, I have age. Wonderful. Yes, I have the age column. So let's actually see how can I, so based on the age, what I can try and see is maybe I can create a column. First, let's look at the age column, data of age. And if I want to simply look at how the age is distributed, so look at this. This is basically referred to as a histogram. And what it is telling you is on your x-axis here, on your x-axis, we basically have, this is the age and this is the count. So what we are saying is this bar that we see over here is basically number of people between the age of 0 to 10. We had approximately around 75 people. Yeah, it's basically an approximation, but that's basically what we have. And what it is also telling us is majority of the people, because I have this huge bars in this section, but what it tells me is most people are between the ages of 20 and 30, 20 and 40, so to say. So that's like a good thing. Of course, most people are, of course, going to be of a higher age group, and there are very few people. So maybe what I can do is maybe we can look at just this chunk of people. Maybe they actually survived more as well because they're kids, right? So let's actually take a look if that is really the case. So the way I'm going to try and find that is I'm going to try and create a column. First things first. Right now there isn't a column, so I'm going to create a column called child is child. I'm just calling it is young, just for the heck of it. But is equal to, and I'm going to say data of. I'm also going to use another library over here called import numpy as np. Here is where I'm using np.list where, so it's like basically applying an if else clause. So np.where, and now what I'd like to probably see is data of, what's that column, age, when it is less than, so I'm basically just using maybe somewhere around 15 as a reference. Let's go with 18, maybe, I don't know. Then 1, else 0. So where age is basically less than 18, I'm just calling it 1 and 0. 18 is too much of a age, but yeah, I think this is have 18 for now. But we can always come back and change it. So now I have a new column called is young, and I have a 0 or 1 over here. Basically, if you look at these kids are all 1s, and these people are all 0s, have a column 0 over there. So now what do I need to do? So I will have to basically just do the same thing, but this time I'll probably, instead of doing it by sex, I'll essentially do it by is young. What do you see there? Do you think being young had an impact on the survival rate? Yes, most of the young survived. More than 50% of the young people survived. But if you look at the ones who are older, not as much. If you look at the older ones, the survival rate is actually far more skewed, right? So the survival rate in this group is almost 50%, but if you look at this particular group, it's actually almost less than, somewhere around the 30% mark. So clearly, survival rate has, or rather, age also has an impact on the survival rate. Now, Rahul has a question: does age have an impact, or does age group remain similar by gender? We don't know that. We probably have to see this histogram by different sections of the population. So what you could do is you could basically apply a condition wherein we say something like that sex is equal to male, and I want the age column from age. This is the histogram of men, and this is the histogram of women. It's almost similar. If you actually look at it, of course, the counts are a little different because you have more men. But if you look at the distribution in general, I think the distribution almost looks the same. So yeah, this is okay. But then the question could be that would this, again, you could actually put one more over here. You could actually also have one more condition. Like, for example, I could put X and then do this. So now this is basically 3 variables all at the same time. So you're looking at folks who are young. Actually, you know what? Let's put this here to make it easier. So men, children. So this row is basically children for men. And this group is children over women, girls and boys. That's what these 2 groups are. Yeah, so if I don't use the unstack here, so this is how it's going to look like. It's going to look a little untidy. So I just put the unstack so that it.
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. Val. B. Raise. C. Try. D. With. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Sort of converts this into a more prettier representation. That's about it. So if you now look at this group, right? Look at this group. This is insane, right? Girl children, their survival rate is almost like 75%. Boy children, on the other hand, their survival rate is probably not as high. Men, in general, their survival rate is as bad as it could get. Women, on the other hand, their survival is actually quite high. So the group that actually got impacted the most is this. Right? That seems to be the group that seems to have got impacted. So chivalry has its own cost, right? So probably don't need to be at all that chivalrous at times, because all that might happen is it might just become a study in a data point in a study. The point is that. So now what we've been trying to do over the last few minutes is we've been trying to dig into data one after another. We just kept asking questions, and mind you, until this particular point, we just sort of used some very, very simple variables. We just used age, we used the survival column, and that's it. These are the 2 columns that we sort of used, and gender. But mind you, there are a bunch of other columns that are available here as well, which we still haven't dug up into. Now the question is, if we just keep doing this, right? I mean, it will take me an eternity to figure out what would cause somebody to survive. So with this understanding, we definitely know the fact that when somebody is young and if they're women, the likelihood of them surviving is actually quite high. If they're women in general, the survival rate is definitely high. If they're young, your survival rate is high. So we know these as broad patterns, but if I really want to look at the interactions between all these variables that I see over here, doing this manually could be very, very challenging. So that is exactly where we are actually going to start building a model, right? So we're going to try and capture all these patterns using a very, very simple model to understand if somebody is going to survive or not. So I'm going to use data preparation for model building, right? So we're going to do some data preparation for model building. And how do we do that? So I'm going to use firstly, we're just going to do some preliminary description of our data. Actually, you know what, even before we do this, let's look at if there are any missing values within our data. Like for example, in this columns, right, these columns have a ton of missing values. Dot is null dot. If I do a sum, what this is telling me is the age as a data set age as a column has almost 263 missing values. Cabin has 1,000 missing values. There are 1,300 data points, boat and body, home, destination. These all have a ton of missing values. And that's almost like 70-80% of the data has missing values there. So what we're going to do is we're probably going to drop columns which have too many missing values. Age has the lowest number of missing values. Let's see how we can fill that. But we'll probably have to drop these columns because there's too much missingness in there. So how do I drop columns? So I'm just going to say columns to drop. I'm just going to create a list of column names. One is going to be cabin. The other is going to be boat. Just going to say body and home, destination. So for the purposes of this particular exercise, I'm actually going to drop these columns. And additionally, I'm also going to drop one more column, which is nothing but my name. So here's a question that I have for you guys. Do you think your name could be a factor, or one's name could be a factor for somebody's survival? If it is, then it's probably the most bizarre thing that I would ever hear, right? I mean, honestly, name is a unique identifier, right? Name identifies you as a person. So I would love to believe the fact that name has honestly no impact on the survival of a particular person. So for that purposes, I'm actually going to drop the name column. And one more column that I'm also going to drop is the ticket. Ticket as in the ticket number. The ticket number probably doesn't have any bearing, but what may have is the cabin that they're seated in. Actually, the cabin is actually a good column because it might give you an indication of which part of the ship where they're sitting. But unfortunately, the cabin has almost 1,000 missing values. So we'll probably come back and see how we can handle the cabin column later, but definitely the ticket number might not have an impact. So I'm actually going to drop these columns just because logically they don't make sense. And the others because they're way too many missing values. So I'm going to drop these columns. So how am I going to drop them? So data dot drop. So I'm just going to use the drop, and I'm going to say columns to drop x equal to 1. So when I drop it, this is how the data set looks like. And Gayatri has a question. Fare can also be removed, right? Think about it, Gayatri. So the more you pay, it's probably an indication of where you're seated. It would probably be an indication of how affluent you are as a person. So maybe that has an impact on somebody's survival. So which is why I think having it as another column. So yeah, so this is how the data set would look like. If I looks like this is okay, so I'm going to assign it back. So this is how my data looks like right now. So if I look at the missing values, so there are 2 columns that have missing values, actually 3 have missing values in them. So what we can do is we'll probably need to fill these missing values. So how am I going to fill the missing values? There's some interesting ways of filling these missing values. One very popular way, we'll just finish off these missing value filling and then we'll go for a break. Well, just a quick point before we head out there. We're just going to talk about how we'll fill missing values. One very popular way of filling these missing values is filling it with some simple statistic like average, exactly. Filling it with an average. Why would you fill it with an average? I'll give you an intuition and then we'll come back and discuss about this in more detail later. The intuition here is that, take for example, there's a classroom and there are, let's say, 100 kids, and the average of that particular classroom is, let's say, 22. The average age of that classroom is, let's say, 22. If I were to add another person into this particular classroom, and if the addition of that particular person, if it shouldn't change what should be the age of this new person in the classroom in such a way that it doesn't impact the distribution of the kids in the classroom. The age of this particular kid should exactly be equal to the average. So even if I add somebody with the same value as an average, the value per se or the average of that particular classroom isn't going to get impacted. So which is why I think the most popular way of filling this data is by filling such missing values is by average. Some kind of a central tendency. We will learn about this in more detail when we learn about mean, median, and mode in more detail later on. But yeah, it's basically one of the reasons why we fill it with age is because age is like the most popular representation, so to say. So dot age dot fill in a, and I'm just going to say value is equal to, that's it, and I'm going to just say in place equal to true. That would fill the missing value of age for me. Next is going to be fair, same approach, and last but not the least, I'm going to fill the same thing for embarked. But mind you, embarked is not a numeric column, so I cannot compute the mean or the average. So what can I replace the missing value with? There's only 2 missing values in there. So what is the best bet that I can use over here to fill the missing value with? NA is the missing value, right? So I'm going to fill it with the most frequent value, most frequent observation. That's my best bet, right? Because I have, so if you look at dot value underscore counts, I have 914, 270, and 123. So just going to simply fill the missing values with 914. Rashmi has a question. How about dropping those records? Yeah, you could very well do that. Absolutely, yes, you can do that as well. It's a matter of choice. You could try both, right? For the purposes of this example, I'm actually filling them with missing values. You might simply say, hey, Srinath, you know what, there's just 2 records, why don't we simply just drop it? You could very well do that as well. And there's nothing wrong with it. You could try either. These are 2 different paths that we could take. Whichever yields you the best result, you go in that direction. But there's no one right way of doing it. So because I already have only 1300 observations, I'm a little stingy about dropping observations. I'm not very keen on dropping records, which is why I'm going the route of actually filling them with mean. But if you have, let's say, 1 million records, or let's say a few thousand records, a few 10,000 records or 20,000 records, then dropping 2 or 3 observations is not going to be that big of a deal. I'd still be okay doing it. But yeah, it's basically a matter of choice. So yeah, so first things first, if I were to compute the mode, this is how the mode looks like. All right, so what I'm simply going to do is I'm actually going to do the same thing, but the only thing that would change is that this value will be that. That's it, boom, done. So now when I run this, I actually see no missing values whatsoever. So that's actually good. So there were missing values originally. So we decided to drop a few columns that have missing values. And then we realized that there are some more missing values. And what we did with those is we filled them with some values, and then we observed that there are no missing values whatsoever. Great, wonderful. Now what? The next step is, one of the tricky things about Python is that before we build the models are often built on numeric data, meaning your data should just have numbers in them. But unfortunately, if you look at our data, it actually has some string values as well in them, right? Actually has some string values in them as well. The other thing is, as I said, one of the most tricky things about Python is that, as I said, we require our data set to be sort of fully numeric, but unfortunately, we have some string values over here. There are a few ways of handling it. One way of doing this is by we sort of do something like pd.get_dummies of data, and so that's all. That's what I did. So basically, if you look at the embarked column, instead of having one column with S, C, Q, and S, I simply converted that into embarked Q and embarked S. Actually, if I remove this, right, it'll make it even easier. Okay. So I have embarked C, embarked Q, and embarked S. So which is what I did. And what I basically did was, instead of having all numeric values, I simply changed that to instead of having all string values, I simply sort of transformed that into a numeric representation. Now, if you look at my data, the data is fully numeric, which is why what we are going to do moving forward is this data set is now ready to be actually used to build the model. I couldn't have done this because Python would simply throw an error. It would say that, hey, you know what, these columns are not some. So I don't understand what these numbers are, what these values are. So you need to convert. So that's like the first thing that we're doing. So that's basically what this is. So I have my data ready. Now that's okay, doesn't matter. And then the next step is the actual model building process. So to build a model, we're going to do two things. First things first, what I'm going to do is I'm going to split my data into two parts. One is my target variable, which is nothing but data of target variable is nothing but the variable that I'd want to use to my desired output, which is my survived column, and the other column, which is data.drop. So now if you look at X, it's the same data set without the survived column, and Y is just the survived column. Right? So I've just split the two, X and Y. The next thing that I'm going to do from a jargon standpoint, this is sort of called as the independent or the dependent variable, also referred to as the target variable. In this case, X is referred to as independent variables, or also referred to as the input variable. It's also referred to as the output variable, and it's also referred to as features. The features data. X is also your features and Y is your target variable. The most popular is features and target. That's like the most popular terminology there, but yeah. Okay. Now is an interesting step. So this particular step, what we're going to do is we're going to actually split our data into two parts. So what we're essentially going to do here in this particular step is, as I had mentioned, we are going to take our data set, which currently looks like this, right? So you have this is your X and this is your Y. What we're going to do with this is we're going to randomly split this data set into two parts. So imagine you have, let's say you have 1,000 records, 1,000 rows. So what we're going to do is we're going to split this into two parts. Let's say something into 800 and 200. Yeah, 700 and 300 is like 70-30%, something like that. 700 and 300. Now, why do we do this? The reason why we do this is because it's more like we're going to use these 700 and actually build a model. Right? This is going to help us build the model. And we're going to use the remaining 300 to evaluate how good this particular model is. So how does that work? So the way this is going to work is, so as you observe, I have X and Y. So when we split this is going to be X underscore train and Y underscore train. So that this is nothing but your training data set. And we call this data as your test data set, Y underscore test. So basically your data set is randomly split into two parts. This is your train set and this is your test set. Why should we split it into train and test? So here's a simple example, and you can think of it this way. So going to a school, and let's say you're basically learning math or science or whatever. Now, in your classroom, let's say in your textbook, let's say there are 1,000 questions. What you do in the class is you basically provide 700 questions, or you provide solutions for 700 questions in the classroom. and you ask the students to take the remaining 300 questions and ask them to fill this up or take that up as a homework. Why would you do that as an assignment? The reason why we do this is because we sort of give those 300 questions to test if these students have actually learned these concepts. 700 questions are sort of meant to cover the complete breadth of all the problems in your data or in your book. The remaining 300 are like a sample set or like a test set, and you pass these, you give these to the students and ask them to fill these out. So once they come with the solutions, you actually take those solutions and then compare it with the actual solutions and see if they've performed well or not. That's exactly what we're going to do here as well. We use these 700 to actually build the model for the model to learn from these 700 examples. The remaining 300, we will generate predictions for these 300 data set, 300 records, and then compare with the actual values and see if we are correct or not. That is exactly what we're going to do. I hope that makes sense. So how are we going to do it? So we're going to use a model selection import train test split. So if you look at the train test split, this is basically how it's actually going to get implemented. I'm just going to copy paste this here. So what I'm asking it to do is I'm actually asking it to split train x test, y train, y test, train test split, passing x and y into it, and I'm saying 33% and 66%. And I can actually say 30% and 70%. So boom, done. So x underscore train dot shape. Now, if you look at the shape, it's just 916 observations. Earlier, we had 1300 observations. Now it has dropped to 916 observations. And similarly, if you look at y dot shape, y underscore train dot shape, it's the same. It's 916 observations. Same is the case with the test set, right? So same 393 observations and 393 observations on either side. So same set of observations, or rather same volume of observations on either side. It's just that this is going to be used for your training and this is going to be used for the tests. Now I'm actually going to build a model. So from sklearn, by the way, is just like how we are using pandas to build a model, pandas to do some kind of data slicing and dicing. And we're going to use sklearn, nothing but scikit-learn. Scikit-learn is like a machine learning library within Python. So from sklearn dot linear model, import logistic regression. Now, logistic regression is a model, is an algorithm that we're going to use to train. It's a type of an algorithm. Remember, I mentioned that it sort of generates an equation. So this is basically the model generation part. So clf.fit. So when I say fit, this is basically where I'm asking it to actually train. But I'm actually going to pass x underscore train, y underscore train. So I'm passing the x train and y train observations, and I'm getting it to train. So my model has been trained here. Ignore this. This is a warning. Let's not worry about this too much. But long story short, the point is that my model has been built here in this particular step. So one single line, my model is built. Now I'm going to use this model to generate predictions. So how am I going to generate predictions? So xclf.predict of x underscore test. So I'm just passing my test set and I'm generating predictions. So here you go. I have zeros and ones being predicted. These are my predictions. Now I'm going to compare these predictions with my actual one. So predictions df is equal to pd.data frame of just going to be x underscore y underscore test, and this is my predictions. It's going to be, so if you observe, now I have my actuals and my predicted, meaning these were the actual values. So like, for example, if you observe, in reality 1148 did not survive, and we also predicted, our model also predicted that the person would not survive. 1049 on the other hand had actually survived, but our model predicted that the person wouldn't survive. 1159, the model and the actual in reality, both of them have correctly identified, and here as well, our model correctly identified that the person would actually survive. So using this, now what we're going to do is we're going to try and see how well our model is actually doing. So how do you evaluate that? So I have my actuals and I have my predicted values. So how do I evaluate if my model is actually doing well or not? So if you technically think of it, right? So there are 4 possibilities that one could get. So this is your actuals and this is your predicted. So you could get something like both are zeros, This is 0, but it is predicted as 1. This is 1 and this is predicted as 0. And both have been correctly. I mean, in reality, the person survived and you also actually predicted that it would survive. This is the reality and this is model prediction. Right? So you have 4 possible combinations. The best way of sort of representing this is by using a matrix called as a confusion matrix. So the way it looks like is this: the actions and predicted. So if you look at this, this is basically, this section is basically where the model or your data point was actually 0 and it was predicted as 0, or the data point actually, the person actually did not survive and you predicted that the person wouldn't survive. On the other hand, if you look at this column, this section, it's basically the person actually survived and you predicted that the person would correctly survive. So these two are good, but on the other hand, these two sections are erroneous. Why? Because in reality, the person was predicted. In reality, the person did not survive, but you predicted that the person would survive. And here, in reality, the person has survived, but you predicted that the person wouldn't survive. That is what this particular section is. So what we're going to see is we're going to actually try and identify how good or how bad our model was. So let's take a look at this. So confusion matrix off, and then it would ask me to pass the true values and the predicted values. The true values is nothing but my preds df dot actuals, and the other is preds. So here you go. This is how my model currently is behaving. So again, what has been predicted is, or the behavior of your model is as follows. It says 202.106, 202.106, 22 and 63. This is basically how your model is currently behaving. So meaning for 202 observations, the model actually predicted that the person would not survive correctly. For 106 observations, your model actually correctly predicted that the person would survive. For 63 observations, the model incorrectly predicted that somebody would survive, incorrectly predicted that somebody wouldn't survive. And for 22 observations, your model incorrectly predicted that somebody would actually survive. So that is essentially what you have over here. Now, based on these, we can then come up with some kind of metrics, which we will talk about in our later sessions. But one of the most simplest metrics that one can come up with is called as accuracy. So what is accuracy? Number of correct predictions by total observations. So how many did I correctly predict? So 202, this is correct prediction. This as well is a correct prediction. So plus 106 divided by the total number of predictions, which in my opinion is somewhere around 300 odd observations. Basically the summation of all of these. So essentially 202 plus 106 plus 22 plus 63. That is basically what my accuracy is. I can also compute this using a simple function over here. So from sklearn.metrics, import accuracy score, and the way you would calculate accuracy score is just type. So what we're saying is right now my model is 78.37% accurate, given all of this data, given these predictions that we've made for the 393 observations. What we are basically saying is that the model is 78.37% accurate. But of course, there are more other predictions as well, or other metrics as well that we would need to look at. Like, for example, let me give you a simple example of how the metrics would look like. Import. So for example, over here, if you observe, the accuracy is 0.78, and that is exactly what we see over here. Long story short, the point is that we've been able to read a data set, we've done some exploratory analysis, we prepared our data set, we cleansed our data set for our model building. Then we actually built a logistic regression model. This is a logistic regression model. We could build a ton of other models. And then we also evaluated how well our model is performing. In this particular case, our model is 78.4% accurate, but is that it? Or are there other metrics that we need to look at? Yes, there are actually other metrics that we need to look at, and we'll learn about that in more detail in the subsequent sessions. But yes, this is sort of, by the way, this is not the end. This is where this is sort of like the last step over here. So we got the data, we did some processing, we did some analysis, visualization, we cleansed the data, and last but not the least, we actually built and evaluated the model. But of course, this is not where it ends. As I said, we need to then use this model that we've currently built, this classifier that we currently built. We'll have to actually use that and then sort of make this model available for this to be used. In this particular case, it probably doesn't make sense for us to make this available for other cases. But let's say in the case of the Swiggy example that we looked at, the food delivery app example that we looked at, it would definitely make sense for us to make the model available for the application to start using and set up an experiment to evaluate if the model is doing well. Yeah, so that is sort of the typical life cycle of how a model is built. Now the question is, what is it that we need to double click into? Well, there are so many things that we need to learn. First things first, we need to learn how these libraries work. How does Numpy work? How does Pandas work? We need to learn not just that. We also need to learn firstly how to make sense of numbers. We need to learn about statistics. And then we need to learn how to perform visualization. Then we need to learn a little bit about what it means to, what are the typical data pre-processing steps that we need to use. And then what are the different types of models that we have to build. And then we also need to learn how we could use a certain kind of techniques to evaluate the performance of a particular model. Right. So what is statistics? Statistics is a branch of math that deals with collection, analyzing, and interpreting and inferring large amounts of data. Simple as that, right? So interestingly, while machine learning is a field of computer science, statistics is a field of math. So what we're going to do is, like for example, like where is statistics used? Like these are 4 examples. Actually, statistics is used everywhere. Medical research. I'll give you a simple example. So take, for example, the drug discovery process. Not the discovery process, actually, the clinical trials process. That discovery to some extent, but the clinical trials process. So what is clinical trials? Clinical trials is basically a phase of the whole drug discovery wherein a drug is formulated, discovered, and then they actually put this to test to see if that particular drug actually has or actually results in the kind of actually comes up with the kind of results that we expect it to. So take, for example, it could be a drug, it could also be a food supplement, it could be anything, but anything to do with mass audience, it has to go through that particular phase. So take, for example, Horlicks. What is Horlicks? Horlicks is, all of you know what Horlicks is, right? So Horlicks is like your milk supplement, and it's manufactured by GlaxoSmithKline. So if you look at the Horlicks ad in India, what it says is you drink Horlicks, you become taller, stronger, and sharper, right? So that's what they claim. But imagine if Horlicks were to really prove that if you actually drink Horlicks, you're actually going to go taller. Horlicks, somebody let's say raised a query saying you're claiming that some people are going to grow taller if you drink Horlicks, and somebody asks them to prove this, to prove that this is actually true. So how will Horlicks go about? How will GlaxoSmithKline go about conducting this particular analysis? It's actually quite interesting. So the way they do this is by setting up an experiment, right? So they'll design a particular experiment. So what are they going to do? So what they're going to do is they're going to set up 2 groups. So this is control group testing. I spoke about this a moment ago. This is basically the scenario. So they're going to go set up group A and group B. Group A and group B are, let's say, going to have 50 kids. And
just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answers in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
The distribution of their ages is going to look alike, right? Meaning, let's say they all have the same kind of behavior, and they all, let's say in some form or the other, they all are, let's say, of the same age, they all are, let's say, from the same locality, they all have very, very similar background, and they represent, let's say, the population. Each group represents the overall population. Now, what they're going to do is, first things first, they are going to try, and let's say this group will get only milk, and this group is going to get milk with Horlicks. Everything else between these 2 groups remains the same.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
If these kids play for 2 hours every day, these kids also play for 2 hours every day. If these kids go to school by a bicycle, these kids also go to school by a bicycle. So their physical activity and their daily routines, they try and keep it as much as controlled as possible. They try and keep them exactly the same. The only difference, they try to make the only difference between these two groups to be, let's say, milk and Horlicks. Right? Just that this group gets Horlicks and this group just gets milk. So before the experiment starts, what they do is they have group A and they have group B, the start of the experiment and the end of the experiment. Similarly, start of the experiment and the end of the experiment. So what they do is they capture the heights of every kid of group A and group B at the start of the experiment, and the same after the end of the experiment. Let's say they decide to do this for 3 months. So after 180 days, they capture the heights of each of these groups at the start and at the end. So for group A and for group B, what they're going to do is they compute the growth, meaning let's say kid 1 grew by, let's say, 5 centimeters, 2 centimeters, 2.5 centimeters, 3.8 centimeters, and so on. Similarly for group B as well. So now they have some data over here. Now they'd want to analyze if the growth in group A and growth in group B, if they're significantly different or not. If they are the same, then drinking Horlicks is probably useless. If growth in group B is significantly higher than growth in group A, then Horlicks is actually impactful. Horlicks actually has an impact on the outcome. So the point being that from here, the question is, how do we measure if group B and group A are significantly different from each other or not? How do we measure that? That's exactly where statistics kicks in. So statistics will help us answer this particular question. So from here, we'll conduct something called as a hypothesis test, which will help us compare if group A and group B, if they are similar or dissimilar. Right? That's one of the reasons why statistics is super, super important. The other reason why statistics is going to be important is how will they consider genetics? A great question. They cannot, and that's something which is beyond your control, because that is basically one level deeper. See, these are all observational tests, right? These are all observational in nature. Most of the analysis that we do is observational, meaning we observe a certain kind of an analysis, and based on the observational data, we kind of come to a conclusion. But we don't, or rather, our field doesn't sort of go into the into those deeper layers. For that, you'll probably have to set up a completely different experiment. You'll have to understand that. You'll have to firstly profile their gene sequences for each of these groups, and then look at if they are similar or not, and that would be extremely expensive. But yeah, you also have to understand that when you set up these experiments, you also have to keep cost into account. And again, I don't know. I'm not, let's say, an expert in the field of genetics either, so probably they set it up in a different way. So the point is that, again, it is a design decision. It depends on how this experiment is designed. If this experiment is designed to take genetics into account, if they make sure that these two groups are genetically similar as well, then yeah, that'll be great. That'll be amazing. But again, it's a matter of design. It's how you designed your test more than anything else. Again, so going back to the point that I was trying to drive here, of how do we know if these two groups of 50 and 50, if they're actually similar or not? Even with, let's say, regards to age, how do I make sure that these 50 kids actually represent the population of India? I know that this test was conducted on 50 kids, great, on either side, overall 100 children. But how do you know if these 100 kids are actually a true representation of your population? Do they represent the whole of India? Do they represent the overall behavior of all kids in India? So that even if, let's say, the test comes out to be positive in favor of Horlicks, then will people be okay to accept this as a test? Or because then you would still need to make sure that this particular test is sort of applicable for the whole of India. Is that a fair assumption to make? It's the same thing, right? COVID vaccines these days, right? I mean, the question is, most people say, hey, you know what, you shouldn't be taking Covishield or you should be taking Covaxin because this was tried out on different people and it worked for the Western population. It hasn't been tested on the Indian body constitution, so we don't know if it's going to work well or not. So there'll be, when there are 10 studies that are going to speak for a particular for a certain thing, there will be 100 other studies coming in that will try and debunk that particular theory. So long story short, there will of course be these discontinuous discussions about if the test is good or if a particular product is good or not. But I think what will make this simple is if you take the subjectivity out of the equation, if you look at it objectively, then statistics will give, nobody is going to question the numbers. People are going to question the source of the numbers, but nobody will actually question the numbers themselves. So that is what statistics gives you. Statistics gives you a methodology to evaluate these numbers. But statistics, of course, if the numbers are bad or if the numbers have been fudged, then what can statistics even do? Right. So statistics gives you a methodology to compare groups, conduct these tests. But more often than not, the question or the issues that you see out there is not that the numbers are or the statistics is wrong. It's just that the folks who actually put these tests together, they probably did not design the experiment correctly. But yeah, that's basically how these studies typically work. So again, this is essentially one example where statistics can come in very, very handy. Another very cool example is, as I said, I work for a beer brewing company, and when let's say a beer, or let's say even, for example, any product that is being manufactured at a large scale, how do companies make sure that the product is actually of the right quality? So they have a QC team, a quality control team, which is responsible for running this. So every time there's a new batch of product that is being brought in or being manufactured, the quality control team actually collects samples from the conveyor belt, or let's say through the manufacturing process, take that and then run tests at the background to ensure that the product quality is exactly how it is supposed to be. And they're responsible for publishing these results back to the company, and companies responsible for publishing these to food, so to FDIs, or let's say even the Indian, or let's say the respective government regulatory authorities. So whenever audits are done, that's what they're that's how governance is set up as well. So again, nobody questions the numbers. The numbers are never going to be wrong. If the tests are incorrectly conducted, then nobody can do anything about it. Or if the tests are fudged, then nobody can do anything. But yeah, that's basically how statistics is going to really help us. So stock markets, another classic example which will help us do some forecasting about if a particular if a stock is going to improve over the next X number of days or not. Sales projections, will the sales of a particular company improve or not? Weather forecasting, again, will the weather, will it rain in the next X number of days or not? These are all where statistics play a very, very important piece. The first and the foremost question is sampling. So first things first, how do you, as I said, right, how do you make sure, what is sampling? Sampling is basically a process of collecting data to perform an analysis. So if I want to do and run an analysis, I need to collect data. How do I collect the data? So for example, if I want to analyze the salaries of all IT employees in India, then I need to collect data. Wonderful. But what data do I collect? Do I actually go and collect all the salaries of everyone in India? Well, trust me, that would be great if we can actually collect that data. But tell me something. Do you think we'll even be able to collect that much amount of data? Probably not, because A, collecting that data is going to take a lot of time. B, the process is extremely expensive, because even in terms of money, right? Because it's a very time-taking and a tedious task. So what we do is, instead of actually working with the complete population, we actually draw a sample, right? A sample is a subset of the population which is analyzed to make its inferences. So population is the entire data set as the whole of population of a country, or entire data set of all of, let's say, the IT employees in India. The sample is a smaller subset, is a subset of that particular data set with which we're going to try and draw some analysis. Now, What is a sampling frame? A sampling frame is a list from where a sample is selected. So like for example, it's not always necessary that your population and your sampling frame is the same. Sampling frame is basically the list. So if, for example, I need to get all the salaries of all employees in India, NASSCOM, which is the national scale, whatever, I'm not fully aware of the abbreviation there, but the point is NASSCOM, who is that is a skills registry, organized body in India, is supposed to actually have some of that data. But does NASSCOM has all of that data? Probably not. So for me, NASSCOM is like the sampling frame because I'm essentially drawing a sample from that list. But yeah, I might only assume that the sampling frame is my population at times because I don't know, even if I have actually access to all of that data. So sampling frame is like a list. It's like a citizen registry, or it's like an employee list, or it's basically the list from where we actually generate a sample. At times, when we talk about a sampling error, sampling error is the error that leads to our sample not accurately representing our population. Now, meaning when we actually sample our data, when we generate a sample, when we actually draw a small sample, there are two reasons. There is basically, what may happen is when you actually sample, you might end up sampling in such a way that your sample is sort of biased towards a certain kind of a population. Unfortunately, let's say, in your population, let's say you have 50% men and 50% women, but when you drew a sample, you ended up drawing, let's say, 75% women and 25% men. So that's a sampling error, right? Because you ended up drawing a sample which does not represent the population. So you need to make sure that your sample is always representative of your population, right? I'll give you another example. Surveys is a classic example, right? When you set up a survey, so like for example, at the end of every call that you make to a customer care, right, they ask you to rate a call. Now, if you've ever observed, these customer care representatives, they don't offer everybody that particular option. They only offer that option to X number of people. They only offer that as an option to people who they think they've answered the query quite well. So when you look at that data is skewed already because that data is biased already. That data is only taking in information of people who have responded back positively. Does that make sense? Yeah. So survey, first things first, is skewed. And secondly, even if you're offered that particular option, only certain kind of people actually answer back. Take, for example, your Glassdoor reviews. Who on the planet actually has time and effort to open Glassdoor and write a review about a particular company? Nobody writes it. The people who write it are the ones who have had a bad experience and who want to actually rant about it. So that's their place to vent their anguish and their anger about Glassdoor. Point being, again, websites like Rotten Tomatoes or IMDb or let's say Glassdoor, these reviews again are only going to have reviews when something actually goes wrong. So the sample is actually quite biased already. So you have to be very careful when you're dealing with this. So such kind of error is typically referred to as sampling error. So you have to be very careful when you're dealing with data, right? You have to be cognizant about the sampling error, and you'll have to make some steps to actually resolve these sampling errors. The other is non-sampling error, which is basically, so take for example, you're capturing information about salaries in India, let's say salaries across the globe, and unfortunately, it so happened that the salary column is only the magnitude is being captured, the units are not being captured, meaning that currency is not being captured. So like for example, for somebody who earns let's say 20 lakhs in India, right, 20 lakh rupees in India, and you take for example somebody who earns let's say $100,000 or one lakh dollars in the US. If you disregard the currency, the numbers will tell you a completely different story. It will show as if the Indian is actually earning more than the US guy. But in reality, the units are not correctly standardized. If you actually standardize all of them to INR or all of them to the USD, then is where you will actually get the right kind of representation. So non-sampling error is, the issue is not with drawing the sample, the issue is with the collection. The data was not collected correctly in the first place. So for example, if I'm trying to capture the temperatures in India, unfortunately, at certain cases, the temperature is, let's say, captured in centigrade scale, and in some cases it is captured in Fahrenheit scale. And if I put both these in a single column, if I try to compare these numbers, the numbers might look completely haphazard, and it might not make any sense, right? So again, we have to be very cognizant about how and the scales that we're using to measure these data, and also maybe the equipment itself is wrong. Maybe the equipment is bad. You would actually see this more often than not. You measure yourself, your weight at different places. There is definitely a difference in each machine. So certain weighing scales give you are probably a little more liberal. Certain weighing scales give you a little more conservative. They show you lower weights. So again, challenges with equipment, challenges with with data collection process. So that is non-sampling error. That has nothing to do with the sampling process. It's just that the data was collected differently. So again, you have to be very cognizant about how it's measurement error, exactly, right? So you have to be cognizant about non-sampling errors. Again, both sampling errors and non-sampling errors, you will have to be very, very careful and cognizant about trying to handle them. And you just have to be aware. I mean, how can you resolve this? There is no one solution to resolving this, right? So because you have to make sure that such errors do not occur in the first place. If it occurs, then the only way that you would know if this is an issue or not is if you really know end to end how this data is collected and where it is stored and how it is transformed and how it is actually landing with you. So as a data scientist, it is your responsibility to understand that complete process. Else you will not be able to iron out any of these issues within the data if at all they exist in the first place. There are three popular ways of extracting or performing sampling. One of the most simplest one is called as random sampling, or also called as simple random sampling. Now, simple random sampling is basically like, let's say, we must have come across these kind of problems in our childhood, right? You have a bag, and in the bag has, let's say, 100 balls, and you need to pick, let's say, 10 balls out of it. So when you randomly pick those 10 balls, and basically there is no condition in how you extract those sample. Every ball has an equal likelihood of getting picked. So that kind of sampling is what is referred to as simple random sampling. So as you can read the definition over there, simple random sampling is the process of selecting a subset from a population such a way that every data point has an equal likelihood of getting included in that particular sample. So there isn't really, you're not sort of applying any kind of pseudo condition or any kind of conditioning on top of your data extraction process. You're genuinely randomly extracting your sample. So that's one type of sampling technique, simple random sampling. And many a time what we may observe is simple random sampling actually is good enough to represent your population. But at times what may happen is, if you want to be doubly sure, so let's say, for example, your population, let's say, take for example city, right? There are 3 cities, A, B, and C, right? Your data set is basically covering, let's say, 3 cities, and let's say you have 1,000 observations in your population. So the distribution is something like 500, 200, and 300 observations. So you have 500 observations coming from city A, 200 observations coming from city B, and 300 observations coming from city C. Now, you would, let's say, want to draw a sample from this data set, right? You want to draw a sample. So when you perform a sample, let's say you'd want to extract a sample of 100 records. You want to extract 100 observations from this. Now, when you extract 100 observations from this, if the sampling actually happened correctly, what should have happened is, you should have ideally had 50 observations from A, 20 observations from B, and 30 observations from C. Because if it is a perfect random sample, and if the sample were to represent the population, then I would expect the same kind of representation, the same proportion of the city sort of being represented on either side. I would expect the 5:2:3.
the 5:2:3 ratio to sort of be maintained on in the sample as well as in the population. I would ideally expect something like that to happen. But because that might not happen many a times, because again, you're randomly sampling. So what may happen is, because when you randomly sample, what may happen is you may end up picking 55 observations of this, right? 25 observations of this, and maybe only 20 observations of C. That might happen. And it's not because somebody deliberately did it. It's just that because you're randomly sampling, you might end up sampling A more, B is slightly lower, and C is slightly lower, and B is slightly higher, and C is slightly lower. It may happen. These are small aberrations, and it actually may happen. But if you would want to make sure by hook or by crook, you actually maintain the same kind of the same type of ratio. So what we do is because you'd want to generate 100 observations, which is basically like 10%, you want to generate a 10% sample. So what we do is we perform a stratified sampling. So what is a stratified sampling? So when you perform a stratified sampling, you basically split your data into 3 parts. In this case, 3 parts because you have 3 cities. If you had 5 cities, you would essentially break it down into 5 parts, respective cities. You generate 10% from this, you generate a 10% random sample from this, and generate a 10% random sample from this. So when you generate a 10% random sample from this, you'll get 50 observations, you'll get 20 observations, and you'll get 30 observations. By doing this, you are always guaranteed to have the same kind of representation as your original population as far as city is concerned. Does that make sense, everyone? So by doing this, what you're making sure is you're making sure that the same representation is maintained as your original population. There is one more type of sampling, which is referred to as systematic sampling. So systematic sampling is typically performed, let's say, when you're collecting the data actually. So let's say, for example, you're generating the data in a supermarket, right? Let's say you're collecting some kind of right? Let's say somebody is standing at the door of the supermarket, and this guy is, let's say, running some kind of a survey. So this guy is actually trying to collect some information from people who are walking in. So every time somebody walks in, this guy is responsible for collecting the data. Now, if this guy randomly starts collecting the data, it might so happen that he might just end up collecting data from one kind of a population, either from men or from women, or majorly from men, majorly from women. That's probably also because when you actually look at number of people who walk into a supermarket, in certain areas, it's probably only women who majorly come to a supermarket and not as much with regards to men. So what may end up happening is that this guy might only generate data from women and not from men. So what this guy then does is he performs his sampling approach in a very systematic manner. He says, I'm going to first gather data from a male, then a female, then a male, then a female, a male, a female, and so on and so forth. Or in any other manner. He could have also said, so male, male, female, male, male, female. He probably follows a certain kind of an order, certain kind of a system with which that data is collected. So this kind of technique is what is referred to as systematic sampling. Now, mind you, systematic sampling is not fully random. There is some kind of a pseudo algorithm that goes along with it. There is some kind of a system that you put in place while you're actually generating the data. Or he might also decide that, this data is actually very, very large. So this guy might actually say, there's no point in collecting data from every guy who walks into the store. So let me only collect this data from every 5th person who walks into the store. So 1, 2, 3, 4, 5 collects the data. 1, 2, 3, 4, 5 people walk in. On the 5th guy, he collects the data. Another 5 people walk in. The next guy, he collects the data, and so on and so forth. So every 5th guy who walks into the store, this guy collects information. That is also another kind of a systematic sampling. So this process is what is again referred to as systematic sampling. It's another kind of a sampling technique. Mind you, there are other ways as well, but the most popular ways are as I mentioned. So one is random sampling or simple random sampling. The other is stratified sampling. And last but not the least, we have systematic sampling. Right? These are the 3 different types of sampling techniques that we have at this particular point. Now, The other point also is, so just to kind of go through that particular definition, stratified sampling is the process of dividing your samples into layers or groups and then performing random sampling on each of the groups. So, which is what we just saw. The other is systematic sampling, which is systematic sampling is the process of selecting your sample by picking every kth element in your population. You don't need a list for this, but it's just that you're generating this data, data point after data point. So now once you generate these samples, of course, sampling is one, but once you generate these samples, that's when you need to start running some kind of aggregations on top of these samples. I have a population. Out of the population, I've generated a sample. I've identified, let's say, a certain group of people within India, and I've actually captured, let's say, all their salaries. Let's say my purpose is to identify if the salaries of people in India is the average, the average salaries of all people in India, or what is the typical salary of all data scientists in India. Let's say I want to identify that as a number. So to do that, one of the many things that we will have to perform is, as I said, you'll have to do the sampling. You need to identify the right group on which you're going to run this analysis. But more importantly, once you identify the group, you should then be able to represent those salaries in an efficient manner. So what do I mean by that? So let's say I have collected information about name, and I have collected, let's say, salary, right? And let's say I've collected this information for, let's say, 100 people. Now that I've collected all of this, and let's say I also collected some more information about what the age of the particular person is. Now, what I need to do is, now I should actually be able to run some kind of aggregations on top of this data. How do I, what kind of aggregations can I run? First and foremost, we often refer to the most preliminary type of aggregations as central tendencies, meaning I want to identify what is the typical behavior of all the data points that I have over here. What is the overall, how are all these data points behaving? So to compute the central tendencies, we have three very popular measures: mean, median, and mode. Mean, median, and mode, we all actually have been using mean, median, and mode in some form or the other. We've been using that since our childhood. We all know what mean, median, and mode is. So mean is simply nothing but it's also called as the average, right? So mean is a mean, median, and mode. These three are different metrics that sort of represent the centrality of your data. What is the central behavior of your data? So they sort of tend to give you what is the typical representative behavior of your data in a way. So what is mean? So if you, let's say, have n data points, right? N data points or n salaries. So let's say x1, x2, x3 all the way until xn. So your mean is nothing but x1 plus x2 plus x3 plus and so on up to xn divided by total number of observations. And you also will see at times it represented by, right? It's also sort of represented using this summation symbol. This stands for summation, right? That's basically what your mean is all about. Then we have something called as median. Now, what is median? Median is...
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. Val. B. Raise. C. Try. D. With. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Essentially, the centermost data point, right, in your data. The centermost data point in your data is what is referred to as median. So take, for example, you have numbers 10, or rather, let me add one more data point. Let's say you have 10 observations. Okay? These are the 10 numbers that you have. First things first, to compute the mean, average or mean. Average or mean. Mean is simply nothing but the summation of all of these data points divided by 10. Divided by 10 because you have 10 data points. So the summation is 40, 50, 60. 60 plus 40 is 100, 120, 150, 160. 160 plus 60 is 220 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 data points, which is 22. So the average or the mean behavior of this particular group is 22. Okay, that is good. The other is median. Now, what is median? Median is the centermost data point of this particular group. So when you have to identify the centermost data point, the most important thing that you need to do first is to order these numbers. Most importantly, you need to firstly sort your numbers. You need to order them in either the ascending order or the descending order. So let's say first we order them in ascending order, or it doesn't matter, ascending or descending order is the same. So let's say I order them. So the smallest value is 10. I have 1, 2, 3, 4 tens. And then I have, let's say the 20s, I have 20, 20, 20, because I have 3 20s. And then I have 130, 140, and 150. 30, 40, and 50, right? So this is basically your data points, the sorted data points. Now, in this particular point, in this particular case, what we will then have to do is I will then need to identify between these data points. I need to identify what is the centermost data point. Now, unfortunately, I have 10 points over here. So what should be ideally the centermost data point, right? So the centermost data point is, because I have 5 data points here, right? And then I have the remaining 5 on this side. What is a centermost data point? So I don't really have a centermost data point. So what I typically will have to do is I'll have to take an average of these two. So what is the average of 20 and 20? The answer is 20. I will have to take the average of these two data points in this particular case. Okay, that is basically your median. That is how you compute your median. So median is simply nothing but the centermost data point of your data. So you need to order your data first in ascending or in the descending order, and then pick the centermost data point. That is basically how you compute your median. Then the third metric is mode. What is mode? Right? What is mode? So mode is nothing but the most frequent observation. So in this particular case, what is the most frequent observation? Your 10 is the most frequent observation, hence your mode is 10, because 10 is most frequently repeated, so hence 10 is the most frequent data point in this particular case. Okay, that's it. So these is basically how you compute your mean, median, and mode. Now, so right now, whenever you talk about the data, whenever we talk about distribution, this is how we also always try and compute mean, median, and mode, which is, so when somebody asks you, hey, when given a particular distribution, if you were to describe a particular distribution, the first and the foremost thing that you do is you describe the centrality of your distribution. So you can tell somebody the mean, median, and mode of that particular distribution, and then sort of gives people a sort of an idea. Okay, the typical central behavior of this particular distribution is around so and so. But what it doesn't give, what the central tendencies fail to give, is they don't give us a sense of how spread out this data is. It tells us where the center is, or intuitively it sort of gives us an idea of where the center is, but it doesn't tell us how spread out this particular data is. So to capture that, to basically capture that spread, we then typically talk about a few other measures of spread. So these are central tendencies, and then we capture something called as measures of spread. So to capture spread, the first and the foremost thing that we capture is range, and then we have something called as interquartile range, also short form is IQR, and then we have variance, and then we have something called as standard deviation. These are a few measures that one can use to explain spread. These are 4 popular measures that sort of give us an indication of how spread out your data is. Now, first things first, simply, what is range? Range is nothing but minimum, or rather, the other way around actually, maximum minus minimum. So take a distribution, compute the maximum value, compute the minimum value, and take a difference of the two. If the range is very high, then what you would typically see is you would see that the what you would typically see is that the range would be typically high, or that what you would typically see is that your data points are quite spread out. If your range is small, then that's an indication of the fact that your data points are not spread out. So first things first, so that is what range is. So in this case, if you were to compute your range, your maximum value is 50 and your minimum value is 10. So your range is 40. Now, mind you, range doesn't give you everything, because range simply says what are the bounds of your data. Sort of this takes the bounds into account, but it doesn't take, right? It doesn't take the typical behavior or the typical density of your data. Meaning, do I have more data points towards the minimum values? Do I have more data points towards maximum values? Like, for example, I may have a distribution that looks like this. So I may have a distribution that looks like 10, 10, 10, 100. And then I may have a distribution 10, 20, 80, 100. And then I might have a distribution 10, 90, 91, 92, and 100. All these three have the same range, right? All these three have the same range. So this, the minimum and the maximum value is 90. The range is 90 here. The range is 19 here. Also, the range is 90. So what range fails to capture is range fails to capture the density of the data points. It doesn't know where the data points are. It doesn't tell us where the data points are. So which is why range as a measure is okay. It's easy to compute, but it's sort of incomplete. We still need something more robust, something that captures more of the density, so to say. So then comes something called as interquartile range. So it's like range, but it is slightly different. What is interquartile range? To understand interquartile range, we need to understand firstly what is a quartile. Right? Firstly, let's understand what is a quartile. To understand what a quartile is, it's actually quite simple. Quartile is, let's say you have your data, right? And let's say you've sorted your data in ascending order or in descending order. So in this case, let's say you sorted your data in ascending order. So you have your minimum value in here, and then you have your maximum value here. So let's say you have x1, x2, x3. So many data points. Doesn't matter how many data points you have. What quartiles are is basically, so you have your minimum and then you have your maximum. Now, what you need to do is split your data into quartiles. What do you mean by a quart? Quart is nothing but a fourth, right? Quart stands for 4, right? The quartile is split your data into 4 equal parts. Sorry, this was probably not equal. 1, 2, 3, and 4. So there you go. So this is your quartile 1, this is your quartile 2, this is your quartile 3, and this is your quartile 4. 4 quartiles is what you need to split your data, right? So this is 1, 2, 3, and 4. Let's say you have 4 parts that you split your data in. So the minimum is this, maximum is this. This, or the point where you split your first to second, or first quartile to second quartile, is what is referred to as your Q1. This is typically referred to as your Q1. Also, your 25th percentile. What do we mean by percentile here? Percentile is simply nothing but, so when you say that you are at the 25th percentile in your class, what that means is you're ahead of 25% of people in your class. That is essentially what you mean by 25th percentile. Right? If you say you're at 99th percentile, that means you're ahead of 99% of people in your class, or you have scored 99%, or you've scored better than 99% of people in your class. That's what you mean by 99th percentile. So Q1, because it's 1/4 of the data, this is 4 equal parts, right? 1/4, 1/4, 1/4, and 1/4. So because this data point is ahead of 1/4 of the data, which is not even 25th percentile, this is your 50th percentile. 50th percentile is also nothing but your, what is this point over here? 50th percentile is the centermost data point. It's the center, exactly. What is the other term for the centermost data point? Median, exactly. This is Q2, or also referred to as your median. Perfect, exactly. This is Q2 or your median. Then you have Q3. This is your 75th percentile. And then this is your max or your 100th percentile. So if this is your 100th percentile, then what is this? The minimum value is nothing but your 0th percentile, because the minimum value is ahead of nobody else, is ahead of no one else within your data. So the point is, whenever you get your data, you split your data into 4 parts, and based on the 4 parts, you then determine. So let's say, for example, you have, right, let's say take this series, right? So you have 10, 10, 10, 20, 20, 20, 30, and 50, right? So you need to basically split this into 4 parts. So this is one part on either side. This is how you're going to split the whole thing into 4 parts, right? So your minimum value is 10, or your 0th percentile here, right? Your Q1 or your 25th percentile is nothing but the average of these two, which is 10. Your Q2 is nothing but the average of these two, because this is 20. Your Q3, which is nothing but the average of these two, so this is going to be 25. And then you have your maximum value, which is nothing but 50. Now the question is, what is interquartile range? So Q2, Q3. Interquartile range, see, is nothing but Q3 minus Q1. So if you remember, range is nothing but max minus min, meaning you take a difference of these two extremes, right? You basically take a difference of these two extremes. That is what is, right? This is what is range. Interquartile range is basically the difference between these two, right? So IQR is Q3 minus Q1. Now, why Q3 minus Q1? What is so special about Q3 minus Q1? So here's the thought process behind it. So whenever you look at data, right? So take, for example, salaries of people. Now, when you capture all the salaries of all your employees within your company, and if you actually sort them, so the first part, the minimum to max, the minimum to the Q1, these are people with very, very low salaries. There are very few people with very low salaries, right? And there is that last set of last percentage of data, last 20, the first 25%, the last 25%. These are people like your CEOs, like your executives, like senior executives and leaders within your company, and these guys actually end up earning more, right? So these are people who earn quite a bit, right? So to actually understand how spread out your data is, one of the best thing to do is, get rid of these data points on either side. Ignore this, just concentrate on the real meat of your data, which is this part. And then based on just that middle part, you then compute the range of this particular middle part, which is nothing but 50% of your data. So this is what is referred to as interquartile range. If you have a very high interquartile range, that means the center part of your data is actually quite large, meaning your data is extremely spread out. Even the center 50% of your data is also extremely spread out. Even after removing the 25% on either side, you still have a very high IQR, gives you an indication that your data is very, very spread out. So basically, you're concentrating on just the middle portion of your data, and then you're trying to draw an inference of the middle portion of your data, or of your distribution, so to say. So that is what is referred to as interquartile range. Hope that makes sense, everyone. So we spoke about two. One is range, and then we spoke about interquartile range, right? Then the next is interesting. The next part is what is referred to as variance. Now, what is variance? The variance actually comes from a sort of a interesting background. It's sort of like when you're computing variance, the idea behind computing variance is to sort of try and identify how far away is a data point from the centermost data point. So take, for example, first things first, even before we go and learn about variance, let's talk about some interesting ways of representing this data. Many a time, whenever we talk about distributions, right, distribution is simply a set of data points. When we talk about distributions, distributions are often represented using a histogram. What is a histogram? A histogram, we saw a histogram. You essentially will have, let's say, age or whatever metric, age or salary, or weight or height or whatever metric, doesn't matter. And then you will have the count. So 0, 10. So if you look at the typical age distribution of people in India, you have lesser number of people in the group of 0 to 10, and then from 10 to 20, you have a significant representation of people in the group of 10 to 20. 20 to 30 is where we have the maximum representation in India these days, right? And then from 30 to 40, between 30 to 40, you have a fairly decent representation. 40 to 50, 50 to 60, 60 to 70. So India has this kind of a representation, right? On the other hand, if you take, for example, Japan, right?
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Japan, on the other hand, has a slightly different representation. So Japan has less people in this bucket and has more number of people in that bucket. So Japan has a slightly different distribution, and that's because of the unfortunate incidents of Hiroshima and Nagasaki. Unfortunately, they have very high mortality rate. They've had a very high mortality rate, and because of which not a lot of kids survive. So most people who are right now, they're they're sort of older people who survived through those phases. So which is why they have a slightly different distribution. So the green bars sort of represent Japan, so to say. If you take, for example, India, right? These bars, right? More often than not, people prefer, instead of representing these as bars, people actually prefer representing these using a smoothened curve, right? So we could simply represent this as a curve, right? Because it's a continuous set of values. So you would more often than not see something like this, sort of a curve. Same, you have age, and then you have a count. Now, this curve can look differently. It doesn't always have to look so neat. It might actually look like this. It might actually look like this. It might look differently. It might simply just look like this, and it might have multiple bumps and so on and so forth. So it could look in whichever form or shape, right? It could look like that. It could look different, but just for example purposes, I'm sort of giving you a representation. So this is basically it's called as a histogram, or popularly also known as a frequency distribution curve, because it simply represents a frequency of your distribution, right? It simply gives you how your frequency is sort of distributed across your metric, whatever your metric is. So this is how distributions are typically represented. So whenever we talk about distributions, we will often be representing them using some of these curves. So do not get confused when we talk about these curves. Let's take a simple example, and let's actually try and draw this frequency distribution chart, right? So how do you actually draw it? So take, for example, some of the data, 10, 10. So let's say I have, in a swimming class, right, I have people of age groups in this particular manner, They are 10 people, and their ages are as follows. Let's say in that particular fashion. This is how, let's say, my swimming class is sort of distributed. 1, 2, 3, 4, 5, 1, 2, 3. Perfect. I have 10 people in my swimming class, and this is how the population is sort of distributed in my swimming. How do we actually now represent this frequency now? So what people often do, and this is how we learned in our school as well. So you have age, and then you have your frequency, right? Count. So first things first, so you have 10, 20, 30, and 50, right? So between 10, how many people do we have with the age of 10? In the age of 10, I have 1, 2, 3 people. In the age of 20, I have 4 people. The age of 30, I have 2 people. And then with the age of 50, I have 1 person. Now, I would want to transform this into a frequency distribution chart. So how do we represent this as a frequency distribution chart? So the best way of representing this is by simply putting together a small curve. And then this is 0, 10, 20, 30, right? So ages between 0 and 10, I have, so basically 10 is less than or equal to 10. That's what I mean by 10. So I have 3 people. I have 3 people in this particular group. And then from 10 to 20, including 20s, I basically have 4 people in this group. From 20 to 30, I have 2 people in this group. And 30 to 40, I have nobody. And then 40 to 50, I have 1 person in this particular group. So if I were to sort of represent this as a curve, this is how this curve would look like. Right? I could change it. That's how this curve typically looks like. So this distribution curve is not the most perfect distribution curve, but that's okay. So I have like two bumps over here. This is one bump and this is another. This is basically your histogram. Okay. And it's a way of representing your data. So this is one of the most popular ways of representing your distributions. We sort of need to get used to talking about data and representing our data in this particular fashion in the moving forward. Now let's talk about variance. So what is variance? Variance, again, is a measure that tries to capture how spread out your data is, just like this. So let's talk about this here. So variance, what it tries to capture is it tries to capture the, I'll first probably define this in English, and then maybe we can convert this into math in a minute. So somebody thought, hey, variance is, can we not capture the average distance between every data point and mean? Why mean? Mean is the centermost data point. So it's something like, basically somebody is trying to say, hey, this is how my distribution is. So my mean will be somewhere over here because it's like the center. So now all that I'm going to do is for every data point, I'm going to capture how far away it is from this, and then I'm going to compute an average of it. So if the average distance is very high, then that means my variance is going to be extremely high. The average distance is low, then the variance is going to be low. So if imagine you have a set of data points, x1, x2, x3, all the way until xn, right? So first things first, what we are going to do is we are going to compute the mean. So mean is, let's say I represent the mean as x bar, right? So I compute the mean. Mean is nothing but the centermost data point. So you compute the mean, x1 plus x2 plus x3 on so on xn divided by n. That is nothing but your mean. So now what I'm going to do is I'm going to try and compute the distance from every data point, x1 minus xn plus x2 minus xn plus x3 minus xn plus and so on. Not xn. Oops, really sorry. x1 minus x bar plus x2 minus x bar plus x3 minus x bar plus and so on. xn minus x bar. So what I'm trying to do over here is I'm just trying to compute the distance of every data point to the mean. But remember, if I just compute the distance like that, what may happen is for these data points, I might actually get a positive value, and for these data points, I might actually get a negative value. So the values might actually cancel themselves out, right? Because if you have data points on either side, for certain data points, I'll get a positive distance, and for certain data points, I'll get a negative distance. And if I'm really trying to compute the average distance, I just need the magnitude. So the values might actually cancel themselves out. So what do I need to do here to avoid that? There are two ways of doing it. One, I can just take the positive values. I can sort of put a modulus over here, right? It's like a way of just computing the positive value. Or more often than not in statistics, what people do is they square the values, right? They square the values and you divide that whole thing divided by n, because you have n data points. So which is where variance was supposed to be the average distance, but it ended up being average squared distance between every data point and the mean, right? So the formula of variance is simply nothing but summation of xi minus x bar the whole square divided by n. So I is equal to 1 to n. Right? This is basically what variance is, and it's referred by sigma square. This is how variance is typically represented as. Now the problem with this is, so imagine if I am, let's say, trying to compute the variance of age, right? Let's say this is the distribution of age, and age is in, let's say, years. If age is in years, here I'm taking the difference, but I'm squaring the difference as well. So this will end up being year square. This is year square, right? So something like, something like this. So when you're computing the area of a rectangle, this is length and this is breadth. This is in meter, this is in meter. So when you do L into B, what will you end up getting? This is a meter and this is meter. So the units that you'll get is meter square. Similarly here as well, I am not taking a difference. I end up taking a difference and I end up squaring it as well. So when I square it, this ends up being year square. What is year square? Year square doesn't mean anything. Meter square means something. For many units, squared units doesn't make any sense. So which is why people said, hey, this is okay, but this doesn't physically mean anything. I mean, this is not distance, this is squared distance. What does it even mean? It doesn't mean anything. So that's when people said, okay, this is okay. Let's try and sort of bring this down, simplify this down. So that's when people came up with something called a standard deviation. The standard deviation is simply nothing but a square root of your variance. Because we are squaring it here, we're applying a simple square root on top of it. The square root of variance is simply nothing but your standard deviation. So standard deviation becomes like the average distance between every data point and mean. Not literally, but because you're applying a square root, it sort of tries to bring them back. So it's like a root mean square distance of every data point to the mean. So what does this tell me? What does variance and standard deviation tell me? So if the standard deviation is, let's say, 5 units, what it tells me is on an average, every data point from the mean is 5 units away. Or on an average, every data point is 5 units away from the mean. Right? If the standard deviation is 100, then that means that every data point is 100 units away from the mean. So it sort of gives us an indication of how far away a particular data point is from the mean, how far away or how close a particular data point is from the mean. That is basically what variance really is over here, or standard deviation is over here. So standard deviation and variance sort of give us an indication of that. Yeah. So the reason, so if when I say 5 units from the mean, just give me a second. I don't know if my video is clear. I guess let me adjust my mic. Just give me a second. So every data point from the mean. So when I say the unit, if standard deviation is, let's say, 5 units, what that basically means is every data point is on an average 5 units away from the mean, from the average. So like, for example, the average distance of every data point from the mean is 5 units, is what we're essentially saying with standard deviation, right? Similarly, even with, let's say, a standard deviation of 100, that is exactly what we're trying to say as well. Every data point is 100 units away from the mean. That is basically what your standard deviation is trying to say. Let's try and actually compute this. Right? Firstly, high variance, is it good or not? Then there's nothing about good or bad. We are just trying to describe our data. So having a high variance in some cases might be good, in some cases might not be good. What we're trying to say is, descriptively speaking, our data is extremely spread out. That is what we mean by a high variance or a high standard deviation. So yeah, that's basically what it is. It doesn't talk about good or bad. There's nothing good or bad. High variance or low variance can mean good, can mean bad, both are the same. So it doesn't mean anything about good or bad. It's just an indication that your data is quite spread out. Let's take a simple example. Let's actually try and compute it. Yes, it's just for data spread. As simple as that. It just puts a number against how spread out your data is. That's all that standard deviation and variance are supposed to be. So let's take a look at this, right? So take, for example, a data point, right? So this is, let's say, the salaries of people, or I don't know. Let's take, for example, the height, right? Let's say let's take, for example, this is the height of a crop. So meaning, so let's say you have 5 or 10 crops, or 5 crops, 10 units, 15 units, 25 units, 20 units, 10 units. And let's say this is height. So this is, let's say, meters. And let's say 10. Yeah. So let's say this is my, these are, let's say, the 5 data points that I need to compute, let's say, variance and standard deviation of these data points. So how do I compute the variance and standard deviation? Firstly, the question is, how do I understand if these data points are extremely spread out or not? I don't know right now if these data points are extremely spread out or not. So what I will have to do is I would need to...
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Evaluate, exactly, compute standard deviation or compute spread, the variance. How do I need to do that? So let's actually go back to the variance, the formula of variance. To compute variance, all that I need to do is I need to compute the summation of every data point to the mean and divided by the total number of data points that I have. And I of course need to square them as well. So let's first compute the mean. What is the mean of all these data points? By the way, mean is either represented as x bar or also represented as mu. Okay. So so do not get confused. In some of our other slides, you would see x bar, something represented by a bar or by mu. So don't get confused with that. It's one of the same. So firstly, what is your mean over here? So take the summation of this. Exactly. The mean is in this particular case 16. So 20, 30, 40. And then this is 30. So 70 divided by 70 by 5. So your mean is 16. I have a mean of 16. Brilliant. So now all that I'm going to do is xi minus x bar the whole square. So xi minus x bar whole square. So 10 minus 16 the whole square. So this is going to be 10 minus 16 the whole square. This is going to be 15 minus 16 the whole square. This is going to be 25 minus 16 the whole square. 20 minus 16 the whole square. And this is going to be 10 minus 16 the whole square. So this is going to be how much? 36. This is going to be 1. This is going to be, how much is this? This is 4 and 5. This is 9 square is 81. And then this is 16. And this is again 6 square is 36. Right? And then you sum up all of these, right? So once you square them, then you sum up all of these and take a mean. So when you sum all these values up, what's the summation of all of these values? Quickly, 36 plus 36 is 72. 72 plus 16 is 88. 89. 89 plus 81 is 170. Perfect. 170. And then, so your variance is going to be 170 divided by how many data points you have? 1, 2, 3, 4, 5. What is this going to become? Perfect, 34. That is my variance. Variance is 34. 34. Essentially, what it is trying to tell me is the average square distance of every data point from the mean is 34. But it doesn't mean anything to us. I mean, logically, it doesn't mean anything to us. I mean, it's hard for us to visualize what this number really is. But on the other hand, I could convert this into standard deviation. And standard deviation is basically a square root on top of my variance. So if I apply a square root of 34, what does that become? So square root of 34, which is approximately something around 5.8ish. Right, perfect, yeah. Right, so that's 5.8. Now what we're saying here is, on an average, every data point from the mean. So mind you, these are my data points. The mean is 16. So what we're saying, on an average, if you look at all the data points, they are 5.8 units away from the mean. If you look at every data point, on an average, they're 5.8 units away from the mean. That's all that we're trying to say here. Yeah, for a few data points, they're going to be closer. A few data points are going to be far away. But on an average, we will have a representation. So that is what we have over here right now. That is what variance and standard deviation are meant to tell us. Does this make sense, everyone? Firstly, are all of us okay until this particular? Intuitively, does all of this make sense? Okay, now let's try and see how we can implement the same. Implement the same using, or rather, apply the same using NumPy in Python, right? So there are some easy ways of computing your statistics. So let's say, for example, you have these numbers, right? So take this code at face value right now. I'm just trying to show you how some of this can be really implemented. Right, so let's say this is x. This is basically an array of values, right? So this is basically a NumPy array of values. Now I want to compute, let's say, the mean. That is basically the mean, right? And then let's say I want to compute the standard deviation. That is the standard deviation of my data points at this particular point. So this is the mean, this is standard deviation, and the square of this is nothing but your variance. So you basically perform the square of this. That's your variance. This is standard deviation. Okay. So mean and standard deviation, this is how you compute. You could also sort of compute the median of x. That is nothing but your median. So that is the centermost data point. So if you actually look at it, that's the centermost data point. You can also compute the maximum and minimum np.max. right? And then you can also do np.min, and then you could also compute, actually, just give me a second, x comma. This will give me my 25th percentile, and this will give me my 75th percentile, which is nothing but your, this is your Q1, and this is your Q3, right? 75th percentile. And then I can compute my IQR, and then I could simply do, that is nothing but my, or actually the other way around. That is my IQR. Okay. That is essentially my interquartile range. Similarly, this is min and max, and I could simply do this for my range. This is how you compute your range, right? So yeah, mean, median, range, interquartile range, and standard deviation. I could basically, and if you want to sort of get your variance, I don't know if there's a function. Yeah, there you go. That's the variance. So that's it. So these are some methods to compute your min, max, standard deviation, and so on and so forth. Now, in addition to this, what you could also do is you could also generate some random data, and then you could also do that. But yeah, we'll come to that once we actually learn how to work with NumPy. We'll probably implement some of those in more detail when we get there, because we're just doing some preliminary statistics right now. I'm not getting into the actual details. But yeah, long story short, I think the point is we could sort of learn this or apply all of these easily when we actually learn NumPy. Okay, let's now go back. So yeah, mode, mean, variance, range, percentiles. We spoke about percentiles as well. We spoke about quartiles, and then we spoke about interquartile range, standard deviation, and variance. We spoke about this. So standard deviation is used to express the magnitude by which the members of a group differ from the mean value of that particular group. So it's the same with variance as well. It's just that standard deviation is nothing but the square root of your variance. So again, as I said, mean is often referred to as using the mu, Greek alphabet mu as well. Yeah, so these are some metrics that we've spoken about until this particular point, some ways to understand some of these data points, some ways to sort of aggregate some data points. Now, let's talk about something interesting, right? Let's actually talk about a measure called as, or a metric, a statistical metric called as correlation. Now, what do you mean by correlation? So correlation is firstly a measure of, let's take for example, you have two variables, two random variables, meaning x1 and x2. You could call it x and y, or x1 and x2, doesn't matter. So maybe for the purposes of this example, let's call it x and y. Now, what we would do is, now these two could be random variables, meaning one of them could, let's say, be age, and the other could be, let's say, height. And logically speaking, if you take, for example, if you plot age and height, right, what you would see is, as age increases, you would expect the height to also sort of increase until a certain point at least. Right? If you look at, for example, kids between the age of 0 to 18, right? As age increases, you will see the height also sort of going up. So you would sort of see some kind of a positive relationship, meaning as age increases, your height is also sort of increasing. So you would sort of expect some kind of a positive relationship, right? Such kind of a relationship, meaning as x increases, y is also increasing, or if as x increases, if y, let's say, decreases, there is some form of dependence between these two variables, right? In this case, as x increases, y is also increasing. On the other hand, if you look at, let's say, as age and let's say number of working hours, or number of active hours, let's say, that your body can clock, active hours. Let's say you're capturing this from the ages of 40 to, let's say, 60. What happens as age increases here? As age increases, the number of active hours of people tends to decrease, right? Because you become less physically active, you become slightly more tired more frequently. So the number of physical active hours tends to sort of decrease. So here you might see, I'm not saying you will see, I'm just saying you might see. And I'm not concluding that this is what will happen. It doesn't necessarily have to happen this way. I mean, it could happen completely differently as well. I'm just kind of calling out an example here. So here you might see again, even in this case, right, this is X and this is Y, there is some form for dependence. So what correlation tries to do is, given that these are two random variables, correlation tries to measure how dependent or how related are these two random variables. So is X and Y dependent on each other or not? Is or not actually dependent? Is X and Y in some form? Does X impact Y or not? Or vice versa? Does Y impact X or not? Is what we are trying to sort of understand. So correlation sort of tries to give you, how impactful is X on Y. So we use correlation between dependent and independent variables. Here there is no dependent or independent variable. They are two variables, two random variables, and we're just trying to measure some form of dependence between these two. We don't know what causes what. I don't know if age causes the active hours, or because you're becoming lesser and lesser active, that is what causes your age to go down. If any two variables, if they are related, you typically have two or three types of correlation. Once you have a positive correlation, and then you have a negative correlation, and then at times you may have no correlation. So simple examples are, so you have x1 and you have x2. If as x increases, if x1 increases, if x2 also increases, then this is a strong positive correlation. And on the other hand, you have x1 and you have x2. As x1 increases, if x2 reduces, then this is an example of a strong negative correlation. At times, x1 and x2 are probably going to be completely independent, meaning it's hard for probably us to identify any kind of a pattern within this particular data. That sort of is an indication of no dependence whatsoever. Like, does my, the number of tube lights in my house has an impact on let's say the rent of the house, or the number of lights in the house, does it have an impact on the rent of the house? Probably don't know. Maybe you might see in certain localities, maybe it might impact, and in certain localities it might not impact. And that is probably an indication of something like this. You might not actually see an impact. Or the number of teachers in a school, does it have an impact on the quality of education being delivered by that school, or the marks that are being. So if, for example, if you capture two variables, right, number of teachers in a school, and then you capture, let's say, the maximum score that a student gets in a board examination, or in an SAT for that matter, in that particular school. So you capture all that information from various schools. You probably might not see a relationship there, because just because you have more teachers doesn't make your school any better, right? It just makes your school bigger. It doesn't make your school better. So you might actually not see a dependence there. So that's these are some kind of examples that you can think of. So right now, what we're trying to get at is we're trying to sort of compare these two. So how do you compare them? So the way we are going to compare them is using a simple math again. Correlation as a number is something that varies between -1 to +1. -1 meaning a strong. So if you look at the scale, right, -1, +1, and 0. So anything around the 0 mark is a no correlation, meaning you don't have a strong correlation. Anything that is closer to 1 or -1 have a strong correlation. In this side, it is a strong negative correlation. This side, it is a strong positive correlation. This thing is still a positive. There's still correlation, but it's the direction is what matters. So strong negative correlation, an example is how this is how it will look like. A strong positive correlation, this is how it would look like. As x increases, y also increases. And this is an example for no correlation. So there is purely no data. You don't really have any correlation whatsoever. So the point is, how do you compute this? The way you're going to compute this is, so correlation can simply be computed as, so if you take two variables, x1 and x2. So x1 minus x bar, or rather, assuming let's say you have two variables, x and y, summation of xi minus x bar into yi minus y bar, the whole divided by standard deviation of x and standard deviation of y. So I is equal to 1 to n. That is what this is. Basically, this is how you compute your correlation. So you take your x variable and your y variable, and you compute your, for every data point, x. So x1, my pen is misbehaving, or 2, 3, and so on. y1, y2, y3, and so on. Right? Let's say you captured this data. This is, let's say, number of teachers in the school and maximum marks or maximum score in an SAT. Let's say that somebody has acquired in that examination. So what you're computing is you take the average of all these data points, which is x bar, and you take the average, this is nothing but y bar, and then for every data point, compute the average distance. So basically, what you're trying to see is if this value is positive and this is also positive, then you would typically see a very, very large value. This value will typically go up. If this is positive and this is negative, again, magnitude wise, this might actually go down, right? So the numerator in itself will clearly tell you if both are increasing, then you will have a very positive value, high positive value. Both are reducing, then if one is increasing and the other is reducing, you'll have a strong negative value. If unfortunately one increases and the other decreases, right? One increases and the other all decreases, or let's say the difference is not impactful, then you'll unfortunately see that these values probably will become a very, very small value, minuscule value. Yeah. So that is where you will typically get a negative. That is as far as what correlation is. In your slides, you would see basically the formula for correlation in this form. Do not get confused. It's basically the same thing, because if you actually look at this, right? So if you sort of expand this out, right? If you sort of expand the mean, right? So because here, if you see the metrics are just in x and y. So if you sort of expand this out, so like for example, this would simply become summation of x minus summation of x by n into yi minus summation of y bar summation of yi by n, the whole thing divided by, if you expand x, sigma x and sigma y, then the whole, and you solve for this equation, it looks like this. It basically turns out to be like this. So honestly, I find this too complicated and too convoluted. I just like to visualize this, using this simple form. I think it's basically like your correlation formula or your variance formula only. So if you look at variance, right? Variance is summation of xi minus x bar whole square. Instead of the square, you put y minus y bar. And in the case of variance, you would simply put an n. Instead of n, put sigma x and sigma y. That's it. That's what this correlation formula is. So yeah, I find this a slightly more simpler representation. Whatever works for you, but more often than not, you actually don't need to use the formula, because you will end up using code. So and with code, all of these will be predetermined, so you don't need to really do much. One very, very important point that I'd like to drive is correlation does not mean causation, right? You have to clearly understand this. Doesn't always mean causation. It may in certain cases mean causation, but just because two variables are correlated doesn't necessarily mean one is causing the other. It could also be because there is maybe the other way around. Maybe the causation is in the other direction, or maybe it's just a spurious correlation, meaning you just actually cannot explain why it's happening. Right? So at times you may actually see that the number of deaths in a particular country and the number of diamonds that were mined in that country are actually correlated. In a specific country, the number of deaths and that have been recorded in that particular country in a certain year across different regions, and the number of diamonds that were mined from that particular country in an African country in that particular year. These two are correlated as two columns, as two features, they are correlated. So just because these two columns are correlated doesn't necessarily mean that one is causing the other or the other way around. We call such correlations as spurious correlations, and you would see a ton of these spurious correlations within your data many times. We don't know why that happens. That probably happens just because of the way the data is. No, it's not curious, it is spurious. S-P-U-R-I-O-U-S. Spurious. Spurious means there is no real reason. It's a weird correlation. Spurious means something that is very mysterious, right? And such things happen within the data, and you have to be very careful. And just because two columns are correlated, you cannot assume that one causes the other. That's the point that I'm trying to drive. So be very, very cautious about this. Be very, very careful about this. So whenever you're reporting numbers, please be very careful, right? So yeah, this is basically, and you'll bump into many such other examples. Like for example, in a particular company, what we see is just because more coupons are offered, you see sales are going up. Like more coupons are being lent out, meaning more sales are happening. This might actually seem very true, but it actually doesn't necessarily explain the other. So I'll also explain this using some other examples, right? I mean, when we get there, there are a ton of such examples wherein we talk about spurious correlations. Let me actually draw your attention to a website which actually has some of these spurious correlations sort of captured, and take a look at this website. It's actually pretty cool. I show this in almost all my classes, but yeah, take a look at this. So US spending on science, space and technology, STEM is what they call it, or also even like space and technology additionally as well, and suicides by hanging, strangulation and suffocation. So take a look at this. As the number of years increased, as on your x-axis, you basically have the year, and what you see over here is basically in your black, you see the hanging, suicides, right? And then you have US spending on science. Now, if you just look at these two variables, right, year over year, it might actually seem that these two are dependent, because as one is increasing, the other is also increasing over time, especially as well in this particular case, right? As one increases, the other increases. But how do you even explain something like this? Numerically, they are correlated, because if you look at the numeric correlation between these two variables, the numeric correlation is 99.99, a positive correlation, right? So from a correlation standpoint, there is a very, very strong positive correlation. Because these two things are not correlated even. There's a clear correlation, right? Numerically, they are correlated, because as one increases, the others also increase. There's a strong positive correlation. The correlation wise, there is a positive correlation, but there is no reason why these two would actually be correlated, because it's very difficult for us to explain these two things, which is exactly the reason why these are called spurious correlations, because there's no way that you would explain any of this. That's me, you're absolutely right? So it will be correlated if only people who are working on these in tech. I mean, not necessarily. I just got access to two data sets, and in these two data sets, I have the number of people, the amount that was spent on science, and I have in another column, I have a number of people who have committed suicide, and I just wanted to look at if these two are correlated, and they actually turned out to be that they're correlated. Because they're correlated numerically doesn't mean that as one increases, the other will also increase. Well, hell no. I mean, that's because there is no dependence over here. I cannot explain any causation. They are correlated, but there is no causation over here. So please understand that subtlety, and don't try to explain it using some weird logic that because you're spending more, that is why people are more stressed, and hence people are committing more suicides. No, don't explain. What you don't know is what you don't know. So what we don't have here is what we don't have here. So that is exactly the reason that I'm calling out. Correlation does not mean causation. So do not assume that these two fields in some form or the other will explain each other. Don't make those assumptions. Look at this. Another very, very funny number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in. Why would that even happen? I mean, it's just coincidence that Nicolas Cage has appeared in certain number of movies each year, and number of people who actually drowned is a 66 correlation, a 0.66 correlation. Quite a strong correlation, mind you. But it's just that it just happened. How has Nicolas Cage got to do with the number of people drowning in a pool? There's no, I mean, it just so sounds so absurd, but that's true. That's it exactly. It's just coincidence. And even if there's a reason, per capita cheese consumption is correlated to number of people who died by becoming tangled in their bed sheets. I didn't know firstly that people could die because they could tangle themselves in bed sheets. See, again, that's the point. The divorce rate in Maine. Maine is basically a state in the US, and again, per capita consumption of margarine. How are these two correlated? God knows how these two are correlated. The correlation is 0.99. So how do you explain that? There's no way to explain. It is what it is. Age of Miss America and murders by steam, hot vapors. So yeah, total revenue generated by arcades. Arcades are your gaming arcades, and computer science doctorates awarded in the US. A lot of these are driven by very, very weird reasons. So the point is you need to be very careful when you talk about correlations. Correlation doesn't mean causation. Just because two columns are correlated doesn't mean one causes the other. So you have to be, when you call out that one causes the other, you have to be extremely sure that there is a causal effect between the two, and not just because one causes the other. We need to be really careful when we call something like that. Okay, so correlation is just a numeric representation, numeric dependence. That means nothing. That doesn't establish any causality. So please just get up. I just want that fact to sit deep in your head somewhere. Now let's talk about, let's actually go back one step, right? And let's actually talk a little bit about distributions. Forget about this term for a second, normal distribution. Forget about this terminology of normality. We'll talk about what normal distributions are later. But I think first things first, what we'll try and understand is a regular distribution. So whenever we talk about a distribution, take for example, this is age, right? And let's say your distribution looks like that, right? So now what does this mean? So in this particular case, you have lesser number of people with, let's say this is age 0 to, let's say, 60, right? And you have, what this diagram basically tells us is, what it's trying to basically tell us is there are very few people with, in this particular age group, and there are maximum number of people in this particular age group, and again, there are lesser number of people in that particular age group. So that's sort of what we are trying to convey using this kind of chart. So, and another way of visualizing this is using your bars. The bars were essentially converted into a curve-like structure. So this is basically what it is. Now, what we can understand is this, right? So first and foremost, this particular point is simply nothing but, or the central behavior. When you talk about your mean, median, or whatever, they sort of are typically going to be present in this, somewhere around in this particular region, because you seem to have a nicely well distributed data set. So your centrality is somewhere going to be focused in this region. So when you compute your average or mean or median, they're going to be somewhere in this particular space, somewhere here. They're going to be somewhere in between these two places. So what it means to us is there are different types of distributions that one would typically bump into. One is a distribution that looks like this. One is another distribution that sort of, many times your distribution might also have some amount of skewness in it. Like for example, if you look at the ages of people in
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. Val. B. Raise. C. Try. D. With. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Let's say in Japan, right? So you would see a distribution that sort of looks like this. And if you take, for example, the people in India or in Pakistan, right, they would sort of have a distribution, or even China for that matter, they would sort of have a distribution that looks like this. So wherein we have a larger tail onto the right side in India, and we will have a larger tail to the left side. So this is like a tail. So you will have a larger tail to the left side here in India, in let's say somewhere like a Japan. Now, why is this the case? That's because of the way ages are distributed in those respective nations. It's just the way the data is sort of distributed. What does that translate into? So take, for example, let's start, for example, here, right? This kind of a distribution, firstly, these type of distributions are called as skewed distributions. Both these, this one as well as the one that you see over here. These are skewed distributions. Why? Why is there a skewness? Because your data is either concentrated onto one side, right? There is a level of skewness because in this particular case, your data is sort of pulled towards this side. And in this case, there's a certain amount of data that's sort of pulled towards or concentrated onto one direction. This kind of data can be, this kind of distribution is referred to as a left skewed distribution, or it is also referred to as a positively skewed distribution. There's a positive skewness. And on the other side, this is called as the right skewed distribution.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Or a left-tailed distribution, because the tail is on the left side, you can call it left skewed or a right-tailed distribution. Different terminologies. So I don't think the terminologies matter. I think what we really need to understand here is, if you take, for example, this particular left skewed distribution, what is happening here? What's exactly happening is we are adding, take for example, a class with people of ages, there are, let's say, 3 people, 10, 20, and 30 in a classroom. You have 3 people with ages 10, 20, and 30 respectively. Now, let's say suddenly, let's say you have another guy of age 50 added to this particular group. Let's say majority of people in this particular group are, let's say, within this age group. Now, suddenly you have one person, or let's say 2 or 3 people of very high age actually joining this particular class. What would happen because of them? While majority of the data is going to be in this place, because of these 1 or 2 people, you will have a small tail onto this side. And because you have a small tail onto that side, because more people, there are just few representative points onto the other side, you'll have a small tail onto this side. And because you have a small tail onto this side, what will happen to the mean is your previous mean, which was at 20, because of the addition of one guy, your mean will shift towards this direction. Your mean, which was previously at around 20, because I've added one guy with age 50, your mean will shift significantly from which it was previously at the center to towards the right side, towards the larger point. The point that I'm trying to drive is mean as a metric is actually very, very sensitive to extreme values, especially larger values, even like say towards the left side as well. Whenever you have certain extreme values being added, mean is extremely sensitive. Mean gets extremely impacted because of these extreme values. So the moment I add this extreme point, your mean was at 20 earlier, but because now I've added this new guy, look what happens. Your mean now suddenly shifts from 20 to almost around 30, almost towards 30 is what your mean will automatically shift to. So there will be a huge shift from 20 towards 30. And that's a little unfortunate. That's also because you've just added one data point on the other side, and because of that, your mean just shifted, right? So that's one of the big challenges with mean. So I'll give you a simple example of this and make it really clear for us to understand. So take, for example, a representation like this. Let's say your data looks like that, right? 10, 10, 20, 20, 20, 20, and 30 and 30. Now, let's say to this particular group, you've added a new person. Like, so when you actually look at how this distribution is, this distribution has 2 10s, 4 20s, and then 2 30s. Basically, your distribution sort of looks like that. This is how your distribution is currently. Now, because now let's say I had one person of age, let's say 500 to this, not age, let's say this is something else, let's say salary, right? This is salary of all employees in a particular company, and this is salary, let's say, of the CEO. I add, let's say, another person with the value 500. One person. I had, 4, 5, 6, 7, 8, totally 8 people in my data set earlier, and all of them were in this particular page. I had one guy with such a large value. And what happens? With such an extreme value that because of that one guy, my complete mean just gets pulled towards this new person. Earlier, my mean was 20 because you do your computation, it would typically be 20 because it's sort of fairly distributed. The mean earlier before was 20. New mean is going to be what? 160 plus 500, which is 660. 160 plus 660 divided by 9. So almost this shifts almost towards 70, or approximately towards 70 or 74. Yeah, 73. So this new mean almost becomes, just because of this one simple guy, one additional guy, your mean has just shifted towards the right side. So now what happens is your distribution, which was originally looking like this, right? Because of this one extreme data point, your mean, which was previously here, has now shifted towards that side. So the point is, mean as a metric is extremely sensitive. But tell me something. I've added one additional guy with value 500 over here. Your mean has shifted from, let's say, 20 to 70. But what happened to the median? With this distribution, the median will shift, but the value hasn't changed. Even if the value changes, because median is always the centermost data point, I've added an extreme point to the right extreme or to the left extreme. Even if the median shifts, the median will shift very, very little because it will shift within these center data points. So though your median has shifted, though your mean has shifted, your median has not shifted as much. So your mean was previously 20 and is currently 73, and your median previously was 20 and currently is also 20. So what does this tell us? In the presence of external values, in the presence of extreme values, between mean and median, which is a more stable metric? In the presence of extreme data points between mean and median, which is the most exactly, median is a much more stable metric. Now, coming back to this particular distribution. So let's take a simple example. So now, if you had a nicely distributed data set, right? A well-distributed data set without any skewness. Let's say there was no skewness. What will happen to the mean and median? How will mean and median be related? Mean and median. What will be the relation between these two? They will approximately be equal. So somewhere like this, right? So your mean and median will be somewhere in the center. Wonderful. But if, let's say, you take a distribution which is slightly skewed, take for example a distribution which is slightly skewed, like in this case, this distribution is slightly skewed. So what will happen to the mean and median? Because you have some extreme data points over here, your mean, which was previously here, will shift. So your mean will probably be somewhere over here. So let's say this is age. Your mean was probably somewhere in this range. But because of the extreme values, your mean will shift towards the right. But what will happen to the median? Your median will still probably stay there. So in this case, mean and median, how will they be related? Mean will typically be greater than median. Exactly, that is what's going to happen. So whenever you see a distribution where the mean is greater than median, you can immediately visualize a behavior like this. You could sort of think of a distribution that basically looks like this. You could expect a behavior like this, right? On the other hand, if you take this behavior, what will happen? Now the extreme points are added to the left. So the extreme points are added here. So the tail is towards the left side. So what will happen? It's the reverse. So your median is going to be greater than mean here. So because your median will still stay there, your mean will shift towards this particular side. That is exactly what's going to happen. So these two distributions are referred to as skewed distributions. And skewness means that your mean and median are typically going to get impacted because of that. That's learning number one, something that is extremely important about distribution. Now, let's go one step ahead. Now, if you take a regular distribution, right? So again, what people have observed is that, again, this is basically where statistics meets philosophy. But long story short, I think the point is that many metrics or many phenomenon in the world, the way they naturally occur, like if you take the mean, or let's say if you take the ages, or let's say the heights, or let's say even the blood pressures of people in a certain group, or let's say you take any of these metrics that typically exist in the world naturally, they all tend to follow a certain kind of a distribution, and that distribution is often referred to as a normal distribution. What is a normal distribution? Normal distribution is a distribution that follows a certain kind of a behavior. What is the certain kind of behavior? First things first, there are certain characteristics that a normal distribution exhibits. It's also like a regular distribution only. It is basically a collection of numbers, but there are certain kind of specific characteristics that a normal distribution exhibits. Like what? So here you go. First things first, a normal distribution is a symmetric distribution, right? Which has firstly a symmetric distribution. What do you mean by a symmetric distribution? So this is also a symmetric distribution. So if you draw the symmetric over mean, so if you draw the distribution and if you basically draw the mean, distribution on the left side and the right side are actually the same, right? So this is basically a symmetric distribution. But symmetric distribution basically also means that your mean is approximately the same as median, right? So your mean and median approximately have the same kind of behavior, or mean and median are approximately equal. So that's the first and the foremost characteristic of a normal distribution. What next? There is another very, very important behavior that normal distribution exhibit. Normal distributions exhibit, an empirical behavior, which is an empirical rule. Like they exhibit something called as a 68, 95, and a 99.7 principle, or a rule, let's say, call it a rule. What does this mean? What this means, you'll actually have to put your thinking hats on a little. It's a very popular behavior. So what this represents is, so if you take any distribution, right? If a normal distribution has a certain kind of a behavior where if you take the mean, let's take this is the mean, and if you actually you compute the mean, and let's say you compute the standard deviation, mean and sigma, and this is mean and this is standard deviation, not sigma square, sigma, standard deviation. So if you compute mean plus, this is mean, so now you compute mean minus 1 standard deviation and mean plus 1 standard deviation. What is a standard deviation? The average distance of the data points from the mean, right? So if you compute the mean plus 1 standard deviation and mean minus 1 standard deviation, so you compute the mean, let's say the mean is 20 and the standard deviation is 5. So basically 20 minus 5 and 20 plus 5. So between 15, so mean is 20, between 15 and let's say 25. The volume of data between mean plus 1 standard deviation and minus 1 standard deviation should ideally be 68%, basically 34% on this side and 34% on this side, right? Then you take mean minus 2 standard deviations and the mean plus 2 standard deviations. Now when you compute mean plus 2 standard deviations and mean minus 2 standard deviations, so the data in this red section should typically be 95% exactly. So this section, right? This section should typically have 95% of the data, right? From here all the way until, not there actually, all the way until here, right? So between mean plus 2 standard deviations and mean minus 2 standard deviations, you would typically have 95% of your data. And then the last, right? The last is mean minus 3 sigma and mean plus 3 sigma is basically the 3 standard deviations on either side, right? So mean minus 3 standard deviations and mean plus 3 standard deviations. It says 99.7% of the data should ideally be between mean minus 3 standard deviations and mean plus 3 standard deviations. right? Minus 3 sigma plus 3 sigma. How many sigmas are we talking about? 6 sigma. So 6 sigma, the concept of 6 sigma comes from, something like this basically. So the point is that a normal distribution is a distribution that sort of has this sort of a behavior. So within one standard deviation from the mean, right? So between mean plus 1 sigma and mean minus 1 sigma, actually the other way around. So mean minus 1 sigma and mean plus 1 sigma, you will have 68% of the data. Mean minus 2 sigma and mean plus 2 sigma, you'll have 95% of the data. And last but not the least, mean minus 3 sigma and mean plus 3 sigma, you're going to have 99.7% of the data. Then what about anything beyond the 3 sigmas on either side? What about they? They are nothing but your outliers. So meaning all this data on either side, right? What about any data point beyond the 3 sigmas on either side? The 0.3% of your data, they are referred to as statistical outliers, right? They are outlierish behavior. They sort of have a very outlier sort of behavior. And this is what is called as a curve that, or a distribution that showcases this type of a behavior, is what is referred to as a bell curve or a normal distribution. It looks like a bell, right? This curve sort of looks like a church bell. Look at it. Okay? So it's sort of referred to as a bell curve, or also called as a normal distribution. So a distribution that is asymmetric, first things first, symmetric distribution where the mean and median are approximately the same, and a distribution where you have data represented within 3 standard deviations on either side, or 99.7% of the data represented between mean 3 standard deviations of mean on either side is, and that follows like the 68, 19, 95 and 99.7 principle, is what is referred to as a normal distribution. The reason why we call it normal distribution is because this many such phenomenon within our planet, and it's sort of like the magic number. There are a lot of natural phenomenon that follows some of these behaviors around the bell curve. It actually captures some really cool natural phenomenon that has all of these captured very well. I just want to share that. So if you ever roll a dice, right? Take for example, you have 2 dice that you roll, right? And if you look at the probabilities that would get generated, this is, let's say, when you have 2 dice, the lowest possible number is 2 and the maximum number of possibilities is 12. And if you look at the likelihood of a particular outcome coming through, see if the chance that you would get a 2 is just 1 out of 36, because there are total 36 different possibilities when you roll 2 dice. And the chance that you will get a 2 is just only 1 chance, because you need to get 1 on either side. That's only the case where you will get a 2. And the chance that you'll get a 12 is you need to get 6 on either dice, on both the dice. That's when you'll get a 12. So the point is that if you look at the likelihood of you getting a 2 or getting a 12, it's actually quite rare. On the other hand, getting a 7 or 8, so which is why if you observe, a lot of games are basically designed around the 6, 7, 8 sort of a strategy. They also always expect you to sort of get lower numbers or very high numbers for you to do well. So and it is statistically insignificant. So this sort of follows the bell curve. Again, flipping a coin or IQ graph, right? Typically, if you look at the IQ, most people, if you look at the IQ, they sort of fall in this particular category. There are a few people who have lower IQ scores and a few people who have higher IQ scores. These are the Einsteins of the world. These are, I don't know, people like me, but this is like people like, most people on the planet are typically here. Stock markets as well, they sort of follow a certain kind of shoe sizes are actually quite a good example, right? So shoe sizes, t-shirt sizes are very good examples of this. So many people, right? So very few people will have these small shoe sizes. Take for example, female shoe sizes of adults. Most people are going to have their shoe size around the 6 to 7 mark, somewhere here, and very few people on the either side. Birth weights. So if you look at the weight of adolescents and infants, the moment they're born, neonatals basically, they all have a certain kind of behavior. This is in grams. They have a certain kind of a normal distribution over here. So again, this is a very, and yeah, student report cards or marks that students basically get in an examination. They all follow normal distribution. They all follow this kind of a distribution. So the term normal distribution has basically come because these are the distributions that you will typically see in most natural phenomena, and it is why it's called as normal distribution. And there's a lot of research that has gone into normal distribution, and we'll learn about that in more detail in our subsequent sessions. But that basically is what is normal distribution. Okay. So the empirical rule, this is basically the empirical rule, 68, 95, and 99.7 rule. That is what this is all about. Yeah, so now let's talk about something called as z-scores. I'll actually give you a problem statement and then maybe it'll make it easier for us to actually solve it. So the heights of fifth grade boys in the United States approximately is approximately normally distributed. So let's take, for example, all the heights of fifth grade kids in the United States is normally distributed. Let's assume that they are probably draw a better normal distribution, but okay. And with a mean height of, so we're saying the mean is 143.5 and a standard deviation of 7.1. So the mean is 143.5 and the standard deviation is, this is centimeters by the way, is 7.1 centimeters. This is the sigma. Now, what is the probability that a randomly chosen fifth grade boy would be taller than 157.7 centimeters? So let's say there's a guy who's randomly picked. I'd want to identify what is the likelihood that this guy would be taller than 157.7. So 157.7 is somewhere here, right? This is 143, right? This is 143. What I'd like to identify that if I randomly pick a person, what is the chance that this person is going to be actually taller than 157.1 centimeters, right? Now, 143.5 centimeters is nothing but your mean. So what I'm essentially asking is what is the likelihood that somebody would have their height greater than the mean? What I'm essentially asking is what proportion of data will be basically greater than this? As simple as that, 50%. That's it. When I say the mean is 143.5 and we're saying it's normally distributed. So when I say it's normally distributed, that means the curve is like a nice bell curve. And when I say it's a bell curve, the curve is symmetric on either side. When I say symmetric, what do we mean? It is what it basically means. I have equal amount of data on either side of my mean. That is what you mean by a bell curve, right? This is 50% and this is 50%. That is what we mean. Now I asked, what is the probability that a particular data point is going to be greater than the mean? 50%. Anything on this side is going to be 50% likely, right? As simple as that. Does that make sense, everyone? There is a normal distribution, and with this normal distribution, the mean is 143.5, standard deviation is 7.1, and they're asking us what is the probability that your mean is going to be, or a randomly chosen guy's height is going to be greater than 157.7 centimeters. Can we compute how many standard deviations is this away from the mean? We know it is greater because it's on this side. What is this exactly? So how do I compute that? So 157.7 minus how many, what is the mean? The mean is 143.5 divided by standard deviation is 7.1, because I can see what this difference is and divided by the mean, divided by the standard deviation, isn't it? This is like 14.2 divided by 7.1, which is nothing but 2 standard deviations. So what is greater than 2 sigma? What is the likelihood that somebody would be taller than mean plus 2 sigma? That is 2.2, 2.15%. That's it. Simple as that. 2.15 or 2.25%. That's your answer. Now, this 2 sigma that we just computed is nothing but a z-score. So simply put, a z-score is nothing but number of standard deviations that a point is away from mean. So if I have 157.7, I need to identify how far away is this from mean, how many standard deviations is it away from mean. So the way we're going to compute is z-score is going to x minus the value minus the mean divided by sigma. So what is the value? The value is 157.7 minus the mean is 143.1, or I think 143. That's what that is, 143 point. And the whole thing divided by What does this give me? This will first tell me the difference between the point and the mean. This is going to first tell me the difference between the point and mean. So it will simply tell me the distance. But how many standard deviations is it away from the mean? How will I know that? How many standard deviations is it exactly? How would I know that? Divided by the standard deviation, right? I know the difference. This difference is 14.2. But how many standard deviations is this? How would I know it? Divided by the standard deviation, you will know it. This is 2. Okay, this is 2 standard deviations. The z-score is nothing but 2. Does that make sense, everyone? So if I want to compute standard deviation, or if I want to, let's say, compute these percentages, the best way to do it is firstly compute what the z-score is. Z-scores would simply tell me how many standard deviations is a particular point away from the mean. It's not the value, it is the number of standard deviations that it would be away from the mean. Because the thing about normal distributions is we have a reference with regards to the standard deviations. Because we have this curve, right? I mean, we have this curve. So what I would always try to do is I'd always want to identify, given a particular data point, how many standard deviations is it away from the mean? If it is just 1 standard deviation away from the mean, or 1.5 standard deviations away from the mean, or 2 or 3 or whatever, we'd always want to compute that. So that will help me identify, okay, is it like at 1, is it like at 2 or 3? And based on that, I can compute my percentages. So similarly here as well, and I'm just putting a more formal structure to it. I'm calling it as a z-score, right? And z-score will simply give me how many standard deviations to a particular point away from the mean. And using that, the way I'm going to compute it is compute the difference between the point and the mean and divide it by a standard deviation. That would simply give me the how far away the particular point. Okay, that is exactly what a z-score is.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
So when we talk about data extraction, what is it exactly that we're going to discuss? The first thing you need to understand about data extraction, as the name suggests, is basically that it is a technique which will go on to, pull data from places such as websites, social media sites, or whatever it is in general. And this information can be used by you and can be leveraged in such a way that, you can go on to probably use this information effectively. See, for example, there are multiple things when you can consider some simple entity such as a tweet on Twitter. So people go on to, post things of whatever comes to their mind on Twitter, right? So there's something called a sentiment analysis which has been coping up and which has been upcoming for the last couple of years, basically. So when you think about Twitter sentiment analysis, you can understand if people are happy about something, if they're sad about something, or if their viewpoint is even neutral. So who knew a couple of years ago that your post on Twitter will actually help people analyze something? So why would somebody even want to analyze something on Twitter, you might be asking? Well, basically at the end of the day, you're converting this raw data, which basically is the Twitter responses in our case, into information. So you might be wondering if your brand is performing very well, if your product is selling well, and how happy are people when they're dealing with your businesses, and much more. So I just gave you an example which came on the top of my head right now, but again, I can give you a million examples of how and where data extraction is being used very effectively. And in fact, make sure you stick till the end, because in our demo we're going to be considering something from the present situation right now, and it's going to be really nice to understand the real-time use and help of data extraction techniques as well. So again, coming back to the definition, basically what we're talking about is a technique, is a methodology which will help us gather the data, and it does it in an automatic way so that we don't have to manually gather the data. So this part where it's automated is all about what we're going to discuss, because at the end of the day, if it's going to be a manual task, you wouldn't need a procedure to do that. You wouldn't need a technique to do that, right? So all you have to do is see something from a website and start typing it out probably. So this automation part plays a huge role. So when we're talking about extracting data from websites, when we're talking about extracting data from anywhere, you need to understand that there's two types of data present in today's world. One is structured data and the second one is unstructured data. If we're talking about structured data, structured data will have something to adhere to. It'll have some rule, it'll have some policies, or it'll have basically a guiding principle behind it. For example, when you look at the data present in databases, it'll either be of the same type, or it'll adhere to all the rules of the data that is present in the database probably. Or when you're thinking even of structured data in general, it can be just a very good, very well organized calendar or a timetable basically in your calendars. So something from that simple entity to all the way till for example images, it can be audio, it can be video data, and it can be anything text as well. So when you're mixing up all of these concepts, your data becomes unstructured. There is no one set governing policy over the data which says, yes, I can use this one rule to basically assess and control all the data. So this is a very important difference that one must understand when you're working with structured data and when you're analyzing unstructured data as well. So I hope I was clear in helping you understand structured and unstructured data. Anyway, on that note, guys, let's keep the session very interactive. Make sure you head to the comment section and leave us all your comments. So we have our team members waiting for you guys to hit the comment section, and they'll help you out as soon as they can. So make sure you hit that comment section and leave us with any questions you have, suggestions, or anything you'd want from this session as well. So let's keep it interactive. Head to the comment section. Alright guys, so on that note, we need to check one more important thing is how one can go on to do this. There is one term when it comes to data extraction, especially from websites. The term is scraping. See, so when you go on to check any website for that matter, right? So all these websites, they contain images, they contain text of some sort, or they might contain if it's a website such as Amazon, for example, or any e-commerce site, you'll have products, you'll have pricing, you'll have situations where the product is deliverable to one place and not the other, for example, as well. So when you're working with all of these concepts, there are a million ways and there are a ton of data that you can actually gather from these websites. So basically what one can do is, if you guys are into sports, you will know that the players for the teams are usually auctioned off when you're working with Premier Leagues. So when you're talking about all these Premier Leagues, what usually happens is each player has a value and they're bid on and they're won. So you can actually go on to websites to find what the price of the player was when they were bought into the league, and you can create a very nice looking Excel sheet, and you can organize to see what player was worth what, and eventually at the end of the Premier League they usually put out tables and charts with the number of goals. So you can create this very fun project where you're trying to find out the return on investment as well. So again, just another example here. But then if to give you another example, you can go on to e-commerce sites like Amazon, again Flipkart, there are many other places there. You can find out all the prices that each of these guys are offering for the same product, and you can find out who is providing it for cheaper. Is it Amazon, is it Flipkart, or any other case for that example as well. So all this information is gathered in the websites, and we use a term called as scraping to basically pull all of these information out. Scraping literally means hunting for the information that you need, filtering for the information you need, and basically bringing it on to your machine, or basically to bringing it on to your native base, where you'll be converting it into files that you can use. So CSV is a very structured form of storing the data. For example, let's go back to the e-commerce example we went. So you can have name of the product, the vendor 1 and vendor 2, for example Flipkart or Amazon, and you can get the price of both of them, and you can compare and check who's giving it for a better price and whatnot. So this forms the basic outlay of how one can go on to perform data extraction. Data is present in the websites, we'll be cleaning the data and pulling whatever data we require, and after that we'll see if there is any processing to be needed, and if processing is needed, it is done, and at the end of it we will save all of these files in a format which is basically structured and which we can use further down the line. Alright, so on that note, you need to understand why we need to perform data extraction. Guys, again, if you know why data extraction is important in today's world, head to the comments and let me know. So coming to the answer to why one should scrape data, here is a very good first example for you. When you go on to the top job hunting sites, be it Naukri.com, be it Indeed, or be it LinkedIn Jobs or whatever, so in this situation, when you have to find out about all of the top jobs that are present around the world, well, it would be really nice to have all these jobs that you're looking for at one particular website, right? So consider the situation where, let's say, you want to become an artificial intelligence developer. Artificial intelligence is on the rise in today's world, as you might know it, and you're looking for a job. So in this situation, you would want to check out all the jobs that are available in your vicinity, in your area, or in your area of interest as well, right? So if all of these job listings were probably put in a very structured Excel sheet, or if these were put in a very nice place all in one. No. So if all of these were put in a very nice single place where you can look at, analyze, assess, and basically apply, that would be really nice as well, right? So basically, to perform this, you will require data scraping, and this is actually a very good example of projects in case you guys want to consider doing your own projects with respect to job listings as well. Find a keyword, find a career, and basically scrape data of various websites where you can create your own list of these jobs available as well. Anyway, coming to the second reason of why one must scrape data, think about social media analysis. See, all of us pretty much use a minimum of, well, let's say 4 out of 6 social media that you see on your screen, right? Everything from Facebook, Instagram, Snapchat, Twitter, WhatsApp, LinkedIn, and more. If you are a business person, or if you are a marketing enthusiast, programmer, or whatever it is, if you're looking to scale your brand, if you're looking to, sell your products more and ensure how your outreach is, as we discussed previously, you will need social media. At the end of the day, social media is something, we all go back to on our couch at the end of the day to scroll through to see what's happening in our friend's life. Well, let me tell you, it is way more than that, because with the help of social media, brands are being established, they are taking off. So in this competitive world, it is enough that, people have to start using these tools to help market their brand, to make sure that, more customers are coming in and whatnot. This is one aspect of it. The second aspect of it is that, you need to understand what your customers feel about your product. You need to understand what your customers, have the opinion about your product, because, 3 people might be really happy about your product while 10 people might be showing disinterest or saying that your product might be bad. Knowing this can help you with your brand and much more, right? So scraping data with respect to social media is very important, not only in terms of businesses, but in general as well. Now, coming to the third reason of why one must perform data scraping is understanding market value comparison. So this is exactly what I was talking about when I gave you the Amazon Flipkart example. So it's not just e-commerce websites, it can be the comparison between any two products. If you're looking for a product, you can bet on it that there are multiple vendors for the same product. So, it is very, very rare cases, it is 0.001% of cases where there is only one vendor for your product across the entire world. Well, let's talk about the other 99.99 cases, right? So there, you have more than one provider who's giving you the product that you're looking for. So in that case, you need to understand, you need to perform analysis to see who's giving it for a lower price, because if it works out for you at a lower price, you're at an advantage, right? So probably this wouldn't matter if you have a low investment of say $1, $10, or maybe $100, depending on how much you can digest. But then if you're looking to purchase something in the thousands of dollars range, probably in the millions of dollars range, then of course this is going to add a lot of value, because again your savings are in the thousands as well, right? So scraping data for market value comparison is very important. And of course, research and development. When you're understanding that, let's say you can provide scientists, physiologists, and everyone in the field of science more data where, that can be helped for them to perform analysis and give them a look at the data that pretty much that they've never taken a look at from the angle that you can provide with the use of web scraping, is something which is very vital as well, because, they can be working with a lot of data, but then once you step in with web scraping, once you give them data, it might provide them the angle, it might provide them some clarity, it might provide them basically what I'm trying to tell you is that, it will provide them with a view that they have not thought of looking at as well. And of course, all of these data can be further put into use by making use of artificial intelligence, machine learning, or whatever it is. But then to get to that, you need to give them the data, right? And this is exactly what and why it's important to scrape data for the world of research and development as well. So on that note, you might have a question saying, is it legal to start pulling data from everywhere around the world? Well, to answer this is a bit tricky, I'll tell you why. The answer is yes and no. So you can legally extract some information from websites, and you can of course, illegally do it as well. So to understand how you can, abide by the laws to make sure what's legal to be pulled, what's not legal to be used, the websites will actually tell the users about it. So, the websites will tell the users saying, hey, this is legal to do, this is not legal to do. So how, you might be asking, how are the websites telling the users? Because you don't see it anywhere on the websites, right? So every website has a file called as robots.txt, and this robots.txt will basically tell all these crawler robots, all these spider robots, which basically go on to pick the actual data from the websites, saying, hey, you are allowed to do this, you are not allowed for this particular information. So when these websites say, and these robots basically, when they they can have all the access they want to everything that they're allowed to. And once if someone with a very bad intent tries to pick up information from a website which is not allowed to access, then their intentions are not good, and they might be doing something with your data which they're not supposed to. So let access is basically amazon.com/robots dot text, and as soon as you hit enter, it will take you to their file where they will tell you what you can allow and what you cannot allow. So you can see disallow/wish list. So all of these pages which start with disallow means that you cannot legally access all of these as well. You can see allow as well. So basically allow will tell you, hey, you know what, you can have legal access to all of these as well. So this is exactly what I was talking about. But then to give you more clarity on what this means, it's not just Amazon. You can visit any of the websites and just type in /robots.txt, and this will give you an understanding to see if you can actually scrape their data or not legally. So in fact, to add value to my point, here is what it would look like. So basically, as I mentioned, any website will have this file, and this is what it basically means. As soon as we saw user agent start disallow, if disallow is not followed by anything, it basically means that the user or the crawler robot or the spider robot basically, which is going to pick the information for us, it has full access to their website. And if we have a disallow and if we put in a slash there, it means that it will block all access, and no data can be scraped from there. But then you can actually prevent access to particular folders, you can prevent access to particular files and much more. So you can see disallow /folder/. This means that this one particular folder has blocked access, and you cannot access this when you're pretty much trying to scrape the data. And then there is disallow /file.html, and this ensures that there is one particular file which is basically blocked for access by all of these crawler robots as well. So this is very important for you to understand even before you begin scraping data off the internet. And now the question comes, Python for data extraction, what makes Python the tool that one must go on to use? The first thing when we talk about Python is ease of use. So Python has been this amazing language, and personally been a fan of it, been using it for multiple years now, seeing it take over the top position when you're comparing it with Java or whatever it is. Python is amazingly easy to work with. So there are multiple reasons. One, it's very readable for people who have never used Python before. Two, the syntax is again very easily understandable, and you do not need a lot of training when you're working with Python. Of course, structured training is very important to understand the core values of Python and how you can go on to use it effectively as well. But the point here is that there is no semicolons, there is no complex syntax, and everything at the end of the day is a breeze when you're working with Python. So of course, I think many people in the comment section can agree to this point on how easy Python is to use when you compare it with all the other programming languages out there. So point number 2 is something very important. Point number 2 is what makes Python what it is. It is the number of libraries that Python supports. See, for example, in the world of data extraction, we will perform computations, we will perform data storage methodologies, and we will go on to visualize this data at the end as well. So for numerical computations, you have libraries such as Panda and Numpy, which will perform any computation on the data that you have extracted. And for data visualization, we have tools such as Seaborn, Matplotlib, and much more, which will basically help you even after you have achieved the results of data extraction as well. And these are just 4 libraries among hundreds and hundreds of libraries that are present, which are being used around the world as we speak. basically which makes what Python what it is. Because at the end of the day, with getting access to so many open source libraries, you're part of a huge community and you're using tools which will make your job a lot easier. Be it data extraction, be it machine learning, be it neural networks, whatever it is, with respect to Python, it just makes it easier. And this adds value to my last point as well. So coming to the next point, it's small code. You might be wondering what I say by small code. With respect to Python, as I mentioned, the syntax is not complex. One more thing is that the syntax is not long. For small amounts of code, you can basically get big results. In Java, if you have to compare to, pretty much go on to print hello world, you have to write 4 or 5 lines of code.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Those are complex syntaxes as well. So for a beginner who has never seen programming before, that will be overwhelming. With Python, it is pretty simple. It says print, open your braces, put your message inside and hit enter and your results are printed. So I just gave you a simple example again. Even with respect to data extraction, you need to understand that, there is a small amount of code, but at the end of the day, the results that you get for typing the small amount of code is huge. And this, in my opinion, is one of the most important aspect of using Python for data extraction as well. So coming to the next point, it's again a very nice point here, is that it's the community. When you're working with data extraction or any other concepts with respect to Python, we have an amazing open source community where everyone is friendly, everyone wants to help each other out and pretty much develop products, establish brands, whatever it is. Everyone is very friendly, and this entire community is filled with people who are enthusiasts, who are willing to help each other out, and who are basically willing to see that all of them grow together in the world of programming as well. So this is why personally I love Python too. And again, I am sure our viewers can agree to this point as well. So you might be wondering, what are the Python libraries available for data extraction? Well, there are many libraries, but then here are the top 3 most used libraries. The first thing is Beautiful Soup. So Beautiful Soup is again another open source library which basically parses your HTML and XML documents and makes sure that you can extract all of these information very easily. So you might be wondering what parse basically means. So parsing is an operation of performing syntactical analysis where you're trying to make sense of symbols, where you're trying to make sense of the text which is given, the strings or whatever it is, and then bringing you that information. So Beautiful Soup again is a very widely used Python library for data extraction alongside a Selenium. So Selenium is basically used for automating your browser activities as well. So when you perform web testing, when you perform activities where you're pulling the data continuously, you have to go on to test to see if your data is being pulled right, to analyze your data, to automate this process of verification and validation. So Selenium is used right after Beautiful Soup for that. And then there's AnyTree. AnyTree is basically helping you create a tree data structure which is used for data extraction. So a tree data structure at the end of the day will basically make sure that your data is organized and it can be pulled in a structured way, and this will help in further analysis, in further storage and much more. See, there are many other tools you can use as well. There is requests which you can use, there is LXML, and there is many other tools as well, but these 3 are mostly the top use tree, because one, we are talking about converting your data into something useful. The second one, we are basically pulling the data for any tree to use, and after that we'll be using Selenium to basically test and automate the process as well. So as I just mentioned, there are multiple libraries which one can go on to use for data extraction. And this quickly brings us to the demo where we'll actually get to see this hands-on. And just before we jump to the demo, we need to understand the problem statement at hand. So what is the problem that we are facing in today's world with respect to data? In my opinion, it is data requirement, because see, when you're basically trying to solve a problem which needs a lot of data, First thing, you need all these data to work with, right? So here is where data extraction is a king. When you're working with data extraction, you can have the ability to basically provide all the data that's required, for example, for the creation of data sets. And these created data sets will help solve the world's problems, right? So let me give you an example. When you're working with artificial intelligence, machine learning, neural networks, or whatever it is, more the data you provide, there is a good chance that your machines and your neural nets or whatever it is, it will learn better and understand quicker. So it's not only about artificial intelligence that, more the data, better the learning. But when you talk about any other situation as well, if you were given price comparison of products from just two places, would it make more sense? Or if I could give you a price comparison of 10 places, the 10 places would basically be a better, point of reference for a business decision, right? Exactly my point here. So more the data, better the learning, better business decisions, better key performance indications, and much more. So let's consider one of the things that's happening right now. So for example, we have the COVID-19 outbreak across the world right now, and it is something very grievous as well. When you look at the numbers on your screen, basically we had total infections of 2.4 million and 170,000 deaths at the time of the creation of this video as well. And pretty much this number is going on and on every single second, and it's very scary to see. And at this point of time, again, I would like to enforce everyone to take all the precautions, that is, stay safe, stay in quarantine, and we can fight COVID-19. So basically, humanity has fought multiple viruses across the history of the last 100 years and more. So pretty much, this is an easy task at hand if everyone does their job, and let the doctors work their thing. And let's see, as IT people, let's see, as the people who are computer science enthusiasts, IT field enthusiasts, let's see how we can help them out better to achieve this, right? And that's exactly my point here as well. So again, when we're talking about how important is a data set to solve a problem, let's see if we can bring machine learning together and medicine together. So we have a comprehensive video on the channel which will guide you on how machine learning is basically used to fight against COVID-19 as well. So make sure you check that out after this video. So coming back to how important the data set is, the first thing your data set can help in this particular case is it'll tell you where you can trace the outbreak from, where it originated, how it started out, where is it spreading, how quick it's spreading, and much more. Diagnosing patients is something very important. Again, it will help you tell what patients have been diagnosed at what time for what particular disease or whatever conditions they have as well. Disinfecting areas, you can find out by making use of machine learning models saying where the contamination is highest and help disinfect those areas as well. And then when you're looking at finding a cure, probably this is the most important thing. This is the most widely asked thing right now, to see if computers can help fight against a virus. And of course, computers are doing everything they can. There are experts out there who are bringing together the world of IT and medicine just for this cause. So if computers can help scientists find a cure for this particular disease, it would help. And again, if we take a quick backtrack, of course, medicine in all of its glory will be the one finding the cure. But then the field of computer science, if it can speed up something in the field of medicine, that is what we're basically achieving. To speed up something, we need more data again, and more data is obtained by making use of data extraction, right? So you see where we're going here. So just before we dive into the world of showing you how data extraction works with respect to the demo, here is a sample fact about how machine learning came into picture. So basically, Blue Dot is an artificial intelligence platform which basically tracks all the infectious diseases that happen, right? So this actually found out that there was a lot of pneumonia cases happening around one particular market in Wuhan, China. And just 9 days later, after the Blue Dot platform found out this unusual rise in cases, World Health Organization stated that they have found a new virus out there, and there are a lot of people hospitalized with respect to pneumonia as well. And this was at the end of 2019, and now we know that in the April of 2020, we know where we are. We know the 100,000 deaths which has happened, 2.4 million cases and whatnot, right? So this again was one of the places where IT helped, and it could only do this where if it had all the data from around this market in Wuhan or whatever it is, right? So again, they and the people at Blue Dot basically again made use of data extraction to get all of these data and create artificial intelligence models around it, and then put out a conclusion saying there are a lot of pneumonia cases here as well. So this is exactly one case. So I picked up a medical case study to show you guys, because again, I believe that artificial intelligence, I believe that you can make use of machines with medicine together to help speed up today's world of medical research and whatever it is in general as well. So I'm a huge fan of that, and I hope you guys could see the connection as well. So coming to where you can pick up the data, in our case, let's say COVID-19 dataset creation, you can have data picked up from the satellites, you can have data picked up from the news, you can see who all flew around the world at what time to trace and understand where there could be an outbreak by taking all the data from the flights across the world, and of course all the health organizations, hospitals, your local governing bodies which is taking care of the local areas as well. So there are multiple places where you can find a lot of data. For example, every day you can check out, there are news about where hotspots are, where there is a lockdown, where there is a complete shutdown, where people cannot step out of the houses as well. So when you look at the data, there is plethora of data, there is a lot of data. To go on to use this effectively, you need to create that structured aspect that I spoke about in the starting of the session, right? So just onto that, here is what the solution would look like to perform data extraction on a data set such as the COVID-19 data set by making use of web scraping, by making use of data extraction. So as mentioned, we'll be making use of Python in this particular cases, and we'll create a data set for various reasons, and all the various reasons we just discussed in the problem statement, right? So quickly coming on to how it works, it is pretty simple. So it's about 10 or 11 steps, and it's really simple to follow as well. So follow along with me. The first step to perform data extraction is to make sure you set up everything you require in your Python runtime environment. For example, here we're making use of Google Colab. Basically, it's a free Jupyter notebook where you can run Python commands online, and everything is stored on the Google's ecosystem, and they provide you storage and computation power as well. But then I'm aware that most of you might not be using Google Colab. So if you're using your local machine, if you're using any other environment to run your Python code, just make sure you install a couple of libraries before we begin with. As discussed, Beautiful Soup 4 again is a very important library for web scraping. We have requests as well. So requests will basically help you pull and parse data from the HTML sources we'll be looking at as well. So in this case, we'll be pulling data from a very famous website called as worldometers.info. So these guys have been putting out very structured information when it comes to how the outbreak is being handled and all. So to do that, to pull the data, to pull all the HTML data and to analyze and understand it, we require requests. And we have a library called as LXML as well. So LXML again will help you parse your XML data and pretty much make it understandable and make it usable for further down the line. So you can execute these code statements that are in the comments in case if you're using any other environment as well. So coming to Google Colab, basically Google Colab has all of it covered for us. So all I need to do is run it, and basically it is imported because it's already installed in the backend. Step 1 is very simple. Step 1 is to get your runtime set up. Now step 2. So what we're trying to do in step number 2 is we're creating a beautiful soup object. All you're trying to do is making use of the website's HTML, and here is where the LXML parser will come into the picture, and we're trying to create this object where we're getting all of the source from the website URL as well. So you can see the URL is given on your screen. It's worldometers.info/coronavirus. So this is where all our data is, and all we're trying to use is make use of the get operation in HTML request to basically pull all of this data. So by running step 2, you would have created an object. Step number 3 is something simple as well. So what we're trying to do here is we're trying to create tables with all of the data surrounding COVID-19, right? So when we're trying to do this, you need to understand that there are multiple tables which will be available in that Worldometers website. So we need to perform some analysis in the backend to find out what table ID is given. So we can pull all these data from that particular table as well. So here the ID attribute which I found out to be the table there was given as main table countries today. And running this will basically create a table. It will find us the ID attribute, and at the end of the day, so our beautiful soup basically understands that this is the table, this is the ID where I can pull all the data from. So step number 4 is basically where we go on to extract the headings that we require for the data chart that we're going to use. So to do all of this, you might be wondering, is the data already clean where we can directly grab the data and start using it? Well, the answer is no, because with respect to most of the cases, the data that we see and use will basically be some sort of it'll have some sort of an anomaly, or it'll have some sort of characters that we would not want to use, or let's say it's of no use to us. In that case, what we basically do is we replace all of these unwanted characters with something else, and we make sure that we actually go on to keep the data as clean as possible for further use as well. So you can, for example, see every new line character here is basically replaced by a blank space when you're working with heading, and you're working with a non-breaking space as well. So /xa0 deals with non-breaking spaces, and again we are replacing those non-breaking spaces with an empty string as well. So all we're trying to do in step number 4 is clean the data and get all of the headings so that we can have headings for our columns and use it further as well. And after step number 4, step number 5 is to find the data for all the continents across the globe. So for example, in the data that we have analyzed, there is the data continent aspect where data can be pulled for each continent. So in our case, we want the data across the world, right? So we're not looking for data only from say Africa, Australia, only from Asia or whatever it is. We want the details from across the world. So all we're trying to do is to ensure that we find the table where all of the rows which do not have a data continent attribute. So if it does not have a data continent attribute, it means that we're trying to pick up the data from all the countries and not just any one continent, right? So we want the data from around the world. To do that, we need to recursively go on to check if these particular aspects have the country's attribute, and to find out if these attributes are present or not. If they're not performed, then we're going to pick that, because that indicates we're looking at all the countries and not just one single continent as well. So basically, after performing analysis and after setting our scope to the data across the world and not just one particular country, we need to remove the first row. So basically, all we're trying to do is we're removing the first row in the heading, because we already extracted it before, right? So if you remember, we already pulled out headings in step number 4. So basically, performing this operation will remove the first row, since we already have it to repeat it again. Now, coming to step 7. Step 7 is basically the creation of the result list. So all we're trying to do here is we're creating a list and we're calling it result. And this list will basically hold all of the data temporarily until it can be written into a CSV file, which will be our final output. So let me repeat. We're going to create a list called as result, and this result will be a temporary point of storage for all of our data, which will later be written in a CSV file, and this CSV file will be our output. So basically, running step number 7 will create the list. So basically, at the end of the day, we need to append all of these headings. We need to add all of these headings to the list, right? So result.append of headings will do just that. It will make sure to add all of the heading to the results that we actually want. And step number 9 until step number 8, we have cleaned the data. We have pulled all the data that's required. We have created headings, and we have basically removed all the unwanted spaces. We have created a result list, and we have added the headings there. Now step number 9 deals with adding all the data with respect to the each rows and each columns as well. So until now, we already picked up the headings. With respect to step number 9, we are going to basically find all the data that needs to be extracted, to find all the data, to scrape all the data, and we're going to add it to a list called as row. After we are adding it to a list called row, we're going to check if it's present already. If not present, we're going to keep adding it. And after that, we're going to have to add all the data that we found in the row list into the result list, right? So basically, the row list will have all the data that we have pulled through all the different rows in the data. So it will not have headings at this point of time. To make sure that the data is collaborating with the headings, which is basically present in our result list, we actually append the rows to the results as well. So performing step number 9 will add all the data of each particular row and eventually append all of this to our result list. And then step number 10 is the most simple step probably, because here is where we are preparing for storage. So whenever you create any file in Python, basically be it CSV file or anything, we need to create a file and we need to open it as well. So basically using the open command, we're creating a file called as data.csv and we are opening it in the write mode, and we're starting it with a blank line as well. So when you go on to run this particular command at step number 10, it will create an empty file. It will create a file called as data.csv. It will open that file for further working, because we need to write the data, right? So the file writer needs to have access to all of these files that it can write to. So that is why we open it prior to writing. And again, the second part of step 10 is to actually write these files that we actually obtained it into this file called as CSV file, and then we can actually push all of this results. Step number 10 was basically preparing it for storage, creating it, opening it, and make sure that there is a file writer which can write. Step number 11 is where we actually write the result into the CSV file. So writer.write rows of result will write the actual results to our CSV file. This will be pushing all of the data that we have from our result list into the CSV file, and at the end of it, it is always a good practice to close the file basically, which will make sure that the data is saved. So you might be wondering now, okay, step number 11 is done, we've written everything to the CSV file and it is stored, but where is the file? Well, in your case, you will have the file present in the Python interpreters folders. In our case, it will be created basically in the Google ecosystems files, and let me double click on the data.csv that we just created here. And as you can see on the right hand side of your screen, you can choose to pick up how many ever details that you have to show on your screen as well. So here as well, all the countries, all the total cases, the new cases from yesterday, the total number of deaths in that country, new deaths, total recovered, and much more. So this detail we've picked up from the worldometer side. What are the active cases? How many of these active cases where people are serious? What are the total cases for 1 million of population, deaths per 1 million population, and much more. So worldometers is a comprehensive website, and this at the end of the day, this will create a very nice data set, and this data set at the end of the day can be used to perform analysis. Again, to find out how that is done, make sure to check out our machine learning video, which is basically performed using a data set similar to this as well. So this creation of data set, not just in the case of COVID-19, it can be anything across the world. Once you have structured data and once you've created structured files like this, you can understand that you can leverage this and make full use out of it down the ladder. It's basically performing analysis. It can be working with deep learning, working with machine learning, whatever it is. Step 1 is very much essential in all of these fields of processes, and step 1 is creation of data. And we have created a structured pipeline to access our data as well. And this again, in my opinion, is one of the most important use cases or uses of data extraction when you're working with Python as well.
How to import a dataset using pandas, and how to analyze various attributes of the data. How we can import a dataset using pandas. So for importing the dataset, the very first thing that you will be doing is importing the pandas library. So I'm importing pandas as PD. So next we are going to read the dataset and store it in a data frame. So I'm defining a data frame named cars, and inside this I'm passing the path of my CSV file, which is empty cars2.csv. At this point, you can specify the path to your CSV file. Okay. And finally, we are printing it. Let's see the output. So this is my entire data. So let's move ahead and see what are the various analysis we are going to perform on it. So first is type cars. So this type car is used to check the type or check the data type of the car. So it's a data frame, right? So as a part of output, we got pandas.co.frame.dataframe. Okay. So the type of cars is, it's a data frame. Next is cars.head. Well, this is used to view only the first 5 records of your data frame, which in our case is this. Okay. Next is, if you want to view first 10 records from your dataset, you can pass the attribute over here as 10. And so as an output, you'll get first 10 dataset from the data frame. Okay. Next is, what if you want to view last 5 records, then you can use the parameter dataframe.tail, which in our case is cars.tail. Okay. So this will give you the last 5 record of your data frame. Okay. Similarly, if you want last 10 records from your dataset, you can specify a value over here. So dataframe.tail, inside this I pass 10. So this is giving me last 10 records from my dataset of cars. Okay. Next is cars.shape. Now if you want to view the total number of rows and columns in your data frame, for that you have dataframe.shape. So cars.shape gave me the output as 32 and 13, which means I have 32 rows and 13 columns in our dataset. Now if I want to concise the summary of the column of my data frame, for that I have dataframe.info. And inside info, I'm passing null underscore counts equal true. So what it is exactly giving me, it is giving how many non-null values are up here. So as you can see in QSEC, we have 29 null values. So from here you can say that we have 3 null values in our column QSEC. Okay. This is the data type of each column. The first serial number is of integer data type, next is object, MPG is object, cylinder is integer, and so on. So in total we have 4 columns which consist of floating data type, 7 columns which consist of integer data, and 2 columns which consist of data of object data type. Okay, and the total memory usage is 3.3 plus KB. Fine, let's move ahead. Now if I want to calculate the mean of my data frame, I can just write dataframe.mean, which in our case is cars.mean. So as a part of output, it gave me the mean of each column. Okay. Next, if I want to calculate the median, similarly dataframe.median, cars.median, it gave me the median of each individual column. Okay. Next is standard deviation. Well, for standard deviation, we have dataframe.std. So if you see the output over here, you are getting the standard deviation of each column. Fine. Next, similarly, you can calculate the maximum value of each attribute by using dataframe.max. So we have cars.max, for which we are getting maximum of each attribute. So in serial number, we have 35 unnamed maximum value. This MPG, it's 33.9 and so on. Okay. Similarly, you can calculate the minimum value for each attributes using dataframe.min, and you'll get minimum value for all these different attributes. Fine. Next is dataframe.count. So if you want to count the total number of non-null record in each column, then you can use dataframe.count. So which in our case is cars.count. So here as our output, we are getting how many non-null values are in each column. So here in QSEC, you can see that we have 29, which suggests that we have only 29 non-null records and there are 3 null values in it. Okay. Next is the dataframe.describe function. Well, it is used to print the descriptive statistic summary. If you don't want to calculate each of the feature individually, you can just write dataframe.describe, and this will give you the output of count, mean, standard deviation, minimum, maximum, 25 percentile, 50 percentile, and 75 percentile values of all the different columns. Okay, so these were the various attributes you can use it for analyzing your data set. Okay.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So without delaying any further, let's see what exactly is data cleaning. So data cleaning or data cleansing is a process of detecting, correcting, or removing corrupt or inaccurate records from a dataset, table, or any database. It also refers to identifying complete, incorrect, inaccurate, or irrelevant parts of our data and then replacing it or modifying it. This is what a data cleaning is. So let's see how we can clean our data. So the first thing that we can do to clean our data is we can rename the column. Okay, so in our data set, we had a column as unnamed, right? So instead of using the column name as unnamed, we can replace it by name of the model, which represents the exact name of the column, as the column contained different model of the car, right? So here what we are doing, we are renaming the column unnamed to model. So as you can see here, as an output, we got model up here. Okay. So this is the very first thing that you can do while cleaning your data. You can rename the attributes. Next is, what if you have some null values in your data? So for treating null values, what you can do, you can fill the null values with the mean of the column. And this is how we do it. So cards.qsec. So as we have analyzed in our previous session that QSEC had 29 non-null records, right? So which it meant that it had 3 null values in it. So we replaced all those null values with the mean of the QSEC column. So what we did, we took the mean of the entire 29 and whatever value we got for the mean, we replaced all the null values with that particular value. Okay. So replacing the missing data with the mean value will help analyzing the data in a better way. Okay. So this is how we can replace the null values with the mean of the column. Next is drop the unwanted column. So here we can drop all those unwanted columns which do not add any value in analyzing the data. For example, we had serial number previously, right? But the serial number was not adding any value to our analysis part. So for the further processing of the data, we can avoid or we can drop the column of serial number. Okay. So how we can drop any column? So for dropping any column, what we have to do is data frame.drop, and inside that we have to mention the name of our column, just like this. Cars equal cars.drop, and inside this columns equal we are mentioning the name of the column as serial number, and it got dropped. So as you can see here in the output, we don't have the column as we used to have it previously. So here a serial number column is dropped. Well, next is finding correlation matrix. Well, this correlation matrix will help you to find how a variable is correlated to other variable. So if the value of correlation is high, so that means the two variables are highly correlated to each other. That is, changing one variable by a factor of x changes other variable by a factor of y. Okay. So here as an output, we got a correlation matrix, right? So from here you can see that cylinder to cylinder, it's highly correlated. That is one, obviously. Cylinder to displacement, it is 0.9. So it means that cylinder equals 0.9 times of displacement.
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. Val. B. Raise. C. Try. D. With. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
So it's like if you increase cylinder by 1 unit, your displacement would increase by 0.9 unit. Okay. So similarly for DRAT, you can see that cylinder equal minus of 0.69 times of DRAT, which means if cylinder increases by 1 unit, it means the value of DRAT would decrease by 0.69 units. Okay. So if while finding a correlation matrix, you get a very small value of the correlation. For example, let's consider this. So here correlation between carburetor and DRAT is minus of 0.09. So it means they are very weakly related to each other. So it's like if the carburetor is increased by 1 unit, so it means that if the carburetor is increased by 1 unit, then DRAT would decrease by 0.9 unit, which is almost very less, right? So by finding correlation matrix, you can define the correlation between the variable, and from here you can decide which attribute to choose and what not to choose while working on the problem. Okay, fine. Let's move ahead. Next is changing the data type. Well, initially MPG was of data type string, right? Well, MPG had some float or numerical values into it, right? But with the string, we cannot manipulate it, or we cannot perform any calculation on the string data, right? So MPG has to be converted to float in order to perform some data manipulation on it. So here we are converting MPG from string to float. So how we can do that? So it's dataframe.mpg equal dataframe.mpg as type, and inside that we are mentioning the data type which we want to convert to, and here in this case is float. Well, now if you want to see the change, you have to see cars.info null underscore counts equal true. So from here you can see that my MPG has been changed to floating data type, right? And even for the QSEC attribute, we have replaced all the null values from its mean, right? So here it's giving me 32 null values. That is, now it is not having any null values in it. Okay, let's move ahead. So again we are finding the correlation. This time the MPG part is included as it has become of a floating type. Remember, while calculating the correlation between two attributes, both the attributes should be numerical in nature. No correlation can be found between attributes of string data type. Okay, if you compare it with our previous correlation, you can see that there was no MPG value, right? As initially the data type of MPG was string, right? Now since we have changed the data type of MPG to float over here, so next while finding the correlation, we are getting MPG value. Okay, now Python is treating it as a numerical attribute and it is using it to find the correlation. Okay, so this was all about how you can clean your dataset. Okay, so in this session you will learn about how to perform indexing on the dataset, how to set a value for a column, how to manipulate the data using lambda function, how to sort a column, and finally you will see how to filter your records. So without delaying any further, let's start with our first topic, manipulating dataset indexing by position. Well, what if you want to view a single column? So how will you do that? Well, Panda gives you a functionality of iloc function in which you can specify the parameters to view a single column. So for example, I want to view HP column only. So my HP column belongs to 4th row, right? So I mentioned the iloc colon, which means row. So entire row, comma, 4th column. Okay. So what it will give me? The 4th column of the data set, which is nothing but the HP column. Okay. Let's move ahead. Next is, what if I want to view first 5 record of the HP column? So in it, I'll mention this is the number of row. So iloc row starting from 0 till 5. Okay. Actually 0 till 4, just before 5. And the column 4th. So it will give me the first 5 result from the column HP. Okay. Next is, what if I want to view all the rows and all the columns? So all you have to do is iloc colon comma colon. Okay. First colon means all the rows, second column means all the column. So it will give you the entire data set. Next is, let's see I want to see all the column from HP to cow and see all the record from index number 6. So how will I do that? So for that I have row start from 6 till the end and column start from 4th till the end. So 4th column till the end and row from 6th column till the end. Okay, let's move ahead. So now we want to look at all the rows from the first column. So again, so here inside iloc I have mentioned colon. So this represents the row. So we need all the rows. So for representing all the rows we have colon. Okay, and the next parameter is the column number. So our column number is 1. So as you can see in the output, we got all the rows from our first column. Okay, let's move ahead. Well, you can even view your record on the base of the name of the attribute. Okay, so for example, I want to see all the record of MPG column. So how will I do that? So instead of iloc, first of all, I'll be using loc over here. That is location. Okay, then inside that the row and the column. So colon includes all the rows and the column is MPG. So what it will give? It will give me all the rows from the MPG column. Okay. Next is display the record from index number 0 to index 6 from MPG column. So similarly, so loc starting from 0 until 6 and from which column? In MPG column. So it gave me records from index number 0 to index number 6 from MPG column. Okay. Next is to see first 7 record from MPG to QSEC column. So here what I'll do, so inside location what I have mentioned, the row. So starting from 0 till 6. So how many records are over there? It's like 0, 1, 2, 3, 4, 5 and 6. So in total there are 7 records. And from which column? So a column should start from MPG and it should end till QSEC. So from MPG to QSEC, I need 7 rows over here. Fine. So this was all about how you can play with index values while manipulating your data set. Okay. Next is setting the value. Well, if you want to set a specific value to the entire column, so you can do that easily using Panda. So here cars is our data frame. So what you are mentioning, cars of AM. So AM is what? It's a column name. Okay. So data frame of AM equal 1. So what it will do, so it will assign value 1 to the entire column of AM. So even in the output, you can see that AM has all the values of 1. Okay, let's move ahead. Next is applying function. Well, now what if I want to double my record? Well, for that, I can use lambda function over here such that x is x multiplied by 2. So whatever value would be there, it will just double it up. So cars of AM equal cars of AM dot apply f. Okay, f is our function, this. So as you can see in the output, we got all the double records in AM. Okay. Next is sorting the data. So what if I want to sort a column in ascending order? So for that I have data frame dot sort underscore values, and inside this I'll mention the name of the column. Okay. So for example here my data frame is cars and the name of my column is cylinder. So I'm mentioning cars dot sort underscore values by cylinder. So as you can see here, my cylinder column has been sorted in ascending order. Okay. Next is descending order. Well, all you have to do is add one more parameter over here, that is ascending equal false. And as you can see here, my column has been sorted in descending order. Okay. Next comes filtering the data. Well, what if I want to view the record which are having more than 6 cylinder? So how will I do that? So for that I have cars of cylinder is greater than 6. So So wherever the value of cylinder is greater than 6, so we are getting a true value over there, and apart from that, all are false. Okay. Now what if I want to filter my records and see only the data or only the model which are having more than 6 cylinders? So how will I do that? So for that, I'm storing the value into filter 1. And next I'll apply a filter to my entire data frame. So filtered new equal cars of filter 1. So what it will give me? It will give me all the true parameters from my data frame or from my filtered cars of cylinder greater than 6. Okay, so when you view the output of filtered new, you can see that we got all the values in which the value of cylinder is greater than 6. Okay. Next, what if I want to filter my record and check for the model which are having 6 cylinder and horsepower more than 300? So for that, we added this condition over here. That's it. That is, cars of cylinder is greater than 6 and cars of HP, that is horsepower, is greater than 300. So we are using AND operator over here. Okay. So this will give me a true result only if both the parameters are true. And again, same, we are filtering the data frame and displaying the filtered data. So as you can see here, we have only one model, Maserati Bora, which is having a horsepower of 35, which is greater than 300, and number of cylinders as 8, which is again greater than 6. So both our conditions are true. So there's our filtered data over here.
Yeah, so this is our first task, data manipulation. And to do this, let's go ahead and actually import all of our libraries. So I'll just type in import pandas as pd, and then I'll also load the numpy library. So I'll type in import numpy as np. I'd also need the matplotlib library. So I'll type in from matplotlib import pyplot as plt. So these are all of my required libraries. I'll just wait till these libraries are loaded. Right, this is done. Now I'll also go ahead and load up my customer churn data frame, and I'll store it into an object and name that object to be equal to customer churn. I'll just use pd.read underscore csv. And inside this, I will give in the name of the data frame, which is customer churn.csv. Right, so I have successfully loaded the file and I've stored it into a new object, and also I've named that new object to be equal to customer churn. Now I'll go ahead and have a glance at the head of this. So customer churn dot head, and this is the data set on which we'll be implementing all of the operations. So this is just the unique customer ID. This column gender tells us about the gender of the customer, whether the customer is male or female. The senior citizen column tells us whether the customer is a senior citizen or not. So if it's 0, then the customer is not a senior citizen. If it's 1, then the customer is a senior citizen. And then this tells us if the customer has a partner or not. This tells us if the customer has dependents or not. This is the tenure of the customer in months, right? So 1 month, 34 months, 2 months, and so on. This tells us if the customer has phone service or not. Does the customer have multiple lines? And this is the type of internet service used, and then whether the customer has online security, whether he has device protection, tech support, streaming TV, streaming movies, and so on. And then this column is for contract. So this just tells you the contract type of the customer. So the contract type of the customer could either be month to month, 1 year, or 2 year, and there's a type of billing, whether it is paperless or not. After this, we have the type of payment method. So the type of payment method could be these: electronic check, mail check, bank transfer, and so on. And then these are the monthly charges and total charges incurred by the customer. Right. So now let's start off with our data manipulation tasks. So this is our very simple task. We just have to extract some individual columns from the entire data frame. We'll have to extract the 5th column and store it in customer 5. So let me do that. I'll type in the name of the data frame first, which is customer churn, and I would use .ilog. I would need all of the rows, and I would need the 5th column since the indexing starts from 0. So 0, 1, 2, 3, and 4, right? So this would be my 5th column over here. And I will store this in, let's say, C underscore 5. And I'll have a glance at the head of this, C underscore 5 dot head. right? So we have successfully extracted the 5th column from this entire data frame, and this is the head of it. Similarly, we'd have to extract the 15th column and store it in customer 15, right? So if it's the 15th column, then the index number would be 14, because again, the indexing starts from 0, right? I'll store this in C underscore 15, and I'll also make this to be C underscore 15. I'll click on run, right? So this is the streaming movies column, and I get the same thing over here. This is column number 15, and I've extracted only this particular column from the entire data frame, right? This was basic extraction of columns from the entire data frame. After that, we'd have to do data extraction on the basis of a condition. We'll have to extract all the male senior citizens whose payment method is electronic check. Right. So there are 3 conditions over here. The first condition is the gender of the customer needs to be male. Second condition is senior citizen, the value of senior citizen needs to be equal to 1. And the third condition is the payment method needs to be equal to electronic check. So I'll give in all of these 3 conditions over here. I'll start off by giving the first condition, customer churn. I'll type in gender, and the gender needs to be equal to male, right? I'll cut this and paste this inside this. Of this, I'll use the AND operator and then given the second condition. So the second condition would go something like this, customer churn. After this, we'd have to set the senior citizen value. Right, so senior citizen, this needs to be equal to 1. And then I'll go ahead and give in the third condition. So over here, the third condition, this is for the payment method column. So the payment method needs to be equal to electronic check. All right. So I have all of my 3 conditions over here. I'll just paste a cell below. Now, what I'll do is I will copy all of these 3 conditions and I will paste them inside this, and I will store it into a new object and name that object to be crandom, right? Now I will print the head of this, crandom.head. So we see that this, so if you have a glance at this gender column, then you'll notice that all of the values are male. Similarly, if you have a glance at the senior citizen column, then all of these values are 1. Similarly, I'll go to the payment method column, then you'll notice that all of these values are electronic check. So I've given 3 conditions over here, and all of these conditions have been satisfied. So next up, we have to extract all of those customers whose tenure is greater than 70 or their monthly charges is greater than $100. Okay, again, we'll do the same thing. Customer churn, tenure needs to be greater than 70. I'll put this up inside this. Now, what you need to notice over here is we are using the OR operator. So it's either the first condition or the second condition, right? So if one of these conditions is true, then we'll get that particular record. So again, customer churn, and this time it's the monthly charges. So the monthly charges have to be greater than 100. These are the 2 conditions. So either the tenure of the customer needs to be greater than 70 months, or the monthly charges of the customer needs to be greater than $100. Again, I'll insert a cell below, and all I'll do is cut this and paste it inside this, right? And I will store this in, again, crandom. Now let me again print the head of this, crandom.head. Right, now I'll head on to the tenure column. Now you see that none of the tenure or none of the values of the tenure over here is greater than 70. But if I go to the monthly charges column, then you'll notice that the monthly charges are greater than 100. So it's either or. So one of these conditions has to be true. And in this case, we see that the second condition is true over here, right? So if either of the condition is true, then we'll get that entire record. After this, we'd have to extract all those customers whose contract is of 2 years, payment method is mail check, and value of churn is yes. Right. I'll again copy this, paste this over here. Let me delete this from this. Right, so we have these conditions over here. So we'll have to extract those customers where contract is of 2 years, payment method is mail check, and churn is equal to yes. So let me put in all of these conditions over here. First is contract, and this needs to be equal to 2 years. So let me just check, how is it? Contract is of 2 year, right? 2 space year. After that, it's the second condition, and over here the payment method needs to be equal to mailed check. Again, I'll put in the double equal to operator, and I'll give in the value, and the value is equal to mail check, and then I'll give in the final condition over here. So customer churn, and this time the churn needs to be equal to yes. Right, so I've given all of these three conditions and I've separated them using the AND operator. Again, I will store this in C underscore random. Let me print this out, C underscore random. So we see that there are just 3 records, or there are just 3 customers who satisfy all of these 3 conditions. So let me have a look at the contract of this, right? So contract is of 2 years for all of these 3 customers. Next is the payment method, and again payment method is mail check and churn. All of these values are yes, right? So out of all of those 7,000 rows, only there are 3 rows which satisfy these 3 conditions. Next, this is a question on random sampling. So we just have to extract 333 random records from the entire data frame. And to do this, we'll be using the sample function. So I'll type in customer churn and I'll use the sample method over here. And inside this, what I'll do is I'll give the value of the number of records which I want to sample. So I want 333 records. I'll store this in C underscore 333. Let me print out the head of it. Right, so now what I'll do is, so whenever I run this, every time I'll get a different sample of 333 records. I'll run this again, right? So if you have a glance over here, so all of these values would be changing, the customer IDs would be changing, the indexes would be changing, right? So keep a glance or have a glance at these row IDs indexes over here, right? So again, if you have a glance at this, the row IDs are changing. So this is random sampling. I'm randomly sampling 333 records from this entire data frame over here, and I'm doing that with the help of the sample method. Right, and then this is the final operation when it comes to data manipulation. So I'd have to get the count of different levels from the churn column. So if I want to get the count of the different levels present in a categorical column, I have the value counts method. So first I'll give in the name of the data frame, which is customer churn. After that, I'll give in the name of the column, which is churn, and then I'll just type in value counts, right? So this is it. So let me just wait till I get the result, right? So we see that no, so the number of customers who will not be churning out is 5,174, and the number of customers who will be churning out is 1,869. So you can do the same thing for other categorical columns as well. So let's say if I want to get the count values or the number of counts of different levels for, let's say, the contract column, I'll just change the name of the column over here. So I'll put it to be equal to contract, right? So there are 3,875 customers whose contract type is of month to month. There are 1,695 customers whose contract is of 2 years, and there are 1,473 customers whose contract is of 1 year. Right, so these were some basic data manipulation operations. After that, we'll head on to data visualization. All right. So here we'd have to create a simple bar plot for the internet service column, and yeah, we'd have to set the x-axis label to categories of internet service, y-axis label to count of categories, the title of the plot, distribution of internet service, and the color of the bars need to be equal to orange. Right. So I'll just type in plt.bar over here. Now I'll insert another cell over here. Now what I'll actually do is, so this basically takes in two parameters first. So the first parameter is the names of all of the bars, and the second parameter is the values for those bars, right? So the names of the bars would be coming from the internet service column. So internet service, and I actually want the value counts of this. Value counts, and from this I don't want the values, I just need the keys. And again, I'd have to convert them into a list. So I'll use list over here. Now I'll click on run. Let's see what do we get, right? So these are the three levels present in the internet service column. So from this internet service column, what I've done is I've used the value counts method. So this value counts method has two things, keys and values. Now I don't want the values as such, I just want the keys, and I'll take these keys and I'll convert these keys into a list, right? So this is the list of the names present in this internet service column. Now I'll cut this and paste it over here, and this would be my first parameter, and my second parameter would be all of the values. And if I want all of the values, I'll just remove the method keys from there, right? So this over here would give me all of the values present with respect to this internet service column, right? So fiber optic, or in other words, the number of customers whose internet service is fiber optic is 3,096. Number of customers whose internet service is DSL is 2,421, and number of customers who don't avail the internet service are 1,526. Right, now again, I'll cut this and I'll paste it over here. Now let me print this out. So this is my basic bar plot over here, right? So this is my bar plot. On the x-axis, I have the names representing these bars over here, right? So this bar is for all of the customers whose internet service is fiber optic. This is for those customers whose internet service is DSL, and this is for those customers who are not availing the internet service. And these are their counts over here, present on the y-axis. Now, I had to do some other things over here. I had to change the color of the bars. So the color of the bars was supposed to be set to orange. And for this, I have the color parameter, and I'll just set it to be equal to orange. I'll run this again, right? So we have successfully changed the color of these bars over here. Now I'd have to set the x-axis label and the y-axis label. So I'll just type in plt.xlabel, and the x label needs to be equal to categories of internet service. Let me type that down. Categories of internet service. After that, I would need to put in the label for the y-axis. So this would be plt.ylabel, and I'll just put it to be equal to count. And then finally, I'd have to give in the title. So plt.title, and I'll set the title over here. And the title needs to be equal to distribution of internet service. Let me type that out. Distribution of internet service. I'll click on run, right? So this is our final bar plot, which gives us the distribution of internet service, and the x-axis label is categories of internet service, and the y-axis label is count, right? So this is how we can create a simple bar plot, and all of this. So these are the basic steps behind before you go ahead and build all of your machine learning algorithms. So the pre-processing, the data pre-processing part is always the main part of your data science life cycle. So this is where you properly comprehend your data set. This is where you understand the structure of the data set. You understand the correlation between all of the columns, the correlation between the dependent variable and the independent variable. So by manipulating the data set and visualizing the structure of the data set, this is where you understand all of the patterns in the data set and you get insights from the data set. Right, so next up we have to build a histogram for the tenure column. So again, it'll be a similar operation, plt.hist, and I'd have to build a histogram for the tenure column. So it'll be customer churn tenure, and I'd have to set the number of bins to be equal to 30, and I'd have to set the color to be equal to green. So I'll just type in color equals green over here. So this is our histogram, and this gives us the distribution of the tenure of the customers. So so if you look at it closely, so this is basically the count over here, right? So there are around 800 odd customers whose tenure is not even 1 month. So they are churning out before they even complete 1 month. And again, there's a huge peak over here. So there are around more than 600 customers whose tenure is 70 months or more than 70 months. And then rest is pretty much the same, right? So the average customer, this is the normal range of the customer. So it's between 200 to 400. And the average tenure of the customer, you can say, would be somewhere between 20 months to 50 months or 60 months, right? And this is where you have the peak. So you have the peak at the starting and you have the peak at the ending. Again, let's go ahead and add the title. So it'll be just plt dot title over here, and the title of the plot needs to be equal to distribution of tenure. I'll do that. All right, so I have created this plot, and this is the title of the plot, which is distribution of tenure. So we've made a bar plot, we've made a histogram. Now you guys also need to understand the difference between a bar plot and a histogram. So a bar plot is normally used for all of the categorical columns. So whenever you want to understand the distribution of categorical columns, that is when you'll go with a bar plot. And when you want to understand the distribution of a continuous numerical column, that is when you'll go with a histogram. Right, so next up, we'd have to create a scatter plot between monthly charges and tenure. So tenure is on x-axis and the monthly charges is on y-axis. So plt dot scatter, x-axis would be tenure, so customer churn, tenure, and then I'll set in the column for the y-axis. This will be customer churn, and this will be equal to monthly charges. Let me just run this, right? So this is what we get over here. Now let me also set in the labels for this. So plt dot x label, and this would be equal to tenure. Let me type in tenure over here. Similarly, I'll also set the y label over here. So this will be plt dot y label, and this would be equal to monthly charges. Right, so now we also get the corresponding x and y axis labels. After this, I'll also go ahead and set the title. So it'll be plt dot title, and this would be monthly charges versus tenure. Monthly charges versus tenure. Right, so this is our final scatter plot where we have the x-axis and y-axis labels, and this is the title, which is monthly charges versus tenure. Right. And finally, we'd have to also build a box plot between the tenure column and the contract column. So tenure needs to be on the y-axis and contract needs to be on the x-axis. For this, I'll just type in customer churn dot box plot, and so now I'll set in this to be equal to customer churn, contract, and after this, I have the column to be equal to customer churn, and this needs to be equal to tenure. Let's see what is the error over here. Columns not found. So let me actually remove this from over here and let's see what happens. All right, so now we get the result. So we had actually given the name of the data frame initially itself. So it was customer churn dot box plot. And now all you have to do is assign the contract onto the x-axis. So now when I said by equals to contract, what is happening is I'll have one box plot each for the different levels of the contract column. So I have one box plot for the month to month level. I have another box plot for the 1 year level and another box plot for the 2 year level. And over here, the y-axis, this is being determined by the tenure column, right? So this over here, 0 to 70, this is the tenure of the customer. And what we understand from this box plot over here is, so if the contract of the customer is of 2 years, then most probably the median tenure of the customer is very high. So if the contract of the customer is of 2 years, then his tenure or median tenure would be around 65 months. Similarly, if the contract of the customer is 1 year, then the median tenure of the customer would be around 45 months. And then if the contract of the customer is month to month, then the median tenure of the customer would be around 15 odd months. All right, so these were all of the examples of visualization. Now it's finally time to head on to machine learning. Right, so this was your data pre-processing part, where you had understood the structure of the data. You had learned how to extract individual columns, and after that you learned how to visualize the data and get some interesting insights from the structure of the data.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
We'll start off with our first machine learning algorithm, which would be linear regression over here. And linear regression, as you already know, so over here the dependent variable would be a numerical column, and you're basically trying to understand how does one variable change with respect to another variable. And over here we'd have to build a simple linear model where our dependent variable is monthly charges and the independent variable is equal to tenure, right? So, or in other words, we are basically trying to understand how does monthly charges vary with respect to tenure. So monthly charges, dependent variable, tenure is the independent variable. And these are all of the subsets when it comes to this linear model. So we'll start off by dividing the data set into 70-30 split, and then we'll build the model on the train set, pick the values on the test set. After that, we'd have to find out the root mean square error, and we'd have to print out that root mean square error. So let me go ahead and import the linear regression model from sklearn. So I'll type in from sklearn import linear model. After this, I'll type in from sklearn dot linear model import I need linear regression, right? So these are my two basic libraries. So I needed linear model, I needed linear regression. Now I would also require the train test split. So I'll type in from sklearn dot model selection import train test split, right? So this train test split method would help me to divide my dataset into training and testing sets. So now it's time to divide my data into training and testing sets. So before that, I'd have to get my target and the features, or in other words, I'll have to separate my dependent variable and the independent variable. So monthly charges is the dependent variable. So what I'll do is y equals, and I'll extract only the monthly charges column, and I will store it in a new variable and name that variable to be equal to y. Similarly, I'll only extract the tenure column, right? So I'm extracting the monthly charges column and I'm storing it into a new object, naming that object to be equal to y. Similarly, I'm extracting only the tenure column and I'm storing that column into x. Run columns, customer churn. What seems to be the problem over here? Monthly charges. Let me put it to be capital C over here. Right. Now let me print out the head of these two, y dot head and x dot head. Right. So these are the values from monthly charges column and these are the values from the tenure column. Now let me go ahead and divide these two into training and testing sets. So I'll use in train test split. I'll pass in x as the first parameter. So all of the features would be which are stored in x go as the first parameter. After that, I'd have to give in the target labels, and the target labels are which are basically my monthly charges, which are stored in y. And then finally, I'd have to give in the test size. So let me check what was the test size. So the test size was supposed to be 0.70. And then I'll also set a random state. So if I want to use these values again, I can just set the random state to be equal to the same value which I'm giving over here. This is smallest over here, right? So this test size 0.70 basically means that 30% of the records would go into the testing set. Oh, this has to be 0.30. Sorry for that. Yeah. So 30% of the records would go into the test set, and 70%, the rest 70% of the records would go into the training set. Now I'll be getting 4 results over here, and those 4 results are X train, Y train, X test, and Y test. These are actually the labels which we conventionally use. I'll explain what these are exactly.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
X train, Y train, and then we have so this would actually be X test first, X train, X test, Y train, and Y test. So over here, X train represents all of all of those values of your features which are present in the training set. X test represents all of the features which are present in the test set. Y train represents all of the dependent values which are present in the train set, and Y test represents all of the dependent values which are present in the test set. And whenever we are building a model, we'll build that model on top of the train set, right? So we'll build the model on top of X train and Y train. Let me also show you the shape of all of these. So X train dot shape. Let me do the same for the rest. X train dot shape. I'll make this to be Y train. I'll make this to be X test. And I'll make this to be Y test. Right. So X train, Y train. So the training set has these many records, and the testing set has these many records over here, right? So these are all of the features which are present in the training set, and these are all of the features which are present in the. Sorry, these are all the features of your dependent variables, and these are all of the features of the independent variables, and these are all of the target values when it comes to the test set, and these are all of the target values when it comes to your dependent variables. All right. So now that we have xtrain, ytrain, xtest, and ytest, let's go ahead and build the model on top of the training data. Now I will go ahead and create an. So normally your training data would be bigger because so let's say your splits are either 70-30, 65-30, or 80-20. Because the more data you give for training, that is better. But then again, you can't give out your entire data for the training set, right? So the purpose of training your model is to make sure that your model learns the underlying patterns of that data. And once the learning is done, you'd have to also test how well the learning is done, right? And to test, you'd also need a sample space for that test set. So consider this simple case. So let's say you're giving an exam, but for that exam, let's say if you got 100 exercises. So your syllabus comprises of all of the 100 exercises, and you'd have to learn all of those 100 exercises. But when it comes to your test, it will have only 10 exercises from all of those 100 exercises, right? So the training needs to be done, but then again, the test space, it needs to be completely new, which is not learned by the model, during the training phase, right? That is why the training set has to be completely different and the test set has to be completely different. And the division of training and testing set is done to make sure that overfitting doesn't happen. And when overfitting happens, the problem is this model will perform well on this particular data set, but when a new data set comes in, it'll miserably fail. Right? So this is the reason why we divide the data into training and testing set. Right. So now let me go ahead and create an instance of the linear regression model, and I'll name that to be regressor. So I've created an instance of linear regression over here, and I'll go ahead and fit the model on top of the training set. So it'll be xtrain and ytrain. Right, so I fit the model on top of the training set. Now it's time to predict the values. So it'll be regressor dot predict, and I'll be predicting the values on top of the xtest. And I will store this in, let's say, ypred. Now I've fit the model on top of the training set, and I've also predicted the values on top of the test set. Now I'd have to know how well the prediction has been done. And for this, when it comes to linear regression, we have something known as the root mean square error. So the lower the value of root mean square error, the better your model. And again, we have an inbuilt method to calculate the root mean square error. So I just have to import sklearn.metrics, and from sklearn.metrics, I'd be importing mean square error. Now after this, so mean squared error, what we actually want is root mean squared error. So I would need the np dot square root, and let me use the mean squared error, and this takes in two parameters. First parameter comprised of the actual values which are present in ytest, and second parameter are the predicted values which are present in ypred. So I will cut this and let me ease this to be in this over here, right? So we get a root mean squared error value of 29.39, right? So now let's say if we build some other model with some other independent variables. Now we'll go ahead and build the model, and we'll also predict the values. Now after predicting the values, we'll also have to calculate the root mean square error. So this root mean square error is actually relative. So let's say if there is some other model, let's say model 2, and if the root mean square error of that model 2 is, let's say, 39, then this model would be better than the second model. Similarly, if there's, let's say, model 3 whose root mean square error is 19, then that model 3 would be better than this model which you built over here. So here we are predicting the monthly charges values. That is exactly right. So let me actually show you that. So let's see, I'll put in ypred and let's say I'll have a glance at the first 5 values, right? So these are the monthly charges predicted. Let me also show you y test, then 5, right? So these are the actual values and these are the predicted values over here. Right. So this is not exactly dependent on the churn of the customer. So what we are doing is we are building an entire data science lifecycle process. So over here, we are trying to understand the relationship between the tenure of the customer and the monthly charges of the customer, right? So over here, what we're basically trying to understand is, let's say if the tenure of the customer is at around 10 months, what would be his monthly charges? Again, if the tenure of the customer is 30 months, what would be his monthly charges? Similarly, if the tenure of the customer is 70 months, then what would be his monthly charges? So this is what we are trying to understand over here, right? So this time we'd have to build a logistic regression model where dependent variable is churn and independent variables are tenure and monthly charges. Again, I do the same thing. Let me actually copy these two. So this is what we did over here, Aditya, right? So this is where we went ahead and predicted the values, didn't we? Right? So I have divided my data set into training and testing set. And over here, I am fitting the model only on the train set, right? So training is happening on the training set, or the model is learning from the train set. And we are predicting the values on the test set. So this model, this linear regression model, has not yet seen all of the records present in the test set. It has only learned from the values which are present in the training set. So we'll go ahead and build the linear regression model now. Customer churn. Let me also put in y. I'll do the same thing. So in the logistic regression model, our independent variable is monthly charges. Let me put monthly charges over here, and the logistic regression, the dependent variable is churn. So I have extracted or I have got my features and my target over here. So features are basically my monthly charges and my target is present in the churn column. And I'd want to understand if the customer would churn or not on the basis of the monthly charges of the customer, right? So I've done this, and the rest of the process would be the same over here. I'll go ahead and divide this data frame into train and test, right? So this is 65-35 ratio this time. So I'll set it to be 35. So this time 35% of the records would be present in the test set, and the rest 65% of the records would be present in the train set. And I'm storing all of those into xtrain, xtest, ytrain, and ytest. Right. After this, I'd have to import the logistic regression model. So from sklearn.linear model, I'd have to import the logistic regression model, and I'd have to create an instance of this. So I'll name this to be equal to log model. Right, so I have created an instance of this, and I'll go ahead and fit the model on top of the training set. Right, the entire process when it comes to implementing this is pretty much the same, right? So Python makes it extremely easy. The sklearn library makes it extremely easy. All you have to do is take in the data, find out your independent variables and your dependent variable, and then go ahead and divide those target and features into training and testing set, build the model on top of the train set, and then break the values on top of the test set, and then you will find out the metrics. So for classification, it's confusion metrics and your normal accuracy score, and for linear regression, it could be either root mean square error, or moving averages error. So log model dot fit, and I will fit this model on top of the training set again. So xtrain and ytrain, right? So I have fit the model, Yes, we can also have multiple independent variables, Sharadata. So again, so if we have a single independent variable, then that's that's a simple model. So when it comes to simple linear regression, we have a single independent variable. When it comes to multiple linear regression, you'll have multiple independent variables. Right. So this basically means that we are trying to understand how does our dependent variable change with respect to multiple independent variables over there. And so again, consider this equation. So linear regression equation is based on this. Let me actually open Notepad over here, right? So y equals, let's say, x1 plus x2 plus x3 plus x4. So what happens in a simple linear regression is you just have one independent variable, which would be x1. What happens in multiple linear regression is you have multiple independent variables, which are x2, x3, x4, and so on. Right? And you're trying to understand how does y vary with respect to all of these independent variables. That's pretty much it. Right, so let's proceed with this. We have built the model on top of the training set. Now let's go ahead and predict the values on top of the test set. So it'll be log model dot predict. So here we change the value of x, and no, we are not changing the value of x. We have multiple x values over here, right? So this becomes mx1 plus m2x2 plus m3x3 plus m4x4 and so on. We have multiple independent variables, and you are trying to understand how does y vary with those multiple independent variables, right? So we have predicted the values now, right? So when it comes to a classification model, we can use the confusion matrix, right? So let me import the confusion matrix. So from sklearn.matrix, I will import the confusion matrix, also the accuracy score. Now let me find out both of this. I'll pass in the actual values and the predicted values. Actual values are present in y-test and predicted values are present in y-pred. Similarly, accuracy score, I'll do the same thing. Y-test and y-pred. Right, so this is our confusion matrix and this is the accuracy, right? So to get the accuracy, what you'll basically do is you'll divide the left diagonal with all of the values. So left diagonal represents all of your correctly predicted classifications. So this comprises of all of your true positives, right? So this part over here, this is all of your true positives and this is all of your true negatives, right? So when you divide this with the entire sample space, that is when you will get the accuracy. So let me do that. So that'll be 1815 divided by 1815 plus 651. And I get the same accuracy, which is 73.60, right? So I get an accuracy of 73% for the model which I've built. Now I'd have to build a multiple logistic regression model where the dependent variable is the same and the independent variables are tenure and monthly charges. So now we have two independent variables, so I'll make the changes here itself, right? So Charada, the question which you're asking, what if we had multiple independent variables, right? So over here, we have two independent variables. So this time the independent variables are monthly charges and tenure. And I'm trying to understand whether the customer would churn or not on the basis of these two columns, which are monthly charges and tenure, right? So X now would comprise of these features and Y is the same. And the ratio is 80-20. So I'll change the test size to be equal to 20 over here. I'll go ahead and fit the model. It's the same. Again, I'll flick the values is the same, right? So I build the model. I predicted the values. The only difference which I made over here is I have two independent variables this time instead of a single independent variable, right? Predicting the values. After that, I'll import confusion matrix and accuracy score, right? Now over here, again, I'm calculating the confusion matrix and this time I get an accuracy of 77.50, right? So this time it'll be 935 plus 157 divided by 935 plus 157 plus 106 plus 211, right? So we get an accuracy of 77.50. So this left diagonal are all of the values which have been correctly classified, and this right diagonal represents all of those values which have been misclassified. So this was logistic regression, and then we've got two more machine learning algorithms left, which are decision tree and random forest. So let's build these two. Right, so for decision tree, dependent variable is the same, which is churn, and independent variable is tenure. Right, so let me manually do this. X is customer churn, and the independent variable is tenure. Let me also extract the dependent variable. So the dependent variable would be churn. You have to make sure that you put in the spellings correct, and also you have to take care of the small caps and the capital letters over here. Right, now I will go ahead and also import the decision tree classifier. So from sklearn dot tree, I'll be importing the decision tree classifier. Now I'll go ahead and divide this data frame into train and test. So it'll be the same process. Let me copy this. Let me paste it over here. So the split is 80-20, which is what we are doing over here, right? So this is our feature, this is our target labels, and we have divided the data set into training and testing set. Now let me go ahead and create an instance of this decision tree classifier. I'll name this instance to be, let's say, my tree, right? And I'll go ahead and fit the model on top of the training set. So my tree dot fit, this takes in two parameters, which are x train and y train. I fit the model. Now it's time to predict the values. My tree dot predict, and I'll be predicting on top of the x test. Now I'll import the metrics, right? So let me calculate the confusion metrics and also the accuracy score. Confusion metrics. So I'll actually have to store this in a object first. Again, I'll be storing this into ypred. Let me run the cell again. And this again takes in two parameters. First parameter is all of the actual values which are present in ytest, and all of the predicted values which are present in ypred. So this is our confusion metrics now. Let me calculate the accuracy, which would be 965 plus 87 divided by 965 plus 87 plus 281 plus 76. Right, so for this decision tree model, we get an accuracy of 74%. Right, so the process is entirely the same, guys. Right, what we are doing is, again, at the risk of being redundant, so what we are basically doing is finding out our features and target variable. After that, we are dividing the features and target into training and testing split, and then we'll go ahead and build the model on top of the train data, and then we'll predict the values on top of the test data. Once the prediction is done, we'll calculate the accuracy to find out how well our model has learned. Right, so in the entire data science life cycle, our most important part is the data processing part here. So this is your entire end-to-end project on the customer churn data set, which comprise of data manipulation, data visualization, and implementing all of the machine learning algorithms.
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. val, B, raise, C, try, D, width. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
2D graphs and plots can be created easily using Python script. It can produce the output in a various hardcopy format. That means whatever graph you see here, you can save it to a PNG file, JPEG file, or whatever. So that's where this comes really handy. Okay, that's where it really comes handy. Okay, next is next is why to choose Matplotlib, because it has a, first of all, it is a OOP based API. Okay, the library is almost based on OOP settings, so that means it will have the same kind of structure as classes and objects when you try and refer the Matplotlib module. So that's why you must have seen we have used matplotlib.pyplot, right? So matplotlib is the basic class and pyplot is a function of it. So that's why class name dot object name, object name dot function name, that's how we use it, right? That's the OP basic. So that's how we do it. Okay, next is very wide variety of graphs. We will see that next, like what all types of graphs we have in Matplotlib and how that can be used and what are the usage of those graphs and where do we use it, like that. We have simple functions used for visualization. So if you go ahead and see here, forget about the first example, see this basic. What we have done, we have taken a np.a range. Okay, we have taken a x variable np.a range, and we have the values from 0 to 10 with 0.1 separated. Okay, then we have taken a y value which is 2x plus 5, so that is an x and y linear equation. Okay, and we have plotted the xy points, and this is how it looks like. So this is how you plot a line plot in Matplotlib. Okay, next what we have done, plt.show to show this plot. Okay, to show this plot to you. So that's how easy is that's how easily you can visualize a function in Matplotlib. Okay, so with this plt.show function, you can see the graph in here, and plt.plot will show you the plt.plot will plot you this line. Okay, so that's how easy it gets when you use Matplotlib functions for data visualization. Okay, so that's how it is. And always remember one thing, the behind the scene, the main module that is responsible for this data visualization is called pyplot. Okay, so that's why if I go back to the code, you will always see we have imported the module matplotlib.pyplot. Okay, we always have used it, right? And we have used alias just to have a ease of reference, right? So that we don't need to write the entire thing in there. So that's how it is. Okay, so that's where this Matplotlib is. That's how easy Matplotlib is. Next, what we are gonna see is what are the different types of plot that we have. Before that, let me come to this inline thing. So this inline function, if you don't have it, it will still work. Okay, this percentage matplotlib inline, you won't see a difference in Jupyter Notebook. Okay, because this Jupyter Notebook is anyways browser based, right? So this won't give you any difference when you use Matplotlib from any web based or any kind of notebook kind of scenario. Okay, but if we have a different set of, if you are running Python separately, right? If you are running Python separately, correct, using Spider, it can be Spider, it can be a simple command prompt of Python, anything can be there. So if you are running it from those, IntelliJ idea means PyCharm. Okay, for Python the ID name is PyCharm. So if you are running using those IDs, or if you are running using like what, let's say if you are running it from the command prompt, then this will create a separate window. So that's where it gets difficult. Okay, so that's where it gets it is, it is advisable to use this like numpy, this matplotlib inline command for having the graphs inlined to the screen that you are currently using. Okay, otherwise what it will do, it will create you a whole separate thing. Okay, so it will give you a different set of, I mean, a different window where you will see the plot. So that's why we use this Matplotlib inline. So that's the basic standard, to have it displayed in the same window. Okay, so that is why we use Matplotlib inline. But if you don't want it, if you want the separate window to pop up, it will also work. Okay, that will also work. So that's no need to be worried. Okay, before that, let me show you what are the different types of plot that we are having in Matplotlib and what are their uses. Okay, then we will go to each of the examples one by one. So if the what you need to remember from this whole lecture will be three things. Okay, first of all, why and what plot need to be used, where it need to be used, and how you can write those. Okay, customization, even if you learn it slowly by playing with it, it's perfectly fine. I don't That's not a matter. Okay, the customization thing, coloring thing, changing the axis labels, adding legends, changing the colors, there can be thousands kind of customization in Matplotlib. Okay, so do I have that mail with me? No, I will have it my official email ID. Okay, so what I did, for some requirement I created, there is some kind of graphs and charts that goes to higher management. Okay, for reporting purpose, that goes every day. Okay, so I created something using Python, no data sciences involved. That's a straightforward thing, much easier. So I created a simple script or simple job using Python. What it does, it takes in data from a RDBMS, it plots the data nicely in a Matplotlib plot, and it sends it to you, sends it to the upper management. So when I am telling upper management, that is D plus. Okay, so that's where this comes handy. So and there you understand, right? When we are going to show this to upper managements, we need to have the graphs beautiful, we need to have all the specifications, we need to have pointers, we need to place them in the right position so that they don't find any errors and they won't accept anything so easily, right? So that's how powerful Matplotlib library is. So otherwise I would have shown you. So that's how you can do it. So the graph, what I can do, like the simple graphs that you are seeing in here, you can change the background color of the graph. Okay, so the background will be of some different color and the foreground will be of some different color. As you are seeing there in the right hand side, we have a bar plot, right? In the bar you can choose each and every bar color one by one. Okay, that can also be done. All these bar objects can be accessed individually. Okay, once you plot these bars in Matplotlib, right, all these individual bars can be accessed one by one. You can change their width, you can change their height, you can change their color, you can set text to them, you can write text in between them. So whatever you can do in Excel with all these graphs, the same things can be done in Matplotlib. But again, those things are not required for your day-to-day work. It will require very rarely. So if even if you don't understand those, even if you like the Anascom quartet I have shown you, if I start explaining the whole graph, it will take the entire class because it has too much customization in it. Okay, so just to keep it short and just to give you the proper idea so that you can start experimenting or playing with it, the basics I will tell you. Okay, and on the basic you can build up. Okay, you can build up on the basic. If you do understand the core concept, you can easily build up. Okay, so that's how powerful Matplotlib is. And let's see what kind of graphs we use. We have line plots. So line plots, what we use just to plot 2D equations, right, with x and y. There we will use line plots. Okay, so line plot will give you a trend line in an equation. Okay, so when we see linear regression, we will see its use pretty heavily. Okay, for machine learning, and also for observing a data set how it is distributed. This is really needed. Okay, next is bar plot. This is the same as line plot. The difference between these two is you can add a trend line in bar plot also, so that way it will become this, but this denotes the area covered by the point. Okay, so the bar will start from x-axis and it will go, the height of the bar will equal to its y value, and the shaded area will be showing the area covered by that point. Okay, So that's where bar plot is needed. Bar plot is basically this it is required in the same way we have line plots. So what is different in here? In line plots you might not be able to tell what is the value of x for the value of y at x equals 17.5. You need to go there, you need to see, it will be difficult for you. But in bar plot you can see it there directly, right? Because the bar will do that. Significance of width, there is not much, it is just to illustrate, okay, illustrate this bar one. Okay, this is that is how this bar is designed. So bar means it will show you some area covered by the curve. So if you calculate this rectangle, so what it has, this rectangle is same this rectangle has this width of some x value, height of this y value, right? So if you calculate a rectangle covering that area, so this will denote the area covered by that point, okay, by that x and y point. From the ending to beginning, this area will be covered, so area is shown here. Next is scatter plot. So scatter plot and line plot again are same, but only difference, the points are not joined. So you need to understand when we use these two. When we have a continuous set of data, we know that it might fit a linear equation, right? It Yes, Azam, I just explained it. What is the significance of the area, right? So in the line plot, if you have like if you have a what like continuous set of data, then in that case this line plot will be visible. But if you don't have a continuous set, if you have some chunk of data, clusters of data, then you will use scatter plot. This is to see the data distribution, how they are distributed, and this is the trend line of the data. This example of scatter plot you will see when we are covering clustering. You can understand, right? We have seen some clustering algorithms. So if you plot the data in this plane, then from that you can easily understand how many clusters will be formed from that k-means, right? The k value you can find it from your you can find it by checking that manually only, right? If you plot the data, it will be clear to you. After clearing the data, if you are able to plot that data in this plot, you can find the value of k without any hack, right? And you can pass it to the algorithm to give you those many clusters and their centroids and all. But what you not need to do is you no need to check the data points and decide which point will be belonging to which cluster. Those things you no need to calculate. Okay, next is this histogram. Histogram is basically used for image processing purpose. This histogram shows you basically, okay, so so this histogram is basically used for like image processing purposes. And what this bins are denoting, this bins denotes the number of times the values the frequency of the values the frequency of each point occurring in the data set. Okay, so that's what this bins are denoting. So this is not really used in data science, somewhat used, but it won't fit our purpose always. So maximum for image processing this is used to see how the data is spread and what are the frequency of the data point that we have, what are the frequency of pixels that we have, those kind of cases, and histograms comes handy. I will show you all these examples, but again this is not really required. Image plot, again this can yeah, CPU processing is also histogram, right? So that's what. So wherever the scenario fits in to show you some frequency kind of thing, wherever it fits in, then you can use histogram. Okay, wherever you need to find out some frequency of some point in dataset. Let's say for CPU processing, if you see the graph how it will look, it will give you how much CPU is used in what point of time and what is the frequency of high CPU uses. In that case they will use histogram because it will give you the frequency related data. Okay, difference between bar and histogram is bar plot won't give you this frequency, it will just plot the x and y points. It is almost similar to the trend line, except it will show you the area, it won't show you the frequency. But from histogram you can find out the frequency. When we go to example, let's see how we can do that. Okay, okay, next is image plot, right? Image plot is to plot some image. Okay, again you won't need that. So image plot will fit in a existing image to this to the 2D plot, and it will show you the height and width and all those things. You can see visually. Okay, next two plots are really important for us. Those are box plots and violin plots. Okay, so let's do one thing. Let's see the examples of all the 5 plots that we discussed. Then we will discuss the rest 5. Okay, rest 5 or 6, whatever we have, we will discuss those after that. Okay, let's see these examples first. So this line example I have already shown you. Now the next one is how to customize these lines. So basically these are the basic customization technique I will show you. So see here what we have done. We have taken the same example as the earlier one, just we have reduced the number of points. We have used this fig equals plt.figure, fig size equals 10,5. So this one, this plt.figure object, what it does, so if you don't use it, that also work, but how it works is this plane is a single plot. Within the plot you can create multiple figures. So let's say you want to create two charts side by side. In that case you will use this figure. Okay, you will create a figure size, I mean you will create this 2D plane first. Okay, then you will plot this line. That is the best standard practice, so you should follow that. Okay, you will create a figure object, then you will plot the data points. Okay, that is the standard that we do. So how do we do that? What we do, we use plt.plot function as shown before. We are having x and y, two values for x and y data points. Next we are passing is this line width parameter, right? So this is to provide that line width, what it will be. Next is line style. It has many different line styles also. It has dash, you can give 0, you can give o, any character you can give. Let's say I am giving I, and if I run it, it won't run because I is not a supported character. What was that supported one? I don't remember. I think dash was supported. Yeah, so this line style you can provide anything. Okay, sorry, not line style. Line style will be dot dash, these two things only, or a continuous line. I was talking about this marker. Marker you can put anything. Okay, so marker you can put something like this also. Unrecognized marker. Marker, except to what we had cross, I believe. We had cross, yeah, we have plus, those kind of markers are there. So this marker object is to show you this points. Okay, show you this data points, how you want to see those, but o gives you the best visualization among all. Okay, so that's how you can use it. Okay, next is this line style is for styling this lines, this intermediate lines. If you provide colon, then it will be like this dashed line. If you provide a dash, dashes will join, right? So dashes will join and you will see a straight line. So that's how this works. Next is color. You can provide any color. You can write the full name also. You can use the short name also. You can provide here the RGB values. You can provide, let me show you. You can provide this hex values also. You can do anything. Okay, let me take the default color that is coming. So I will show you this to example. Come on. Okay, if I tell it take it this, and if I put it here, this will also work. Okay, see the lines have changed to blue, right? If I provide this, that will also work. I don't remember the syntax for RGB. RGB is not much used, but still, okay, sorry. But still you can provide like this, I believe. RGB anyways we don't use it much. We use the simple names or hex codes, because hex codes you can find in many places, like in net you can have it easily available. You can create your own colors, but RGB we really don't use in plot. Yeah, so that's how. So I will still show you because it can be done. So I believe we can only mention the tuple. We no need to write anything in behind. Let's see. Still it doesn't work. Why? How to give it? Just the tuple without this single quotes? I believe yes. Let's see how it works. Still not working. So you can provide the hex value, or you can provide the mnemonics also. You can type in any color in full also. If I type it yellow, it will also work. Okay, so that's how you can use this color attribute for all the graphs. For all the graphs you can use it. Okay, so you can type in any color, or you can provide the hex codes also. Okay, so let me give some good color here. So that's how it works. Okay, that's how this color attribute works. Next is for alpha. Okay, alpha is for reducing the brightness. Okay, reducing the I mean the transparency of it. Let me give it blue. That would look the best. So that's how. So alpha is the transparency. Okay, okay, next is alpha is for reducing the brightness. So let's say you will understand on your own only. I don't need to explain. If I run it to 1, see this is much vivid, but if I do it 0.1, you will see this is way too dim. It will be way too dim, right? So that is what is alpha. Alpha is for reducing the brightness. So alpha is the transparency factor. So if you reduce the alpha, then what it will do, it will make the line or plot whatever you are doing transparent to the plane. So it will match the background color of it. Almost it will match the background color of it. It will be a very fade color. But if you pick a high alpha value, it will give you somewhat deep lines. Okay, you will see the dark lines, dark colors over there. Okay, so that's what is alpha used. Marker, as I have shown, these points are called markers. So that's how we plot a line. Next is this title object, right? This title function. So what we do with this title, we plot this title like line plot demo. This we put it using this plt.title, and it will automatically be placed here. Okay, it will automatically be placed at the top. You can change it to bottom also. You have options for that, but the basic that we follow, the standard, that is to put it in top always. And x level, y level, x axis, y axis, you can type it. So the labels, axis will be labels. Okay, axis will are labels. It is not for the value, it is for the labels only. Okay, that's how it is. And for the limit of it, the graph will take on its own. It is best to leave it on its own, because it will be helpful. Because if you are trying to manipulate the graph, because see, you will always not know this, right? That how much data you are covering, how much data you are taking, like that. So that's why this is best to leave it on the graph itself. So it will decide the best min x min y, min x min y, and max x max y, and it will plot it. Okay, so that's how it works. Okay, next is for plotting legends. Legends means this small markers. So to show you, to show someone which one line denotes what, right? That is what is legend. So for plotting legend, what we do, we use this legend function. Okay, we use this legend function, then within bracket we line the marker name. It can be a list also. Okay, it can be a list. If we had 2 lines here, let me show you.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
That will also work. Let's say I have an orange object now with marker as cross. Okay, and it is darker. Let's make it darker. And if I run now, you see we have 2 lines now in the same plot, right? So how you can have here, you can write like this, and see everything will be taken care automatically. Okay, see here in legend it's already added. The my line thing is already added, and LOC equals base means the graph will on its own calculate the best position for the legend, and it will put it. So it will always put in the best position. It can be down, it can be up, it can be anywhere. Okay, plt.grid true, that is to show these grid lines. If you don't want it, just don't mention this function. It won't show you these grids. Okay, so that's up to you. If you like the grids, you can keep it. If you don't, you cannot. So there is no really no real thing in that, in showing or not showing the grids. Okay, somewhere if you fill it, you can provide you can have those displayed. Okay, So that's how this grid works. And plt.show, as you know, to show the plot, to show the to display the plot in front. So that's how this thing works, this line plot works. Okay, so that is what is about line plot. And you have seen only single line plot in a picture, right? So I have shown you two line plots in the same graph, right? Let's say we have two different plots in the same we have two different subplots in the same plot object. How do we do it? Okay, so that is where this subplot function comes into picture. That is where this subplot function comes into picture. So if you see carefully what we have done here, we have taken the same thing, the same functions that we used in the earlier example, and we have shown you this. We have shown here the two different plots in the same thing. Okay, we have shown two different plots in the same figure. So that's how. Okay, so the next thing is the parameters that we have passed and how do we create this subplot. Okay, so how do we do is, firstly what we did, we used plt.subplot function. Okay, so subplot function, we have, there are many parameters that can be passed on to it. Okay, there can be many parameter. So we have provided only three parameters here. This is just to have it in a standard one. Okay,
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
so how does it work? Okay, that means the first one, 2, right? These are for number of rows and number of columns. Okay, so we have created one number of row and two number of columns. Why one number of row? Because we want this to have in a single subplot, right? We want this to have in a single plot. So see, when I change it in two rows, so this first one gets smaller, right? Because it has created two rows. First one contains the first graph, second one contains the extra portion of the second graph. So always try to have n rows as one if you don't want to create more rows. Okay, so sorry, for the first subplot, for this first subplot, if you create two rows, then the same area will be divided into two parts. So the graph became smaller in and got fit into one row, and the next row is left around. Okay, so that's how it is created two rows here. So here, so the idea is, if you want to fit two graphs in the same subplot, then only go for this 2 1. Okay, but standard is to use one, because we generally, when we subplot it, we want the subplots to contain one graph. If you want to fit in two graphs like this, you can create a separate subplot here and you can plot the graphs. Okay, so that's how this plt.subplot is used. See here we have passed in number of rows and number of where we have passed in only plt.subplot, we have passed in some integer numbers. plt.subplot 221 222, so these are just integer numbers, right? So this is 221, this is 222, the starting point of the subplot, and the plot will adjust on its own. This is also an expression that we use, but this is not standard. Okay, this is not standard. This is just to have four plots, four plots arranged in a rectangular way. The standard is always this one. So we pass the number of rows, number of columns that we want, and this one is for number. So that means how many figures are there. Okay, how many figures are there. So this thing, the pyplot.figure function that I have shown you in the earlier part, that will be called, and the figure number will be attached to it. That means this is figure number 1 and this is figure number 2. Okay, so if you want to customize it using this figure object, then you will see how you can use it, but that is not really required. Okay, For now, just know that this is a number parameter that is being passed into this function, and that denotes how many number of what is the figure number that is there in the graph. Okay, so for the next one, if you see, we have created the same subplot size 1 2, and we have provided number equals 2, so that means this is a figure 2. So this is figure 1, this is figure 2. Okay, the rest function the same as what we had in this. So plt dot title, it has plotted these titles of graph 1 and graph 2. Plt dot show showed you the graph, and plt dot plot plotted this x and y1 and x and y2, these two things. Okay, so that's how now line plots can be created and customized, and also multiple line plots can be created in the same subplot. So this applies to all the other graphs that we are going to see. So we won't show you those in that much detail, but you can always create a subplot. You can fit in 2 bar plots, 2 line plots, 2 scatter plots, anything you want in there. Okay, so that's how you can create this subplots. So is this clear? Then we can move on to this bar plot. Okay, so bar plot is basically to show you some counts, to show you some this is basically used to show you counts. Okay, so see here what we have done. We have created a data set with 3 this is a dictionary, right? So we have count for apple, mangoes, lemons and oranges. Okay, for x-axis we have taken the dictionary, the list of keys from the dictionary, and for the y-axis we have taken the list of values, that is the count for those. Again, we have created a figure size. How do we plot a bar chart? We plot a bar chart using plt.bar. We passed in x and y. This kind of nice little rectangles are shown over here. So this is 15 and this is the area behind this curve. So next we will see how can we change the width and all of this curve. Okay, so let's go to this one. See here, this is actually this like horizontal bar graph. Okay, so here for horizontal bar graph we have taken the same data set, we have used bar each function, right? So bar each and bar both will have the same kind of customization. This width will be decided on its own, you no need to specify that. Again, as I told, you can change it, height and width you can change, but that is way too advanced. Okay, so this can be done. Just you, if someone asks in the interview, just tell them yes, we can customize those. It is not by default. But how that is a really advanced topic, I don't think interviewers will know also. Okay, next is data. How do we create horizontal bar chart? This is a reverse bar chart. So here we can have bar each function to be called for the plot, and similarly we pass in the arguments. Now the next thing to be covered is like bar and bar chart customization will be same as both will be same. So here beside this I can provide the colors also. Okay, so colors, let me put, say what should I put? Let's say I put maroon. So next one I will make it green. So that's how it looks. Okay, so you can pass in the color object, color parameter to it, and these bars will be colored according to that. Okay, so similarly for bar and bar each, same things will be applied. And this plt dot title, x level, y level, we have already seen, right, when we covered this line plot. So similarly those can be plotted. So see here, bar graph demo, quantity, fruits. Here also you can put it in the similar way. You can put it in this way. Let me show you. Copy is not enabled, right? So the similarly you can do for bar and bar each. So remember, bar is for plotting bar, bar each for plotting horizontal bars. Okay, so that's how bar plot looks like. Okay, so that's how bar plot looks like. Now next, any doubts in this, or scatter plot is fine now? So now we will go to the scatter plot. Okay, so scatter plot, see, scatter plot is a bit different. It is not like x and y equation. So we have 3 data sets, a, b and x. So this is x and y equation actually. So for this x value, this is y value for one. So let's consider this as x and y, and consider this as x and y1. Okay, so no equation we need to do. What we can do, we can just generally point these things. Okay, we can just distribute the points over the plot. Okay, so that's how we did. Okay, and this points will be taken automatically. Okay, the colors will be taken automatically. So next we will see how can we customize it. Okay, these are the basic customization techniques, not advanced. Many things can be done with it, just remember that. Okay, so again I will change it to maroon. Okay, so here, okay, next thing to be show you is for line plot we use plt.plot, right? For scatter plot we use plt.scatter. We pass the x and y arguments inside this scatter, and then we get this nice looking output. Okay, next is customizing scatter plot. Same equations we have taken. So this C, either you can write C or you can write color, any way it fits you. Okay, S is for size, that means size of these things. If you make it, let me add another 0 and run it. So it will bigger the size of the data points that you have. So size, that is really size, you can write a whole or you can mention the short name, anyways it will work. Okay, edge colors means if you see these lines carefully, the edge is colored as yellow. Okay, because so edge is colored as yellow. So for, if I do it black, you will see that, I believe it is really hard to see here. If I make it 1, I think you can see. Yeah, now see the green round objects are covered by a black border, right? So that is the edge colors to differentiate between 1 and 2. Marker, it can be different kind of things. So marker have 0 o 1, if we give, it will give you some this kind of downwards value. 2, if you give, it will give you some upper kind of values. For 3, you will have the in the reverse side. Okay, in the reverse arrow. And 4, you already have it, right? Or if you put O, it will be the round objects that is going to be put. Marker, can we customize? No, we cannot. Okay, so these are the choices for the marker object. Alpha, as we discussed earlier, alpha is for the same thing. Okay, alpha is for the same thing, to reduce the brightness of it. Okay, next is plt.legend title x level y level, same as others. plt.grid, same as others. So now if you see, we have a plt.savefig scatterplot.png. So this is to save the output of the curve that we discussed earlier, right? This is to save the output of it. So if I go back to my Jupyter notebook, see here scatterplot.png is saved. And if you open this graph picture, you can see, and then you can use it for your own purpose. You can attach it in mail, you can send it, or you can do whatever with this. Okay, so that's how you can save the figure to a nice looking image. So that the command for this is savefig, plt.savefig. Okay, so plt.savefig, that's how it works. So that's what is with scatter plot. And now next is this histogram. Okay, so is that clear? Next is histogram. So histogram is to show you counts for some numbers. So we have taken a huge data set to show you this counts. Okay, and we have created the histogram using plt.hist function. Okay, next we have passed in the array that we need to plot in histogram, and we have passed in this bins, right? So bins means where these markers will be put in. This is again intuitional, you can put it anywhere you like. So these are the markers, the marker points. So 0, 20, 40, 60, 80, 100, like that we have given. So how to, yeah, bins are intervals only, correct? So how to understand this histogram? So can you check the data? If you check the data set and if you see how many points are there between 0 and 20, 1, 2, 3, 4, 5, 6, 6, right? So if you check this, so 20 we have 1, leave it. So till until 20 we have 5 points, right? If you check from 0 to 20, what is the value? What is the y value? 5, right? For 20, so from 20 to 40, if you count, we will have 7 values, so it will be going up to 7. Okay, 40 to 60, it is really small, right? Only 1. So see here, the height of histogram shows you 1, right? 60 to 80, if you count most of the numbers, so 68, 64, 62, 60, 70, 78, 75, 79, and all those numbers. So almost 7 numbers almost. So if you check, or 8 numbers, whatever, so you will see 8. Okay, 80 to 100, 3. So 3. That's how to understand histograms. Okay, that's how you need to understand histograms. So that's what histogram denotes. Histogram denotes the frequency of data points between a range. So from 0 to 20, how many? 22. So what happens if we add another bin, right? The graph shape will change radically. Why that will change? Because within 0 and 10 we don't have any point, so it has kept it blank, so we haven't put the marker over there. Now let's say we are plotting a marker in 30. Okay, we are changing this to 30. So see it, from 20 to 30 the bin has changed, right? Because we have created two different markers. So 20 to 30 we have a dip, right? We have a dip. So within 20 and 30 we have 3 points, and 30 and 40 we have 4 points, like that. So that's why between 20 and 40 we have total number of 7 points. Okay, that's how to understand this bins attribute, and that's how to explain a histogram to someone. Yes, right, it will be changing with data, correct. Okay, so this is to color the histogram. We Yeah, so that's what I'm telling, right? So that's what I told earlier only, right? Before starting with the examples, bar you will see when you just need to, when you have the counts of some data points, you need to display those in a graph. So that's why you, when you use bar, linear equations when fits into scenario, you use line. When you want to see the distribution of data over a plane, you use scatter. And when for image processing kind of thing, and when you need to find out counts of data points, you use histogram, right? You don't know the counts, you want to find out without writing a code, you can, if you plot a histogram, you will have the counts, right? Okay, next is customizing histograms. Again, we have provided this bin numbers. Age color we have provided as black, and color we have provided this funky red color. Okay, title, X level, Y level, grid, Cepfig, already you know this, right? So same thing, not wasting much of a time. So H color and color, we can do it in all the graphs, and we can customize the graphs. Okay, so if you see this box plot, right? Box plot contains the quartile information of a data set. Okay, this is the statistical plot that we use heavily. So this below line will be your Q0, and the top line will be Q4. In between, this will be your mean, that is Q2. This will be Q1. This will be Q3. Okay, 4 lines will be there. Now this is how this data will look like. Now how do we calculate those Q1, Q2s? Okay, I have considered this data set, and I have calculated all those calculations. I have done all those calculations in my Word doc. Okay, when in Word doc we have all these calculations. So what we are doing, we are just having the equation, we are just sorting the array. So if you sort the array that is given, you will get this kind of an array. Okay, this array you will get this one. Okay, so next what we are doing, what we are doing is we are finding out the second quarter, we are finding out the mean of this. So how do we find out mean? What are the number of points? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, right? So we have even number of points. What is the definition of mean? Mean is the middle point of the data set, to which all the left values will be less than to that mean, and in the right side we will have greater than or equal to the mean, right? So we have taken, and for odd even number of values we take the middle two values. So we have taken these two values, we found out their average, and we found 20, and 20 is our mean. Okay, 20 is our mean, and this 20 is referred to as second quartile also. Okay, now so this is the mean. Okay, so here we split the data set. Okay, here in this 20 point we split the data set. Now as we have two middle points of the data, so 2 point we can consider in the for two parts. First let us take this part. Okay, let us take part from this to this 20, and part from this to this 20. Let us take this two part. Now this is already sorted, so we will again calculate their mean. So here if you see 5 number of data points are there, so that means odd number of data. So we will have the midpoint, that is 10 as our quartile, so 10 as our mean. So this mean is called as Q1. Okay, this is the first quartile. Okay, from 20 to 70 we have 30, this is called Q3, third quartile. So what this does, this gives you this 3 Q1, Q2, Q3 informations. And if you see Q0, Q0 is the minimum number, and Q4 is the maximum number. Okay, Q4 is the maximum number. These two are first and fourth quartiles. Okay, so 0th can we say 0? So that is our first quartile, second, third, fourth, and fifth quartiles. So we have 5 quartiles. So we generally consider this for Q0 to Q3. Q4 is the last one, so we don't really consider this as a quartile, but you can tell it like that. So this information will be pasted in the box plot. Okay, this information will be provided in the box plot that we have in here. Okay, that we have in here. So if you see carefully, for the first, this total, this is the box plot for that. What was the minimum value? 1, correct? So here it is 1. What was the first quartile? 10. What was the mean? 20. What was the third quartile? 30. And this sums it up. Okay, this 30 sums it up. So this is the box plot. This much you focus on, and the max point, what I was referring to as Q4, that is not there. That doesn't present. That is not present anyways. So here it is. Okay, how this height is defined? From 10 to 30, how many points are there? 6 points. So that's why this box is a bit bigger. Okay, that box is a bit bigger. So this, the height of it's almost 6. So that is what this height denotes. Okay, from 10 to 30, how many values, like that. Okay, so that's what is this height about. Okay, that's what is this height about, or you can say it like Q1 and Q3. In between, this height is given. Okay, so this box means the maximum number of data points are concentrated in here. So between 10 and 20, how many points are there? If you check, so we have 2 10s and 3 20s. So in a data set of 10, we have 5 values within 10 to 20, right? Within 10 to 20. So that kind of information you can get from there. Okay, that you can get from this box plot. So it basically shows you again the distribution of the data and the basic statistics of the data, the quartile range, and how and where and which part of the data is concentrated. Where the data is more concentrated. Okay, the height of the box is how many points are there, like that. So 10 to 20 or 10 to 30, we have 7 8 data points, so the box is a bit bigger, like that. And from 0 to 10, we have 3 data, so that is the height. Okay, it won't match with the graph. It is just for visualization purpose. It won't match with the graph height. I am just telling you for ease of your understanding. Correct, that is IQR actually. So IQR is, this is between Q0 Q1, this is between Q1 Q2, this is between Q2 Q3. Okay, so that is what is the frequency of the data, right? So that's why we calculate IQR. IQR is to give you a rough idea about how the data is, what is the frequency of the data, how it is spread in a in a range, right? So that's how this works. This won't match with the box line. So this big lines are IQR, interquartile range, and how many data sets are there, like that. So that's what is about this box plot. So here we haven't done many things. We have taken 3 distinct lists. We have taken all those into a single list, and we have plotted the data sets, and we have plotted that using box plot. Okay, that is the command for that. We have told it to show the means. We have passed in that show means to be true, so that's why that orange dots are shown. Okay, those are the means actually. So that's how this box plot works, and that's what kind of information you get from this box plot. Okay, that's what kind of information you get from the box plot. So this is what is about this box plot. Others I have already explained, so not repeating those things. And if you go on this code perspective, we have taken 3 different lists of total, order, and discount, and we have combined all those 3 lists into one using this list command, and we have passed 3 separate lists to plot it. This is just to have the information handy, because this is just to follow the syntax of the box plot, because it takes in the entire data set and it will create 3 boxes for 3 different data sets that it has. Okay, so that's how this box plot works, and that's what kind of information we do have from this box plot. And generally speaking, when you start analyzing data, you will use this box plot to quite some time. Okay, to check the data distribution and to check the quartile range, to check how it is distributed among the quartiles and like that. Okay, so that's what it is. Okay, see, don't think about the height much. So that height is basically the IQR, that is the distance between Q0 Q1, and that shows how many data points can be there. Okay, so that's what is this height reflects. Okay, height doesn't have much of an scenario here. So this is just to connect the plot and show it like a box. That's why the heights are there, and the distance between two quartiles are called IQR, that is interquartile ranges. Okay, so the the value of the height is interquartile range. So I mean, that is the frequency of the data set. Okay, what does that mean? So say 0 is the minimum value and 10 is the first quartile. So if you check the quartile range for the first quartile, that is 10, right? So the height equals 10. Okay, the mean is 20 and the Q3 is 30. So what is that quartile? That is like 10, right? So that's how this height is there. That is the interquartile range actually. Okay, so that's how it works. Okay, so next one is violin plot. It is the same as the same as this box plot, but it is different. It has the same values. Okay, Q0, Q1, Q2, mean, and all those kind of things it has. But what you see here is a violin kind of a shape for all this distribution, right? So that shape that you see, the shaded area that you see outside the middle line, that is the probability density function of the data set. Okay, that is the probability density function of the data set. What does that mean? Okay, what does that mean? So okay, what does that mean? This shaded area. Okay, this shaded area. So this is the probability density function. That means probability of having a number between. So what is probability density function? Probability density function means the probability of a point being in a range or a probability of an event being occurring, right? So let's say we have a range of 0 to 10. What is the probability that in for a particular data set, what is the probability that number 4 will occur? What is the probability of number 4 will be there in the data set? That is what probability density function calculates. Okay, so that means this is the probability of an event being happening in a sample space. You can, if I go by the by default stats terms, that is how it looks like, probability of some event happening in a sample space. So that is what it defines in probability density function, and the same thing reflects in violin plot. So how can you use it? Similarly, as I show you the calculation for q1, q2, q0 to q3, same lines are there. See, only 4 lines will be in here, right? If you see, there are 4 lines. So those lines are for q0 to q4, like that. And then the outside shade is the probability density function. So how can you see, what can you configure from those? Between 1 and 20, how many values are there? If you check the data set carefully, there are 5 to 6 values between 1 and 20. So that's why the curve is thickest at that point, right? So there is a high chance that if any future data comes in, so it will be in that range. So basically you need to think it in a bit other ways. So this static data set won't explain you. So let's say you have built a model. Okay, you have built a model based on some features. Okay, how I mean, I am trying to explain when you use it and how you use it. So let's say you have built a model without seeing anything. You have put in some features, you have taken into you have assigned the features into the weight to the features. So now how do you validate that? So if some feature values are in between, lying heavily between 0 and 20 or 30, then that means when you get a test data set from that of the same pattern, it will always follow that probability density function. So that way you can understand which feature to have what kind of a weight. Okay, and which feature is having what kind of a distribution. So these things you can check. So that won't be only a single feature, that will apply for all the features. That is a machine learning data set that you will have. So this applies to all those. For ease of understanding, I explained with one, because there is only single arrays are taken into account. So this we will plot for all the features, and we will see how the data is being differing. Okay, what is the probability that in future we can have different set of data? So if we have some true false kind of skewed data set, we will have it often. So 0 and 1 kind of data set if we have, then probability density function will have two peaks, one near 0, one near 1. Okay, so that's how it will look like. So let me try and show you. 10 points we have, right? 4, 5, 6, 7, 8, 9, 10. See here, because this is not visible because this is having this large values. So this value, if you enlarge it, you will see the this is stacked between 0 and 1 only, right? So you will see two peaks in here between 0 and 1. So that's how this thing works. So let me try this. See, you have two peaks, right, between 0 and 1. So as we have more ones, so the peak is flattened near 1. As we have less number of 0, so it is flattened near 0. But see, between 0 and 1, the curve is getting shortened, and when it goes uh, so 0.6 will be their mean. Okay, because that is what we have taken as 0 and 1. Okay, so 0.6 will be their mean, and if you see from 0 to 0.6, that the curve is a, so let's say 0 to 0.4, the curve is wide enough, right? Because till 0.5 we can consider it to be 0. So from 0.4 onwards it started to increase, because if it is greater than 0.5 we can estimate it as 1, right? So and at the 1 it has the maximum width, and at 0 it has a maximum width. Others are just shortened, right? So that's how probability distribution function you can use. So here what you can see, this is a skewed data set, right? This is a skewed data set, so this cannot fit a straight line equation or something like that. So you need to change it, you need to change the thinking, and you need to choose, explore other options. So that's how you can check that. Yes, this is a binomial function. So this is a skewed function. It will be of form e to the power x, right? E to the power x by 1 plus e to the power x. That is sigmoid function. Like that we will have this. Okay, this function will output two values only, 0 and 1. So that's how it works. Okay, so that's how violin plot works. So if this is clear, we will just I don't have examples for this because we won't need that. I will just explain these two plots, these three plots actually. We won't need that much, so I will explain what are those and how they are used, like that. Okay, next is this quiver and stream plot and area plot. These three we are not gonna use much. I will start with area plot. What is area plot? Area plot will show you the area covered in a line. So how you can see that? You can check like this. So let's say we have a line plot. Okay, we have a line plot. I am drawing some line over here. So let's say we have a line plot like this. So let's say this is the line plot. So area plot, what it will show this area. So it will show this area that we have inside this. Okay, that is the area plot. So that is to show you the area covered by a curve. Okay, area covered by some curve that we have. So that is what is called area plot. Okay, that is what is called area plot. Now if I show you here, like this is the quiver plot, right? So if you see all these individual data points, right, these individual data points are looking like vectors. It has some directions, right? So that is for basically magnetic field analytics and high-end physics needs. These are basically vectors. These are basically directed vectors. This is basically needed by physicians. Okay, this is basically needed by physicians, these two plots, this stream plot, this one up here and this one down here. These two things are basically required by physicists to analyze the vector and to do vector analysis. Here if you see, this has pointed ends, right? So that is the direction of the vectors that goes in or out. So electrical engineers or physicists can use this plot. So if any electrical engineer is there in class, you will understand this, right? Current inflow, outflow and all those kind of stuff. So if you have a large circuit, it will something look like this, right? So if you have a midpoint in here, what is the current input, what is the current output, and all those blah blah stuffs of electrical things will be there. So that's how this quiver plots are used. That's how the stream plots are used also. In stream plots, what is the stream plot? What is the difference? The difference is in the stream plot we won't have that have that vector direction, we will just have positive or negative value for a vector, and that will be just a representation of the vectors in a 2D plane. Okay, so that's how this quiver and stream plot works, and area plot shows you the area covered under a curve. So these three plots data scientists are rarely uses. Even if you use area plot somewhere some down the line, but quiver and stream, let me assure you, you won't use it ever. Okay, because we are not gonna deal with vectors, right? That's how. Okay.
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. Val. B. Raise. C. Try. D. With. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
So that's how we have image plot. So just know how to do that. If you open a image, okay. So how you can do it? You have image processing library called Pillow inside Python. Okay, you have Pillow library in Python. You can install it. No need to do it. Okay, no need to do it or remember it. This won't be used. So using Pillow library, you can use this image function, and you can open an image. All images are what? Arrays, right? They are arrays of pixels. So you can convert it to a NumPy array. You can pass that NumPy. You can plot that NumPy array itself, and that would serve your purpose, right? That will serve your purpose. So this is what ax1.imshow. Imshow is for showing the image. That is again a Matplotlib function. And if you pass in the array, the corresponding values will be shown as a image here. Okay, the corresponding values of the pixels will be shown as an image in the output plot. Okay, so that's what is image plot. And the image plot to histogram also you can do, so that way you will see the distribution of the like that distribution of the colors in that, right? Colors or pixels in that. So see here, this is at 250. This is a very high value, so it might be some pixel having high value, because see, blue is having a pretty dominant color here. Blue is pretty dominant, right? So that's why it might be causing this high value kind of thing, right? So that's how is for image plot. That is not at all used. Quiver's theme, as I already told, the example is not much required. See here, this is a plotting a vector. How can you do? You can do it using quiver, this quiver option. Okay, this quiver option, we have created a subplot, then we have created this quiver option. Okay, using this quiver, if you pass x position, y position, and the directions, so you know, right, the vectors will have two directions, 1 0 1 -1. This is the direction of the vector, so it will go from 0 to 1 upwards, and this will go from 1 to -1, that is in a downward way. So that's how the vector directions work, and that's how the vector calculations work. That's how you can plot a vector. Okay, you're using quiver plot. So this is a 2D plot. This is a stream plot actually. So stream plot is used for vector calculation, vector algebra, vector physics. I mean, wherever you have a vector involved in physics, electromagnetics, electrical engineering, stream analysis like cyclone analysis, wind trend prediction, like those kind of scenarios, you will have the stream plots into account. Okay, so this is just a bit different from the vector plot. And here also you have the same thing, the stream plot function. Okay, but you won't be, you will use it pretty less. Okay, see here, this is a trend analysis, a wind trend analysis kind of thing. Okay, so that's how this stream plot works. So see, the pie chart is to show you percentage or proportional data. Okay, so this can be this can come handy when you have more than 4 or 5 categories. Then box plot will take up a lot of space, and from the box plots also you will only see the values, right? The counts and the categorical values like that, but you won't see the percentage of the data that is being placed in those each of the categories. So those kind of scenarios pie plot comes into picture. Okay, I will show you the coding example for this pie chart. Okay, but it's not much left for pie chart to be customized. So let's see. So if you see, so now it will be easier for you to understand all these functions. So first what we have done, we have taken a label array of 4 and size array of 4. So that denotes in a data set what is the what are the number of dog, cats, wolves and lions that we have. Okay, so if I show you a quick math, that then it will be easier. So let's say what are the values that we have. We have 50, 45, 60 and 80, right? We have 50, 45, 60, 80. So how it calculates? So 50, 45, 60 and 80. So it comes to 140, it comes to 95, this 2 comes to 275, right? So we have total of 275. Now if you calculate 50 by 275, how much it comes? It comes to 10 by 52. So that is somewhere around 20%, right? If you calculate this, it is somewhere around 20 or 19%, right? 50 is the count of dog. What is the percentage of dog? Percentage of dog is 21.3%, right? So this kind of percentages are calculated and shown over here. Okay, for cat it is 45, so it will be around 90% like that. Okay, so that's what kind of information you can get from this pie chart. Okay, now how do you plot that pie chart? You need to use plt.py function. Within py, if you provide some, and the options I will explain now. So sizes is one variable, labels is another variable. So labels we need to pass it, because otherwise this labels of lion, dog, cat, wolf won't be shown. So and it will be equally, it need to be in the same order as the size array. Okay, otherwise the this labels will be misplaced. Okay, next is auto pct percentage 1.1 f percentage. That means what is the display percentage, what will be the format of it. So we want only one decimal after we want only 1 point after the decimal, right? So that's why we have given 1.1. So that is the number will be whole intact, then after the decimal we want only 1 point. So that's why 1.1. Shadow true means you see there is a shadow effect inside. If you give it as false, I will show you, then you will understand the difference between these two, shadow true and false. So if it's a if it's a 3D plot, I mean if so here the shadow is not really visible, but it should be if you use lighter colors. Okay, lighter colors will have you the shadow visible, so it will have a bulging effect actually. So that's how it will look. So that is not much used, you can leave it. Okay, start angle is 90, means then the angle will be 90-degree angled. Okay, so it will have a equal kind of a shape, so it will have a equal kind of a array actually, I mean sorry, equal kind of a shape of the circle. So that's why start angle equals 90. Explode, as you can see, if you mention 0.1 as an explode, then it will be those slices will be cut out from the array and it will be outside the array. So that's how explode function works. And explode you need to give 1 for each. So where I have mentioned 0.1, those slices, see, they're cut out from the pie chart, right?
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
That's how this pie chart works. Okay, so pie and donut, I will finish it, then I will open for question here. So donut chart is the same thing, just the difference is it shows the area. Instead of showing the percentage, it shows the area. Okay, for that what we do, we create two pie charts and we combine those. Okay, so see here, we create one pie chart here. This pie chart, if I show you one by one, so this is a pie chart, right? We don't have the numbers mentioned, so we haven't mentioned auto PCT, so it haven't shown. We haven't mentioned shadow, so this kind of effect is not there. If you see these two, a difference between these two, you will understand what is the difference of the shadow function, right? So this is a pie chart. Okay, we have created a pie chart using this variable that we have. And okay, this is color white, let me make it black. Black is coming as blue. Why? Okay, black, only one body takes, that's why it's taken blue. Okay, got it. So that's how it will take only one word in the color, so that's why it is taken as black. If I put O is not supported, Y is supported. Okay, so Y for yellow. So you see here we have a yellow kind of a circle. So this circle is to give the blank inner filling. Now if I run this first pie and second pie together, see this effect we want to give, right? So this is a pie chart that is there. So if you remove this second pie chart, what happens? This is the entire chart, correct? This is the entire chart, correct? What is the radius of this? 1.5, right? Now we want to show it as a donut. So what we can do, we can cut out some area, right? So that without saying, if I draw it, it will be easier. So being said that, so let's say this is a bigger circle. Okay, let me change the color. So let's say we have blue here. So this is a bigger circle and we have these three parts. Okay, we have these three parts. Okay, let me change the color again. Let's say I'm taking green. So this part is green. So next I'm changing it. This part is pink. Let's say like that. Okay, and this part is orange. This is filled up. Okay, this is entirely filled up. I am not going to fill it up. So what you can do, you want to show only this much. Let's say only this much you want to show. Oops, sorry. Let me change the pen color. It will be easier for you to understand. I have exhausted all the colors. No. Let me just think. We want to show to the viewer this much of value, this much of portion. So what can we do? We can fill it up with some value. We can fill it up with some color. Let's say we are filling this up with orange. Okay, what will happen? This shade will left upon, right? This outer side circle will be left upon. So that's how you can create a donut chart. It is not an option in it. So let's say if I increase this, you will see the donut chart gets shrinked. Okay, the donut chart will get shrink. That's why we have used white here, and that's how it works. Okay, if you use 1.5, the donut chart will vanish and it will have a slight effect over there, right? If you use 1.3, it will be pretty thin, right? So that's how you can create a donut chart in Matplotlib. Okay, that's how you can create a donut chart in Matplotlib. The pie chart you will create and you will empty its center. That's how you can create it. Okay, so two pie charts combined together will give you a donut chart. Okay, so that's how this works. Okay, so for your ease of understanding, I will leave it as yellow only, so that it's better for you to understand how you create donut chart. There is no donut chart, you are fooling the audience. Okay, so next is area chart. So what you can do, you can use stack plot function, and if you pass two variables, then it will show you the variable the plot covered. So let me show you using a line equation. Okay, oops, sorry, let me copy the line equation that we had earlier. Which one? L. Yeah, so that's how this will work. Okay, that's how this will work. So for this color, if you write black, it won't work, but if you do color, it will work. Yeah, so that's how it works. Okay, so see, now we have, let's not give it green, let's give it maroon, let's give it green. So if you increase the transparency, it will be easier for you to show. Yeah, looks nice. So that's how this stack plot works. So see, this is basically denotes the area covered between a curve. Okay, a curve or a straight line or whatever is it. Okay, so that's how this stack plot works. So stack plot is basically for showing you the area. Okay, the area of the plot covered. Okay, so that is how we have this area plot. So this area plot you might use somewhere, but not much used at all. But this quiver and stream you won't use. Pie donut you will use often. If you have some presentations, you will use this. And without from now on, what I can suggest you, if you are working on some data on Excel and generating some graph on Excel, try to switch to this one, right? Try to switch to this editor like this, like Python. Okay, so just try to switch to Python, and then you will have nice looking charts, nice looking things, and you will learn this Matplotlib library in a vast details. So that will help you. I believe whoever is there, everyone is working on this Excel heavily, so you can try it. Okay, you can try Python for generating those charts also. So that way you will learn it. Okay, you will learn it quite well. So that's how we have.
We are going to learn machine learning using Python, right? So these are like the applications, as I told you, like the product recommendation, the video recommendations, all which comes in Amazon Alexa, Microsoft Siri, all these like are the applications. When we deal with the data, and we also had discussed this when we discussed the Numpy. I told you that we can have the data in the audio format, in the video format, in the images format. So based on the data, we have the different applications, right? So like movie recommendations, as Google traffic prediction, your Google self-driving cars, all these things are possible because of your machine learning. And definition, machine learning is a subset of artificial intelligence which gives a machine the ability to learn without being explicitly programmed. It's like when the machine is learning itself from the previous data, we are not going to program everything, right? Like it is not just working on our instructions, it is working on how the data, what type of data you are feeding into the machine. And data is the key and the learning algorithm. I told you that two things are important. First is your data, because without data it's not possible, and second are the algorithms. And I hope you all know what algorithm is. Algorithm is just like the set of instruction, right, which you give to your machine, that how you are going to learn the data, or what mathematical formula you will follow to learn the data and to get the right predictions. Okay, so machine learning class, as you can see that data cleaning is again a very important part. Data cleaning is basically cleansing or cleaning, you can say, that when you have the unstructured or the dirty data with you, how you are going to clean it. And that usually almost takes 70% time of the data scientist. So as like here, it's just like a meme type that this boy is behaving, Robbie is behaving bad with this girl, so the trainer is saying that I'll send you to the data cleansing class if you don't focus on this. Okay, because data cleansing is like very irritating truly, but just a part of your process. So if you are into a data analytics, right, so you need to perform it. So I told you that machine learning comes under your artificial intelligence, and then just deep learning is just the extension of your machine learning. Okay, so now let's just talk about the types of machine learning. So basically there are three major types, which are your supervised, unsupervised, and reinforcement learning. So let's just talk about the supervised machine learning, that what supervised machine learning is. So see, supervised machine learning is the type of machine learning on which the target variable is available to you. Right now, what do I mean by target variable? So before going into that, let's just talk about a few terminology which you should be aware of. So for that, I'm taking the paint window, and here I'm going to make one data set, and on the basis of that data set, I'm going to explain you what the target variable is, how actually the supervised machine learning algorithm works, and after that like you will get that you will get the understanding that what supervised machine learning is. So let me just create here one data set. Okay, so I'm just creating a random data set which suppose consists of only 3 columns. Okay, so let's just mark the 3 columns. So suppose the first column here I'm taking is the let's say this data set is basically the data set of the certain trainers, right? So trainers means like the people who provide education. So let's say that how much years of experience they have, like their number of years in education. Secondly, either that person provided the corporate training or not. But okay, that either that person provided the corporate training or not. And the third one is like based on these two particular columns, you have the hourly rate of the trainer, that how much does the trainer charge, like the hourly rate of the trainer, right? So this is this data we have. So let's just say that first have 12 years of experience, second have 10, then say again 12, then say 5, then say 6, and then say again like 10, or let's say 15. Okay, so suppose that like few data has been given to you, that yes, this provided the hourly training and a corporate training, and how much does he or she charge. Suppose he or she charge $90 per hour, right? So similarly, this one doesn't have the corporate training, doesn't provided the corporate training, and he or she will charge, suppose, let's say $50, right? Again, no. So let's say that $60, right? So yes, say yes. So say $45. So just randomly I am entering, right? And for 6, say no, and say $30, right? And for like in the machine learning algorithms, again yes. And so now let's just talk about the few terminologies I was saying. So see, I told you that based on the year of experience, right, based on the total number of years or years of experience or education years and corporate training, right, and corporate training, you have to predict the hourly rate. Okay, so hourly rate will become your target variable, because hourly rate is something that you have to predict, right, for the new trainer. So hourly rate is your, there are like terms used as, like you can say this as target variable, right? And this is also known as your dependent variable. Do remember this terminology, right? Because like it's been going used a lot. This is or dependent variable, or you can say this is also known as the response variable, because that is something that you need to predict, and predictive variable as well, because this variable is, I'm going to, so these are something, these three terminologies: target, dependent, and response. Okay, similarly when it comes to your number of years and your corporate, so these are your independent variables. Independent variables means that the variables which are not dependent, these are basically your independent variables. Independent variables are the variables which are not dependent or anything, and they are also known as either your feature set as well, because based on these features you are going to predict your target. So first tell me that, have you understood this terminology, that your number of years and corporate training are your dependent variable or your response variable? So see, now supervised machine learning is a type of machine learning in which you have the target variable available with you. As like this example is the example of your supervised machine learning, because you know, for this is your new data, right? For new data you have to predict. So for your new data you need to predict, but for all of your previous data, have the target variable available with you. So this is the example of your supervised machine learning. So now if someone asks you, you have to calculate that what will be the hourly rate of the new data, right, with the given set of features. That is your target. So wherever, like for the previous data, the target variable is available or it is given to you in the data set, that is something known as the supervised machine learning problem. Okay, so now this is the whole idea about supervised machine learning. Now if someone asks you what is supervised machine learning, so what you will say, the type of data or the type of problem in which we have the target variable available with us, that is known as your supervised machine learning. That types of problems comes under your supervised machine learning. Okay, so see, firstly, what do you have in your supervised machine learning? So see here, suppose I am having data, right? Listen to this, view to this chart carefully. You have data. Data has been divided into two parts, which is your features and your target, right? Features and target, like with each feature you have the target available with you. Then you are going to pass these features and target to one machine learning algorithm, right? So here suppose I am making the ML algorithm. You are going to pass this data to your machine learning algorithm. Now this machine learning algorithm will create a model. Okay, this machine learning algorithm will create a model. Okay, then here you will have the set of new data which only consist of features, right? Because like you need to make the predictions for it, so it only consists of features. Then you are going to pass these features into your machine learning model, and then this machine learning model is going to make the predictions for the new data. So this is the complete understanding of your supervised machine learning. Now let me just move to the GPTs, what is there in it, and check it out. Yeah, so this is the, like you can see, this is a training data. This teacher is training to a robot that this is the apple, and 97% it's the apple. When this is what, so when he asks that what this represents, so the robot will say 97%. Okay, so use cases for supervised machine learning is the ham spam, as like some of the mails are go automatically to your spam folder, so that the ham spam classification, and this is your supervised test, right? So let's just talk about the unsupervised learning a bit here by looking at the, see, so see, as you will see that in unsupervised machine learning, like one of the type of unsupervised machine learning is k-means clustering. So when you have the data like this, as there is no target variable, not the right answer you have with you, so we just find out that which features are similar and we try to combine them. So as you see that all the apples will come combined together by looking at the properties, that something round, red in color, that is your apple. Something in the shape of cylindrical, yellow in color, considered as banana, like round, and orange in color is usually the orange. So we make the clusters, right? This.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
So now let's just come to one another main concept. Okay, so see, as I was telling you that we are talking about the supervised machine learning. Okay, so see, in supervised machine learning, you people know that you have the target variable available with you, right? You have the target variable with you. So see, whenever you have the machine learning problem, always remember this, that your first step is that whenever you'll have the machine learning problem, because whenever we start any project, we usually have the problem statement associated with it, right? So whenever you have the machine learning problem statement, what is the first thing you are going to check? You are going to check either the target variable is present or not, right? Either the target variable is present or absent. This is the first and foremost thing you people will check. Now if suppose that the target variable is present, okay, so then what will be the type of machine learning? If the target variable is present, supervised. After checking this step, in the second step, what all you are going to check is basically that what is the type of the target variable. Now let's just talk about what is the second thing you are going to check, that what is the type of the target variable. Now what do I mean by type, right? So let's just talk about that, what do we mean by type of the target variable. So see, type of the target variable means that either it is continuous, okay, either it is the continuous data, or either it is your categorized data. Okay, now what do I mean by continuous or the categorical data? So see, continuous is something as like any value. Suppose if I say that here you have the target variable is price, right? So see, price can be any value, either it can be 23.5, okay, either it can be 24.2, or either it can be 25, or any value can be there in the price. Or if I say that salary, right, if I say weight of the people, height of the people, so all these things are your continuous, where you can have, suppose if I say in between the range, or like you can have any value exist, like floating values as well. And categorical variables are the variables where you have the classes. Suppose if I say that your in your email classification you have two types of classes, that is spam or ham, fine. And the another example, suppose if I say that you have the when it comes, suppose you need to predict the gender, okay, based on the certain characteristics, there will be two, right, either male or female. Okay, and if I say that suppose you need to check that either someone go out or not, right, suppose go on date, let's say based on Valentine week right. So based on the certain characteristics you need to predict that either that person will go on a date on 14 or not. So again there will be two things, either the person will go on date or either the person will not go on date. Okay, so when you have the classes with you, then it's your categorical data, right? All these come things like height, weight, salary, if I say that the stock price, all these things comes under your continuous variable. Yeah, so now, so what will be your second step, that you will check that either your target variable is continuous or it is categorical. So if your target variable is continuous, so always remember that it is your regression problem, right? So if basically now what is the thing you need to remember, that if the target variable, right, is continuous, if the target variable is continuous, then what is the problem type, or like what type of which of algorithm you'll use basically. So then it is the regression problem. Now what is regression, I'll talk to you about that. So then it will be your regression problem, right? And if your data, like if your target data is categorical, so then it will be your classification problem, right? Then it will be your classification. Then which type of algorithms you are going to use? The classification algorithm. Now there are many classification and few regressions as well, which all we are going to discuss in detail. Fine. So let me first just talk about the regression analysis, that what actually the regression analysis is. So see, the regression analysis is a statistical tool that is very useful in cause and effect measure. Is a statistical tool that is very effective in cause and effect manner, right? So now what do I mean by cause and effect? As like suppose when I say that what will be the effect of temperature on humidity, right? What will be the hydrocarbon level of the water, how it affects the purity when it comes to your distillation process. So something like which where the two things are interrelated to each other. So when we need to find out the cause and effect of one another, that is something known as your linear regression, right? So I have the various PNGs with me. So regression analysis is a statistical technique, as I told you, that is very useful in cause and effect measure. And some of its examples are like effect of temperature on humidity, right? What do you think, what will be the effect of temperature on humidity? If the temperature increases, will the humidity increase or decrease? Increase, right? Process effect of height on weight, right? Height and weight of the persons are usually interrelated to each other. Effect of hydrocarbon level on purity of water during the distillation process. Okay, and other examples is like effect of number of TV ads on number of cars sold, or you can say that a number of ice cream buyers with the effect of temperature. You know, when usually it is too hot, the people are more likely to eat ice creams. In the cold weather there are very few who likes to eat. Fine. So it's like the cause and effect measure. So this is about its simple definition, like theoretical. But when it comes to your mathematics, right, so there is one, like there is the equation. So before actually going into the equation, let me just explain you with this example, that suppose if I take the example that uh, number of cars sold, let's just talk about this example, that number of cars sold on the number of ads. Okay, so suppose that you have two columns in your data set. The first is your number of ads, right, number of ads in TV, number of ads on TV, and second one is the number of cars sold. Okay, number of cars sold. So number of TV ads is basically something given to you, as like suppose when there are two ads, there are one car sold. When three ads, it's again one. When four ads, it's two, right? And when then 10 ads, then there are 13 cars sold. So like this, you have the data set with you, and then in this particular model, what you need to predict, that if some suppose like on one day the number of ads are 15, so what will be the number of cars sold, right? So this is your problem, and by looking at the problem, we just find it out that number of ads will be your independent variable. This will be your independent variable, and number of cars sold, because you need to predict that how many number of cars sold, so then it is your target variable, right? It will be your target variable, independent variable or feature as well. And always remember that in machine learning, the capital X, right, the capital X denotes the independent variables, like set of independent variables or features, set of independent variables or features. Cool. And your y, small y, always represents the target variable, and I told you that there will be only one target variable when it comes to your single data set. Okay, so let me just remove this and open the paint window so that we have the clear picture. Okay, so as I told you that capital X, what does the capital X represent? Your set of features, right? Capital X represents the set of features, and small y represents the set of target variable. Okay, so what does the linear equation do? That in linear equation provide us a set of equation, okay, which describes how y is related to x. Okay, and error term in the regression model. Now what is this error term? That I'll tell you a little late, but as of now what we need to understand, that the linear regression, I mean this regression analysis provides us the equation that describes how y is related to x. Okay, and error term, like what is this error term? I'll tell you in okay, this is what the linear regression equation is described. Okay, so let's just understand it, right? So suppose the equation of the linear regression is y is equals to beta naught, okay, beta naught plus beta 1 x, like, or you can relate this equation with your equation of line as well. I hope you all know the equation of line. What is the equation of line? Y is equals to m x plus c. Okay, so what is your c? C is usually my intercept, right? And what is your m? M will be your slope of the line. Okay, what will be the slope of line? So the same happens in the linear regression equation as well, where your beta naught is basically the intercept. Okay, intercept means like the point from where the line cuts the y-axis. I'll show you. This will be your intercept, and this beta one, you can say this as slope, right? You can name this as slope, or you can also say this as the coefficient of x, right? So what actually happens in the linear regression line, that suppose you have x-axis and y-axis on the graph, fine. On capital X, we always have the, like, this is your x-axis and this will be your y-axis, fine. So here you will have your regression line like this. Suppose this is my simple line, okay, or the regression line. Then this point, this particular point from where it is cutting y-axis is known as the beta naught, okay, or the intercept beta naught, or the C, fine. Yes, yeah, right, Gurvinder. Okay, so now let's just understand this with an example, that how actually does it works, and how do we find a line, how do we draw the line, how actually the predictions happen, okay, what is the formula and everything. So to take the example, let me just create a small data set and take a new file. And I'm not saving it because I have the ones. I'll share that with you. So suppose here I'm taking one small data set, okay, and this data set you consist of the two columns, the same example which I just explained you, number of TV ads and the number of cars sold, okay, and then we'll take the few value of them. So okay, so your first will be the number of cars sold, okay, or you can say number of TV ads, yeah, because number of TV ads is your set of features, number of TV ads, and here you have the number of cars sold. Okay, there are 5 values I'm taking, okay, and just the small value, so that we have the small data for the calculation. Number of TV ads 1, and let's say number of TV ads here 3, and with the corresponding let's say number of cars sold 24, okay, then 2, and then say here 14. So a little bit calculation is required, so please be ready for it. You can like put out your calculators, or you can use tab or phone calculators as well. 17, and then you have here 3 and 27. And oops, let me write it here again, which is your when one there are 14 ads, okay. So as I told you that capital X will be your set of features and small y is your independent variable, right? So now let's see that how we are going to calculate the how we are going to draw the regression line out of it, okay. Okay, so as I told you that to draw a regression line, we have the equation which is y is equals to mx plus c, right? So what all do we have in this equation? We have x with us, right? This refers to x, and we have y with us, this. So what we need to find out? We need to find out the m, and we need to find out the c. Okay, once we have m and c with us, so then we can find out the predicted y, and let's just take that, suppose you need to calculate it like when there are 4 number of TV ads on TV, Okay, what will be, how many cars are sold? Okay, or the 5 TV ads, any value you can have, then how many cars are sold, and y is your dependent variable, right? Fine. So now what do we need to find out? We need to find out m and c. Fine. Where y is your target variable, x is your independent variable. Now just tell me, are you all good with the example? Understood that what we are going to find and everything? Okay, Rahul is good, Sweetie is also fine. Okay, mostly all of you are good. Okay, fine. So see, now to calculate m, fine, the first task is to calculate the m. So to calculate m, we already have the statistical formula with us, which I am going to write. So that formula is summation of, fine, summation of x minus x bar, where x bar is the mean. I told you that we always represent the bar with the mean, into y minus y bar into y minus y bar divided by summation of x minus x bar whole square. Summation of x minus x bar whole square. So this is the formula with us, okay, which is already there to calculate the m. So now we are going to find out the value x minus x bar, y minus y bar, put it in the formula, and then we have the m with us. Okay, so let's just do it together. So what is the first thing we need to find out? X bar and y bar. Okay, so what first thing we need to find out here? X minus x bar, right? So x minus x bar. So what is the value of x bar? And here what we need to find out? And suppose I'm representing with a, okay, and here we have y minus y bar, and let's say I'm representing it with b, then we multiply both of them, x bar into y bar, and then we have x minus x bar whole square. Okay, x minus x bar whole square. Okay, so x bar is 5 and no, x bar is 2, y bar is 19.2 and x bar is 2. 3, 3, 6, 7, 8, 9, 10. 10 divided by 5, okay, 2. So x bar comes out to be 2 and y bar comes out to be 19.2. So here I am writing that y bar comes out to be 19.2. Okay, cool. So now let's just fill the columns. X minus x bar. 1 minus 2 is minus 1. 3 minus 2 is 1. 2 minus 2 is 0. 1 minus 2 is again minus 1. And 3 minus 2 is also 1. And what will be the values? Please tell me, like 14 minus 19.2. Minus 1. Yeah, 5.2. 14 minus 19.2, yes, minus 5.2, right? And then we have 24 minus 19.2, which comes out to be 4.8, right? And 14 minus 19.2, again minus 5.2, 17 minus 19.2, 2.2, and then 27 minus 19.2, right? 27 minus 19.2 is 7.8. Cool. And now I need to multiply them. Okay, as like x minus x bar multiply by y minus y bar. 5.8. 24 minus 19.2. It's 4.8. 17 minus 19 is minus 2.2. Yes, here it should be minus. Okay, so now let's multiply them. 5.2 multiply by 1. Let me change the color and let's take it this one. Is 5.2. Cool. 4.8 multiply by 1. It's again 4.8. It is 0. It is 2.2. And it is 7.8. Right? It is 7.8. Okay. Then x minus x bar whole square 1, 1, 0, 1, 1. And summation means that now we need to sum all of them. So can you please tell me the sum of all of them? So here it is 4. Cool. So what will be the sum of x minus x bar multiplied by minus y bar? 5.2 plus 4.8, 10. Then 2.2, 7.8. So near about 20. It comes out to be 20, right? Yes. So it is 20. So what will be the value of m? M comes out to be 20 divided by 4. And we all know that 4 5s are 20. So the m, the slope for this particular data comes out to be 5. So see now what equation do we have? We have the equation y is equals to, what is the value of m? 5x plus c. Right? 5x plus c. And now what we need to find out? We need to find out the c now. Okay, we need to find out the c. C has been left. So see now how we are going to find out the c. See, always remember that whenever we draw a linear regression line, okay, whenever we draw a linear regression line, it always passes the x, the mean of you have the coordinates like x and y. Okay, the points are there, the data points. So there will be always one coordinate which is the mean of x and the mean of y. I mean, let me show you. Here I'm explaining you that suppose here I'm drawing one regression line. Okay, let's say like this. Suppose this is my x, okay, and this is my y. So for my x, of course, there will be for all the values of x I am having, of course, there will be one mean of x, right? And for all the values of y I am having, there will be one mean of y. So it's always been it is always the case that there will be one data point, okay, in this particular line. I mean, not the data point but the coordinate. It can be data point or it cannot, but there will be always the coordinate which is x bar minus y bar. It means that the linear regression line always passes through the mean of the x and the mean of the y. And by using this principle only, we will find out the value of c. So here we just replace them with the mean. Y bar.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
And x bar. So what is the mean of y bar? 19.2, right, is equals to, what is the mean of x? That is 2 plus 2. So 19.2 minus 10 is equals to c. So what will be the value of c here? I mean, what will be the intercept? It's 9.2. 9.2. Okay, so now the equation of your line is, that is y is equals to, what is the value of m? 5x plus 9.2. Like, this is your linear equation, like equation of the on the basis of this data set. So what is going to happen is that when we have this equation with us, okay, we have the y's with us, which is 14, 24, 14, 17 and 27, and we have x with us as well. Okay, so now what we are going to do, see, y is your actual variable, like target variable being given to you, and now we are going to find out the y hat. Okay, let's understand this clearly. What is this y hat? Y hat will be your predicted y, I mean the y which your model is predicting. Okay, so see, y cap will be your predicted y. Find something, the y which your model is predicting. Okay, I mean, when you have actual variable and then you have the target variable. Yes, Rakesh, I'm going to upload all the images on the link. You have predicted y. Okay, so now let's just find out the predicted y. So see, we already have x with us. Okay, so for first point, the value of x is 1, right? For the first data point, for the first data point, the value of x is 1. So it will be your 5 multiplied by 1 plus 9.2. Am I right? Which is 5 plus 9.2. So what will be the 5.92? It's 14.2. Okay, so the predicted value, I mean, like, if for this particular variable only, sorry, if for this variable only we draw the predicted y, the y which we are predicted from the equation, from the model, the equation of the model we get, it comes out to be 14.2. So, and for the second time x is 3, right? For the second time x is 3. So how we are going to find out the predicted y for it? When x is equals to 3, 5 multiplied by 3 plus 9.2, that is 15 plus 9.2, which comes out to be 24.2. Am I right? Then you have x is equals to 2. So 5 2s are 10 plus 14, 10 plus 9.2. So which comes out to be 19.2. And then you have 5 into 1. So 5 plus 9.2, it's 14.2. Yeah, and when you have 5 3s are 15 plus 9.2, 24.2 again. Cool. Okay, and similarly, when y is equals to 4 for the predicting variable, what will be the value for the predicting variable? 29.2. Okay, so of course 0.2 will not be considered in this, so it comes out to be your 29 only. Okay, so let's say, because we are predicting the discrete variable, so it will be your 29.2 and approximately equals to 29. Okay, now we are going to draw the regression line. Okay, on x-axis and on y-axis. So suppose if your regression line, I mean, what does your y comes out 9.2? Suppose if your regression comes out to be, a regression line comes out to be this. Let's say that this will be your regression line. Okay, and the actual data points, right? So there will be some actual data points and then there will be some predicted data points. So actual data points, what is the coordinate of your first actual data point? 1 comma 14. It means your x-axis should be 14, sorry, 1. This is x, this is y. So here I am predicting the actual data points. Okay, actual data points, what will be your actual data point? 1 comma 14. Cool. 1 comma 14. So your 1 comma 14 will definitely will lie on this line. Suppose this is your x and your y is somewhere 14 here. Let's say this here. Let's say the here x is 1 and you have this point 1 comma 14. You can draw it on a graph. Okay, here we don't have that much clear picture. Then next, and then the next actual is 3 comma 24. Cool. 3 comma 24. So it will be somewhere here. Okay, here I'm drawing the actual point. So suppose these are my actual data points. 3 comma 24, 2 comma 14 again, and then 1 comma 17, and then 3 comma 27. Similarly, I have the predicted data points also. So predicted I'm representing with the blue and dot. Okay, so suppose this is my predicted 1.1 comma 14.2. So 14.2 will be somewhat here because it's 0.2 difference, right?
Just a quick info, guys. Test your knowledge of Python by answering this question. Which of the following is not a keyword in Python language? A. Val. B. Raise. C. Try. D. With. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Similarly, 3 comma 24.2. So you can say somewhere here again above 24.2. It's actual 24. So again 0.2 difference somewhere here. Then 2 comma 19.2. So 2 comma 19.2 will be again at this place maybe. Cool. Then 1 comma 17, like this we have the few predicted points. Cool. So what actually the main thing in the regression, that this distance, okay, this distance, the distance between the regression line and the predicted data points, you know now how to predict, should be as least as possible. Of course, because that is something considered as your errors, because on the linear regression line you'll have your actual data points. Cool. Yes, may not, you have some curves as well, Prashant, but here like we expect that they fall on the data on the line or nearby the line, we can say. So we try to find out the best fit line, which always says that there should be the least distance in between the linear regression line and the predicted data points. Okay, and there is one more term which is error, because I was saying, you know, that in the linear regression equation we have the equation plus error. So what will be your error in the linear regression? It is your actual minus predicted, that is y minus y cap. Y minus y cap. This is your error in the linear regression models. And what do you think, that we should always reduce the error or increase the error? Error should be less, of course, because it is error, right? It should be as less as possible. Yeah, so we need to reduce this term, we need to minimize this function, and that is something also known as your cost function. Although I'll talk about the cost functions in detail, but still this is something your all linear regression is about. Now let me show you some of my previous notebooks, okay, in which it is clearly explained. So the definition, and then we took this data set. Okay, so in the same way we took the data set, we find out the predicted y. See, this is also X number of cars sold, Y number of TV ads. We have the data set, we find out all the thing. To find the best fit line, one of the coordinates of a line should pass through the average or mean of points, as I told you. Therefore, by using this, we will able to find out the small c, right? Once we have the c with us, then we can draw the linear equation line like this. Okay, your blue are your actual data points, red are your predicted ones, and then you need to reduce the distance in between the two. And in linear regression, this error, cool, this error is also known as the residual. Residual also, what does the residual means? Residual also means that it is your error. Okay, and we, as I told you, that we always need to reduce the error, so therefore we need to minimize it. And in order to minimize it, we just do the summation of, because it's for only one. Okay, but suppose if you need to calculate for all of them, so yi minus y cap I means like when your first data point, second data point, third data point, just square this term. Okay, and we need to minimize this. Why we need to minimize this? Because we need to minimize the error. Okay, and this particular function is also known as your cost function of your linear regression, or your least square method. Okay, because you are like y minus y cap whole square is also known as your least square method. And let's just create one more. Yeah, so next we have to discuss is the coefficient of the determination, right? So see, to make a model, okay, now we know the mathematics of the model, but the sklearn library always helps us to do all these mathematics by itself, but we still know how does it works, right? And that we learned. But the things comes in that how do you find that what is the goodness of it? Goodness of it means that suppose you applied a linear regression model on one of your data, and now you want to find out that how much accurate this line is. I mean, what how much, although errors we can find, right? Root mean square error and all, okay, as like with the error function, but still there is one more parameter which will tell you about the goodness of it, that how good your line is. Okay, so to do that, to understand that, we need to understand few more terms, okay, as like sum of squares due to regression, sum of squares of error, and sum of squares in between the sum of squares total. So let's just talk about them. Fine. So suppose here I am having a linear equation line, okay, x-axis and the y-axis. Okay, so here I draw the regression line, let's say. Cool. So I'm just taking the example that this is suppose my regression line. Okay, and I also said you one thing, that your regression line always pass through the best fit line of your regression always pass through the mean of x and the mean of y. Okay, so let's say that this point, I mean, yeah, this point is the mean of y, so let's represent it by y bar. Cool, let's represent it with y bar, and here I'll cut this with this at this point. So where it is cutting the regression line, it is cutting from this point. Let's draw a small one. So this will be your y bar. Okay, and now let's say that you have one data point. Okay, suppose on this equation line you have this data point predicted. Fine, this is your predicted data point. I'm marking it as predicted. Something which you are predicting, okay, data point. And here at this point, let's say that you have the original data point. Okay, at this point of your data you have the original data point, so it will be your original Okay, so see, now there will be the error, okay, which is actual minus predicted. I mean, suppose if this is your actual, cool, and this is your predicted, so there will be your error, this one, I mean this distance. Of course, this distance is the error, as I told you that error will be the actual minus predicted. So suppose if I say, so here it will be your actual, that is your y minus y cap. That is your error one, actual minus predicted. Cool. And this error is known as your SSE. Okay, so there are terms which you need to remember. SSE, always remember, sum of squares of error, and it will be your summation of sum of square of error, SSE. Very simple term, summation of actual, cool, yi minus yi bar whole square. Then after this we have one more error, which is this one. I mean this that let me take it with this. That is this error, and this error is known as your SST. Sorry, this is known as your SSR. That is sum of squares due to regression. Okay, and the formula for this is predicted. See, now this point is what? This point is predicted, right? So predicted, we are saying yi cap, predicting, minus mean, that is yi bar whole square. This is your sum of square due to regression. So let me write down. This is your sum of square due to regression. And how it is defined? Sum of the predicted value and the mean of the dependent value. I also have bar in place of cap. Have I see? It is your predicted yi cap, and for mean it is bar. So predicted minus bar. Okay, and then it comes to your one more type of error, which is your SST. Okay, which is your SST, and SST is your sum of squares total. Okay, sum of squares total, and your SST is SSE plus SSR. So it is the important that in calculating the total error, the SSR also been used. So sum of the squares total. Okay, we have this formula, that is SST is equals to SSE plus SSR. And now next we are going to discuss about the assumptions of linear regression. So I have one blog on the assumptions of the linear regression on Medium. Let me show you. So let's just talk about the assumption. And it is a model that assumes a linear relationship in between the variable x and the single input output variable y. Of course, because it's a linear regression, so its first assumption is only linear distribution, that your data should be linearly distributed. And what do I mean by linearly distributed data? That the data should be in the linear distributed manner. I mean, like something like this. Your data point should be like this. That they can be counted linearly. Now, suppose if I say that your data is something like this, okay, where you cannot draw a line, right? So, of course, this is not your linearly distributed data. So, your data should be linearly distributed. This is the first point about it, right? And now let's just read about it, what has been written. and what is the things that what should be taken care of before applying the linear regression model on any of your data set. So linear distribution, so it is defined as the relationship between two features where change in one feature can easily explain the change in another feature. That is, the relationship between each independent variable and target variable should be linear. Okay, it means that they should be dependent on each other, right? Like on one increases, other decrease, maybe one decrease, other increase. So some kind of relationship should also be there, always be there. And how to check the linear distribution, we can simply plot a scatter plot. We know how to do that, plt dot scatter, right? Understood the first one, linear distribution. There are total 5 assumptions. The first is your linear distribution and the simple one. Cool. The second is your presence of normality. Okay. Now, what do I mean by presence of normality? See that there is the concept of the normal distribution, and the normal distribution is the data that which is something distributed like this. Okay, which is the bell-shaped curve. When your data is like this, it means that your data is normally distributed. Okay, and in statistics, we have one theorem which is known as central limit theorem. Okay, so according to central limit theorem, if the number of attributes, I mean the number of rows you can say in your data is greater than 30, okay, is greater than 30, so then automatically, okay, automatically that data set will follow the normal distribution. So automatically the distribution of data of that data set becomes normal. So this is what something known as the central limit theorem. So here it says that as we know, there are n number of distributions in statistics like uniform, normal, Gaussian, exponential. There are n number of distributions, and if the number of observations is greater than 30, okay, in any variable, if the number of observations, if the number of observations is greater than 30 in any variable, we simply assumes it to be normally distributed, and this theorem is known as the central limit theorem. So it means that your data should be normally distributed, and it will be definitely, of course it will be if there are more than the 30 observations in your data set. Okay, and how to check the presence of normality? To presence of normality, we can always draw the histogram. Okay, below I have an example where in the it's been given as you see. Let me show you. So suppose if this is my data set, right? I'm having the features like TV, radio, and newspaper, and on the basically sales data, that how much advertising dollar spent on TV by a company, how much advertising dollar was spent on radio, and how much on newspaper, and then on the basis of that, how much their sales has been affected, right? So if when it comes to a linear distribution, so we always draw the scatter plot. As you know that TV, radio, and newspaper are the independent variables and sales is your target variable. So just they should follow the linear distribution. Presence of normality, we always draw the histogram. So the histogram should be look like this in between the newspaper and the sales. Okay, so once you go through this article, it will be very much clear to you that what does it mean. So now it's multicollinearity, fine. So that is your third and very important assumption. First, let's just discuss what do we mean by multicollinearity. So see, multicollinearity means that the two independent variables, okay, or two features shouldn't be heavily dependent on one another. I mean, it's like that changing one may not change the other. Okay, so we need to have very little or no multicollinearity in the data. Let me explain you what does it mean. That suppose if I have one column in my data is date of birth, okay, another column in my data is the age. So first let me tell you that what does the multicollinearity means, that two features, okay, should not be dependent on one another, should not be highly dependent, means like strongly dependent on each other, highly dependent, should not be highly dependent. So if suppose if someone's DOB is 12 to 94, okay, then age of birth will be let's say 27, right? So if means these two are representing the one thing. Don't you think that they two are highly dependent on one another? Date of birth and age. Means if you make some changes in DOB, there will be some changes in the age as well, right? So this should not be the case. Two variables shouldn't be highly dependent on each other. There should be only one variable. Either you can drop the DOB or either you can drop the age. So this concept is known as the multicollinearity in the data set. And even this question has also been used in the interviews many times, that what do you mean by multicollinearity? So it's very simple, that two features shouldn't be much dependent on one another. And how you are going to find out the multicollinearity, that is the multicollinearity exist in your data, that is by checking the correlation, by using the Pearson's correlation coefficient or the heat map. As I told you that the correlation values always lies between -1 to 1. Okay, 0 means no correlation, very much close to 1 means highly correlated to each other. So there should be no correlation. So this is your multicollinearity. Yes, in pandas we discussed, right, Prashant? Okay. And then it's your fourth assumption, which is your autocorrelation. So let me explain you the autocorrelation here. So and this is how we draw the heat map. Okay, autocorrelation is that your vector of prediction, okay, shouldn't be dependent on the previous assumption. Okay, so let me just explain you that suppose if you have the sales data. Okay, so autocorrelation say that sale, suppose there are 3 days, 1 2 3. Okay, so sale of one day, okay, I mean like the sale of the second day should not depend on the sale of first day. Similarly, sale of third day should not depend on the sale of second day. So this is something your autocorrelation. That autocorrelation doesn't exist, and it usually happens in the time series kind of data like stock market or something. Okay, so the rare problem which we come, but it is considered as one of the assumption that the vector of prediction, okay, shouldn't be dependent on the previous day prediction. This has all been written here. Sometimes the value of yx plus 1 is dependent on the value of yx, which is again depends on the value of yx minus 1. Mostly stock market or the time series analysis dataset can be counted as an example of autocorrelated data, and we can use line plot or geometrical plot to check its presence. And now the next comes is your homoscedasticity. So homoscedasticity, it means that a homo means similar, okay, and cedasticity means error. It's always good to break the complicated terms into two. So or homo means similar and cedasticity means error. So it can be defined as a property of regression model where the errors are almost similar across all of the input values. Okay, if the errors keeps changing drastically, the result in a funnel shaped scatter plot can break our regression model, and the condition follows heteroscedasticity. It means that the errors should be kind of similar in between the target variable and the independent variable and the dependent variable. If they are not similar, so then you have the kind of example like this. I mean, suppose if you draw the error in between the dependent variable and the independent variable, if the result comes like this, so it should be fine. I mean, there should be like the similar type of errors. But if it is like this funnel shaped, okay, so then this shouldn't be there in your data. So homoscedasticity is something should be present and heteroscedasticity shouldn't be. So now let's just talk about the data set. So see, when you look at this data, so you'll see that there are many features. Fine. So the features are like your longitude, latitude, housing median age, total rooms in a house, total bedrooms in a house, population, households, the median income, okay, the median income of the person who owns the house, the median house value, and the ocean proximity. It means like either it is near ocean or whatever, like near bay or something. So by looking at this data, the problem which has been given to us, that on the basis of these features, that what is the housing median age, it means how much old the house is, how many total rooms are there in the house, how many total bedrooms in the house, how many people can actually live in the house, what will be the median house value. Okay, that is, and all this is in dollars, median house value. So median house value is my target variable over here, and rest of them are the features. Okay, so see, now everything seems to be good, but when it comes to your median income, okay, so here the median income is like $8.32, $7.25, $3.84. So do you think that the people who have like this amount of median income, okay, like can own such houses? Yes or no? I mean, like, if you have such a less amount of median income, so can you own such type of houses? No, but most of the time the answer is no. So therefore, if we look at this data set, so we find out that this median underscore income column is scaled. Okay, now what do I mean by scaled? That I'll tell you a little bit later. Scaled means that we can scale our largest values to a specific range, and for scaling there are many feature scaling parameters available. But as of now, let's say that this your median income is the scaled column in your data set. Okay, and if I talk about the info, housing.info, so you will see that how many total values are there in your data set. There are total 20,640 entries. And how many columns are there? There are total 10 columns. First, you have the data set with you, you will check, you have the problem with you, then you will of course use the info function on the data set, and we'll come out with this. So let's see about the null value. So see, when we check about the isNA.sum, so I just find out that there are no NA values in any of the column, but in total underscore bedrooms, I have 207 null values, right? In total underscore bedroom, I am having the 207 values. So now see, there are total 20,640 rows and 207 null values are there. So now there are many ways to deal with the null values. You know that either you can remove the rows consisting of the null values, either you can drop the entire column as well, right, which consists of null values, and even you can fill your null values as well. So now, before actually deciding that which method we are going to use when we have the null values in our data set, we'll check the correlation. Okay, the correlation means like you know what the correlation means, but the correlation in between the column which is having the null value with the target variable, that either that column is important, it is correlated with the target variable or not. Like if it is highly correlated, so then we should keep it. Like, and even if it is less correlated, so then we can drop it. Why to then waste time in filling the null values if that column is not correlated with your target variable, right? So what we'll check about the correlation first. So how to check for the correlation? What was the formula? House dot correlation, right? So once you use how.corr function, you'll have the correlation with all of your continuous variables. Cool. So now by looking at this data, this is your positive correlation graph.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
This is my negative correlation graph when one increase and other decreases, and this is something like my no correlation graph, like when there is no correlation in between the data and the feature and the target variable. Okay, so here we can find out that strong predictors are median income, total rooms and housing median age. Weak predictors are total bedroom and household. For total bedroom, it's minus 0.007. So like negative and also very weak predictor. And negative predictors are longitude, negative latitude, and the population. Population is not negative, it is 0.004. Okay, so let's remove it. Understood. So now total underscore bedroom is having the very less amount of does not correlated with my target variable. Therefore I just decided to drop the total underscore bedroom from my data set, as it consists of the null values. So what I will do, how to drop, by using dot drop method. Okay, by using dot drop method. See, longitude is negative. It is minus 0.04. Population is negative. I was checking that population is negative. Okay, so what I'm dropping the total underscore bedroom, because I'm thinking that it's a weak predictor, because for total underscore bedroom it's very less, 0.04. Okay, so therefore I'm just deciding to drop it instead of filling with some null values. What I do, I drop it. So how to drop, that you all know. House dot drop, column name axis is equals to 1 for column, and for permanent changes in place is equals to true, and then you have house dot head. So what does it mean? That your total underscore bedroom has been dropped. Okay, so I think we should proceed now. Cool. So I just dropped this column. See, now all seems to be good in my data set, but the problem is with the ocean underscore proximity column. I told you that we cannot pass the text categorical data to the machine learning models, right? What we need to do, we need to convert this ocean underscore proximity, we need to encode it. I mean, convert the text categorical into the numeric categorical, because we cannot pass it directly to our model. So first I need to check, because in the first 5 rows I can only see the near bay. Okay, so first I checked for the value underscore counts function. I told you about the value underscore counts function in the pandas. So there are total like 1H ocean, inland, near ocean, near bay, and island. There are total 5 categories of ocean underscore proximity: 1H ocean, inland, near ocean, near bay, and island. Okay, and now we need to convert this text categorical column into the numeric column, and for that we need to use the label encoding. Okay, so for that we need to use the label encoding, and to use the label encoding we'll take the help of your sklearn library. Okay, how you are going to write, do listen this. From sklearn dot what see, first let me tell you what actually label underscore encoding is. So label underscore encoding is that it will directly, as you'll see that there are total 5 categories. Okay, so what it will do, it will just assign the number 0, 1, 2, 2, 3, and 4. Okay, value underscore all counts always return in the descending order. So in this way, this just encode your text categorical data. I mean, 1H ocean been represented by 0, inland been represented by 1, near ocean now by 2, near bay by 3, and island by 4. Okay, so kind of ordinal values label underscore encoder provide. Okay, as like in one particular descending order. Okay, so now I applied this. So to apply we need to make the use of sklearn library. So from sklearn dot pre-processing I just import the label encoder. Okay, label encoder, and then le, I mean I'm taking one object of it, is equals to label encoder. And label encoder, you can read about it when you press shift plus tab. Once it's been executed, I'll do that. See, encode the target variables, target labels with value between 0 to n number of classes minus 1. Okay, so this is how it works. And after that I want to make the changes in ocean underscore proximity. So house data set, on which column I want to work, ocean underscore proximity is equals to LE, that is your label encoder dot fit underscore transform, and then which data, house data, on which column I want to apply, ocean proximity, and then I have the result like this. For all was nearby, right? So nearby is been encoded to 3. Now just have a look on 8, 12 and 13 and let me know if you have any questions. And either it is working in your system or not. Please write the code and check it out. Yes, kind of same. One hot encoding is different in a way that it provides you the different numbers. I mean, like different columns are there. Suppose 5 columns will get created, right? And 0, 1 will only be there. But in label encoder, it's been like 0 to n minus 1. That is the difference in between one hot and label. Okay. And after that, I just applied the describe technique on it. Describe, provides you the descriptive statistics, mean, median, mode, count, under self-explanatory. Minimum value, rest are the percentiles and interquartile range, right? That's cool. And I just draw the scatter plot in between the median income and median house value. So it comes out to be this, so highly correlated data is there, and also following the linear concept as well.
Linear regression, we do use linear regression to solve a regression problem, right? Where we have the target variable continuous. Now we do have another type of problem statement classification, right? And we can't use linear regression to solve this problem because although our target variable is 1 and 0, it might go well beyond 1 or even below 0 as well, right? And because of which we would be willing to make it could be number, but rather than giving them just 0 and 1s, we could have the output in the form of probabilities. Okay, so that means we could have the probability of the occurrence of the event. For example, we are trying to predict churn or no churn. We could make a prediction saying that, all right, so 0.7 probability we got. So we could keep the probability as is, or we could even turn the probability into a binary value, saying that, right, if it is greater than 0.5, for example, we'll mark them as 1. So over here, 0.7 is greater than 0.5, so it could be marked as 1. So you could say that, all right, so this customer is getting churned. Okay, so classification problems, they are very important category of problems in the analytics world. So where the target variable typically is categorical. So mostly go for the binary classification problem statements where you have 2 categories in your target variable. So the primary objective is over here is to predict the class of the customer, for example, which we call as the class probability, right? Based on whatever values you have in your independent variables. Again, we could have a single independent variable, or we could have multiple independent variables, more than 2 categories as well, which we call as multi-class classification problem. Okay, but yes, typically we have the major business problem statements we try to develop as 2 categories only. Okay, because that makes the decision making simpler, and that's where the most of the problem statements are like. Okay, so let's consider certain scenarios that how it could be. So for example, a bank may like to classify the customers on based on the risk, like low risk or high risk. Now, Babadi, as you mentioned about like more than 2 categories, it could be that they might create 3 categories, like low, medium, high, for example. Okay, so it could be 1 for low, 2 for medium, 3 for high risk. Could be. Okay, but most of the scenarios, they make it 2 categories only. So organization could like to predict the customers who are likely to get churned. Now over here, target variable will take 2 values. 1, if the customer gets churned. 0, do not churn. Health service providers, based on diagnostic tests, would like to classify the patients as positive. There's a presence of that particular disease. That means y is equal to 1, or negative, saying that that's absence of disease. In that case, y is equal to 0. Then you can think of in marketing field, customers who are likely to respond to a particular marketing campaign via emails or phone calls. So over here, y is equal to 1 would be the ones who will respond to the campaign. Y is equal to 0, who will not respond. So HR department of the firm might try to predict whether an applicant would accept the job offer. For example, over here, 2 categories again, accept or do not accept, to 1, 0. Movie production houses would like to predict whether a movie will be hit or not at the box office, for example, again, 1, 0 type of make such kind of probability as a prediction output. So logistic regression over here, as we talk about, it's just an extension of your linear regression model on.
Okay, so we call that logistic regression as a part of generalized linear regression. Okay, so GLM, generalized linear model, where the target variable over here we are considering as the one who is following a binomial distribution. Okay, so and because of which in this scenario, even in R when we talk about, so we call them as the function that we do use is generalized linear model, which the function name is GL. Okay, and we need to explicitly mention over there as we are predicting a classification problem, so we need to mention family is equal to binomial explicitly. Okay, now the question comes over here that how exactly we are saying that, or even in some time we'll just see that the equation that we are talking about in the logistic as a logistic function, which is nothing but a linear regression equation itself, right? So we'll try to derive that particular one as well to understand intuitively that how we could say that is just an extension of our linear regression itself. Okay, all right, so let's start with the grassroots of the understanding of the logistic regression equation. Okay, right, so these are something which we all talk about. All right, so one thing over here important is this logistic regression also falls under parametric approach. So parametric approach, we say whenever the algorithm is taking certain assumptions about the distribution of data, right? So in linear regression, we say that it takes a major assumptions saying that the independent variables and the dependent variable, they have additive and linear relationship, right? So which is one of the major assumption that we are having in linear regression. Now over here in logistic regression, it also follows the linear relationship, but not directly independent and dependent. Rather over here we have the independent variables and the log of odds. Okay, now that takes us to the major question that what exactly this log of odds is. Okay, so let's try to understand about that first. Now, as we talk about this log of odds, it takes us to the very basic form of understanding of what is the exact logistic function looks like. Okay, now this equation of just a linear equation which we have seen earlier. So y is equal to b naught plus b1x. Now the notations you could find very different in different books or blogs or articles anywhere. So over here, for example, it's mentioned as beta naught, beta 1, beta 2, for example, like this. Okay, so it could be, for example, mentioned as alpha, beta, gamma as well, but that does not change the actual meaning of those coefficients, right? So beta naught or b naught over here is nothing but the y-intercept, b1, b2, or beta 1, beta 2, all these are the coefficients of the independent variables, all right, the slopes which we're calling this. So over here, what we're saying that the generalized linear model is that it's a more of like the link function which we're calling. Okay, so you need not to get confused by its name when you're saying logistic regression. It's a classification problem only and not a regression algorithm. Okay, so we use this to estimate any discrete values, the binary values like 0, 1, yes, no kind of data. Okay, and the independent variables could be one or multiple independent variables. There's no restriction on that in any machine learning algorithms, right? And it tries to predict in the end the probability of the occurrence of the event, and that it does by using this logistic function, okay, or we call it logic function. So this is a form of generalized linear model. Okay, so any expression of y by default, if it is linear, is just b naught plus b1x plus b2x2, right? Now we are on top of that. So the link function over here, the g function, which we're saying the g of expression of y. So we're calling this g as a link function, which is mapping this expression of y to our linear equation. Okay, so over here in linear regression, the equation was pretty general, that expression of y is equal to b naught plus b1x1 plus beta 1x1 plus beta 2x2, right? Now on top of that, as now the target variable is just 1 and 0, we are just modifying that one. Okay, and the link function over here for logistic regression is nothing but, so what we call this the sigmoid function. Okay, so which looks like this. Now we'll get into this equation and we'll try to understand how we could derive it from the linear equation itself. Okay, all right, so let's start with the simple thing, the concept of understanding odds. Okay, so when we are saying, let's begin with probability. Okay, so the probabilities range in between 0 and 1, correct? Now let's say the probability of success is 0.8. So let me just type p is equal to 0.8. Okay. Now what would be the probability of failure? So what would be the q over here? Absolutely. So q would be just nothing but 1 minus 0.8, right? So which is nothing but 0.2. Now odds are calculated from the probabilities. Okay, and their ranges could be anything between 0 and infinite. So we are defining odds as the ratio of probability of success and the probability of failure. So typically whenever we're saying odds, we by default we mean odds of success only, which is nothing but p divided by q, which is nothing but p divided by 1 minus p. Okay, and in this case that is 0.8 divided by 0.2, which is equal to 4. Okay, that means odds of success are 4 to 1. And if you say odds of failure, okay, so which is nothing but q by p. Okay, so that means probability of failure divided by probability of success. That is in this case 0.2 divided by 0.8. That is 0.25. All right, so now let's take another example. So for example, there's one data set where saying that 7 out of 10 male students are admitted to a B school, okay, and 10 females are admitted. Okay, so out of 10, let's say there are total 10 females, and out of 10, 3 females got admitted. Now, what is the probability of admission for a male student? That is, for a male student, it would be p is equal to 7 by 10, right? So 7 out of 10 male students were getting selected. So in this case, that is p is equal to 0.7 and q would be 0.3, right? So it's like if you're male, the probability of being admitted to that B school is 0.7, and the probability of not being admitted is 0.3. Now, same thing if it's for female, the same probabilities for female would be, the probability of success would be 3 by 10, that is 0.3. And so I could just mention for female, it would be p is equal to 0.3 and q would be 0.7, right? Now, if your female is just the opposite, in this case, the probability of being admitted is 0.3 and the probability of not being admitted is 0.7. Now, if we can use the probabilities to calculate the odds of the admission for both males and females, right? So it would be that the odds of male would be 0.7 divided by 0.3. So that would be, so for male, it would be around 2.33, right? Or 34 information. Odds is equal to 2.33 for male, okay? And when we talk about the odds of female, it would be 0.3 divided by 0.7, right? So what will be the value for that? So 0.425. So around 0.42. Yeah, right. So it's like probably the odds, as you mentioned, like it's not even the probability of success to the probability of failure that we talked about over here, right? So for odds for male, we got as 2.33 and odds for female as 0.42, right? And the odds ratio would be nothing but, in this case, 2.33 divided by 0.42. Okay. So when we are saying odds ratio, so in this case, OR would be nothing but over here 2.33 divided by 0.42. So it should be around 5 point, approximately around 5.4. Right. So what you could say from this is, for a male, the odds of being admitted are 5.4 times as large as the odds for a female being admitted. Okay, over here we are talking about the odds ratio for the admission, right? So it will be 2.33 in this case, 2.33 divided by 0.42, that is for odds for male divided by the odds for female. Okay, so the interpretation would be like that. So for a male, the odds of being admitted is 5.4 times as large as the odds for male being admitted. So if you just do opposite around, the interpretation also would mean the other way around. So it would be like the odds of being admitted for female is how much as large or as small as low as for the odds for male being. Okay, so there's a generic term, even the English term that has this particular meaning. Okay, all right, cool. So is this clear to everyone? All right, good. So if you see the relationship, so it typically goes, if you try to see the relationship between the odds and the probability, it goes from 0 till the infinity. But if you just take the opposite way around, okay, so you take the log of odds. Okay, so log of odds means log of p by 1 minus p, right? So which we call as the log rate of p. And with respect to the probability, it takes this particular equation, this curve. But if you just try to rotate this, you try to keep the y-axis as probability where you're trying to predict the probability of the occurrence of the event. So y-axis would be always ranging between 0 to 1, and the equation becomes something, it might go from anywhere from infinity till the range of 1 only. So the output would be over here, always would be within the range of 0 to 1. Okay, and this equation, it was z divided by 1 plus equals 0. So this equation is something which we're calling it as the log of odds. Okay, now this is just graphically that we try to understand over here, but let's try to deep dive to understand intuitively that how exactly when we are seeing this, that the log of odds is nothing but our linear equation. So del B transpose x is nothing but your b naught plus b1 x1 equation that we got. Okay, so as you could see over here, it's also mentioned as the logit of p, the log of odds. It's acting as a link function between the logistic regression and the linear regression, and that's why it's called as like the link function. Okay, but how we could derive this? All right, so we would be more interested to understand this theoretically, for example, as a part of derivation, to understand that how we take this linear equation and say that that is nothing but our linear equation itself. Okay, all right, so let me do one thing. So I'll just use another notepad or Google Sheets. So let me use Notebook++. All right, so if you see, when we talk about the any classification problem, now in this case we have the target variable as probability, right? So we are just only concerned about the probability of the outcome of our target variable, which is 1, 0. Okay, and we could establish that using just two things. That is the probability of success and the probability of failure, and they should meet certain criteria, right? So the simple criteria, if you think of that, the probability should be always greater than equal to 0, right? So that's a based on property that we know about. And secondly, that should be again always less than equal to 1, right? All we just want to do is, let's say if you have an equation which could satisfy these two conditions, it could be good for us to get into the code of our logistic regression. Okay, so we have the equation, for example, we take y is equal to b naught plus b1x that we had, right? Now if you just consider the probability as b naught plus b1x, and all you just want to do is make this linear equation a positive value, right? You take the exponential form of this linear equation, and that just makes you sure that the output of that will always be a positive number, right? So for any value of slope and the dependent variable, the exponent of the equation will never be negative. So we could just take the exponential form of this linear equation, and let me just call it as equation 1. Okay, now to make this probability value now less than 1, we should divide this value p by a number which is greater than p itself, right? So if you just divide this value by just this plus 1, so it would be always then less than equal to 1, right? So I'm just naming it as my equation 2. Now if I just use these two particular equation, okay, so it just made me one thing clear, that e to power b naught plus b1x divided by 1 plus e to power b naught plus b1x. So just let me just rewrite this equation as p is equal to, in the simple way, e to power y divided by e to power y plus 1. Okay, so whether call it is y plus 1 or z, it's all fine. Okay, now over here, this is something which we are calling this equation as the logit function. Okay, so this is nothing but our which we're calling it as or even the logistic function as well. So the probability of the occurrence of the event, the p of y is equal to 1, is e to power y divided by e to power y plus 1. Okay, where y is nothing but, we are saying b naught plus b1x, right? Now let me just now then name this particular, so this equation as 3. Okay, so this is my probability of success, correct? So typically whenever we are measuring p, so this is like the probability of success only that we are referring, the probability of the occurrence of that event. Now what will be the q in that case? Q is nothing but 1 minus p, correct? So if you like to just write this equation over here, 1 minus this particular equation, correct, which is your p, and this is your probability of failure, and let me just name it as equation 4. So what will be the odds? That is nothing but probability of success divided by probability of failure, which is nothing but 3 divided by 4, right? So equation 3 divided by equation 4. So e to the y divided by e to the y plus 1 divided by e to the y plus 1 minus e to the y. So it will be just 1 by 1 e to the y plus 1, right? And if you just divide this, you would be having this only leftover term e to the y, correct? So rest all would be getting cancelled out. So which is nothing but p divided by 1 minus p is equal to e to the y, correct? And now if you take just log on both sides, so that means you're saying log of p by 1 minus p, and in this over here on the right hand side, if you take log of e to the y, is nothing but y. So you get the equation over here. If you see log of p by 1 minus p is nothing but the link function that we're saying, right? So the logarithmic outcome transformation that we're doing on the outcome variable, it just allowed us to model a nonlinear association in a linear way, right? So if you just substitute this y value, which is nothing but b naught plus b1x, correct? So this is the equation which we are saying as, if you see, which we just try to derive, which we are talking a few minutes back as the link function. The log of odds is nothing but our linear equation itself. Okay, so you see that we have this equation when we are saying the probability of success e to the y divided by e to the y plus 1. So why we just try to keep it in the shorter way of saying b naught plus b1x, which we just try to derive this particular convention when we are saying log of odds is nothing but our linear equation itself. Okay, so you would see that the typically the probability would never go below 0 or above 1 in this case. All right, so another way is of understanding this. If you look into this equation, let's take this as the first equation. It were so for simplicity, I'll just call it as a to the power y divided by 2 y plus 1. Okay, now as a linear algebra wise, also if you see, if you just take denominator, so this p is equal to e to the y plus 2 y plus 1. If it do some cross multiplication, e to the y plus 1 coming to your left hand side, p multiplied by e to the y plus 1 is equal to e to the y. Do the multiplication over here. And the third step, if you see, we are just trying to get all the exponential term on our, so you're mentioning p is equal to e to the y minus, so we are getting this p e to the y in our right hand side, so it will be minus over here, so minus p e to the y. E to the y, we could take it as a common, left out with 1 minus p. And this is the product term, and we have the p term over here as well. So let's just get 1 minus t in our LHS. So as it is a product term, get this in LHS, so it would be coming in the form of division. So p by 1 minus p, we are left out with e to the y over here in the RHS. And now if you just take the log on both sides, again, it would be log of odds is equal to our linear equation. So two different ways that we have seen, and coming into the same conclusion of the log of odds is equal to our linear equation. Okay, all right, so if we see what we're trying to intuitively, if you try to understand over here, so let's say that you have this scenario saying that you would like to classify a person with, so you like to predict, let's consider that our churn problem statement itself. Okay, so someone would be getting churned or not, and that you're trying to find using a column internet service. Okay, so or even let's say monthly charges. Let's consider monthly charges column only, and you're trying to predict whether based on monthly charges you'll be getting churned or not. So the equation is nothing but the probability of a customer getting churned is equal to e to the power b naught plus b1 monthly charges divided by 1 plus e to the power b naught plus b1 monthly charges. Okay. So that's how this velocity function would look like in that case. So you could just think of it as y-axis, probability of the customer getting churned, and the x-axis monthly charges, and it would be a S-curve, which we are calling as, which is nothing but a sigmoid function. Okay, so this is something which we just talked about. The log of odds is equal to our b naught plus b1x. Okay, all right. So now over here, coming to the point that where in linear regression we use the least square method, right? So we used the method of minimizing the sum of squared errors, right? So yi minus y hat whole square, right? So summation of that. So for every data point, we calculate the error squared and took the summation of that, and that's the equation which we wanted to minimize, right? Which is our cost function. This cost function is nothing but what we call is the error function, right? And we try to minimize that to get the best values so that we could have a best line of fit, right? So over here also in this case, if you look into this S curve that we're talking about, we could have n number of S-curve as well, right? Based on different values of B0, B1, B2. So how do you find the best S-curve as well in this case? And over here in logistic regression, we use this maximum likelihood estimation. Okay, so the likelihood equation is this one, which is originally a product term. Okay, and we take the log of likelihood as the method. Now, before just talking about log of likelihood, let me talk about this maximum likelihood estimation formula itself. Okay, so intuitively we can interpret the connection between the two methods by understanding their objectives. Now, for least square parameter estimation, we want to find the line that minimizes the total square distance, right, between the actual data points and the regression line. On the other hand, over here in the maximum likelihood estimation, we want to maximize the total probability of the data. Okay, so the beta values, the the coefficients that we have between B1, B2 of the logistic regression algorithm, they are estimated from our training data, right? Using this maximum likelihood estimation. So, and this maximum likelihood estimation is just a common learning algorithm as well, which is used by other machine learning algorithm also, although it does make assumption about the data set as well. So over here, the best coefficients typically would result in a model that would predict a value very close to 1 for the original y is equal to 1. Okay, so if it is the target variable is 1, so it will try to make the values, the predictions, very close to 1 for in terms of probabilities. And for the 0 plus, it will try to predict the probabilities very close to 0. Okay, so the intuition for maximum likelihood for the logistic regression is that it's nothing but again a search procedure which tries to find out the values for their coefficients that would minimize the error in the probabilities. Okay, so the predicted by the model to those that we have in the data. So the probability of 1 if the data is, that means the y is equal to 1, and for closer to 0 if the y is equal to 0. Okay, so this log likelihood equation, this expression for the total probability is actually quite painful to differentiate, right? So it's almost gets simplified by just taking the log of the equation, and that is considered as fine in mathematics because the natural log is monotonically increasing function, right? That means over here you could say that if the value on x-axis increases, the value on the y-axis also increases, and that's important consideration also because it just ensures that the maximum value of the log of the probability occurs at the very same point as the original probability function. So we can just work with simpler log likelihood equation instead of the original likelihood. So this is just the log of this particular equation, which just convert the multiplied term into the summation, right? So summation, as you just mentioned, it just turned into the summation that we're trying to do. So get the equation in the positive term, and just the way we have tried to find the best values for B0 and B1. So we try to do partial derivative of the equation with respect to the unknown terms, that is B0 and B1, equate them to the 0, and then get the best values for the coefficients, right? Exactly. So that's the same thing that we do over here, just the way we have done in our that happens in our linear regression best values finding as well. So now that's about what we talked so far is about the underlying mathematics of the logistic regression. Now the very next interesting part that comes is how exactly we would be understanding the performance of the model. Okay, because in linear regression, if you recall, we talked about a couple of metrics, right? So before moving to the R programming, so we'll try to take some more time in understanding this concept of the evaluation metrics, and this is very important concept because this is not very specific to only linear regression. I mean only logistic regression for classification, because logistic regression is just one of the algorithm of classification, right? But we have we could use other algorithms as well to solve any classification, like we could use Deviation tree or random forest to solve the classification. So the evaluation metric that we use the same, right? So for any classification algorithms that we're using. So, and this one is a little bit, I would say, a little bit more complicated than the ones which we have seen for regression problems. Okay, so if you say in linear regression, so the output of any classification problem would be just 0 and 1, right? So the target values over here is just 1, it could be 0. But when you're fitting a straight line equation, as we talked that it could go above 1, it could go below 0 as well, right? And you can't keep in those scenarios any static threshold value as well to classify them as ones or zeros. Now, as we are taking this straight line equation only and squashing it between this range of 0 to 1, so the logistic regression is nothing but that only. So it's squashing the straight line equation within this range of 0 to 1, right? Eventually, which is nothing but finding out the probabilities for us. Now, we could take the action based on just looking into the probability, or to simplify for the business stakeholders or for decision making, we could provide a particular threshold value, right? So, and the setting the threshold value is very much data or the business driven. Okay, so it's typically tempting that we keep the threshold as 0.5. Okay, or so for example, a loss regression model, it returns 0.95 for a particular customer, saying that, all right, so this customer is having the probability of 0.95 getting churn. Okay, on the other hand, there could be another prediction for a customer saying that 0.05 probability of getting churn. So that means 0.05, you would be definitely considering that, all right, so he won't be getting churn, and on the other hand, you would be saying that 0.95, she would be getting churn, right? So either you keep as is as a kind of probability itself, or what you could do is you put a particular threshold value, right? So you define a classification threshold, or we call it as decision threshold as well, where you could set the value as, let's say, 0.5. Okay, so typically if the data is balanced data you have, okay, so balance means the target variable is distributed almost equally, that means 50-50%. Even typically you won't have exact 50%, even if it is 60-40, 55-45, it's more of like the balanced data itself. And you can keep threshold as less as 0.5, anything probability greater than 0.5. Over here, for example, you keep a threshold of 0.5. You say that all these values that's getting over here, we are marking them as zeros. Anything above 0.5, we are marking them as ones. Okay, so over here, somewhere if you say that regression is just a straight line and which can't be leveraged to solve a classification problem, and logistic regression has been motivated from the linear regression equation itself, where we are taking the linear equation, squashing it within the range of 0 to 1 using as a kind of sigmoid function. Okay, so I hope somewhere it's clear now. Cool. All right, so cool. So let's have a quick question on the evaluation metric on the linear regression. So could you all just name few of those? So what all metrics that you could use to identify the or understand the performance of your linear regression model? So let's keep it general. Just talk about as a regression problem. What are evaluation metric that we could use to understand how well it's performed? So our RMSE, somewhere as you mentioned about, that's one metric. Okay, so Nidhi mentioned about MAE. This is SSE is used as a cost function for the linear regression to find the best values for your line of fit. Okay, but it's not an evaluation metric that we use to understand the performance of the model. For example, we could go ahead to it MAE, mean squared error, or let's say RMSE. Okay, so RMSE or MAE is the typical the popular ones. So in mean absolute error, when you're talking about MAE, so you're giving equal weightage to all the errors in your data, right? And that is pretty cool for good intuitive understanding of the errors in your model. And whenever, if you think any large errors are quite undesirable in the final model, in those cases, the business might be more interested in RMSE rather than MAE. Okay, so these are the classic evaluation metrics which are used the most often in any regression problem statements. Yep, so adjusted R-square is more of linear regression specific, which tells us what's the percentage of variation in my target variable explained by the model, right? And it penalizes you for adding any relevant features. So in R-square, even if you add any relevant or irrelevant features, irrespective of that, it will keep on increasing, right? Which will give us a wrong interpretation of the meaning of the R-square itself. So adjusted R-square takes care of that one by penalizing you for addition of any irrelevant features. So it's always a good practice that we look for adjusted R-square rather than looking into the R-squared value. Right. So, and we'll look into in R, you could use the model metrics package, or even you have something called as metrics package as well, And the same function you could use like MEE or RMSE or MSE, which are all in lower cases, actual comma predicted to get the values. Or you could write the equation as well from yourself. But yeah, so it's a very simple function that you could directly use from the package itself. All right, so now coming to the classification problem, right? In classification, your target variable has two categories over here. So Y actual that we're talking about, you could have 1 or you could have 0, right? And then you're making some prediction, which could be also 1 or 0, right? So can you think of like what all kind of combinations that we could have in our predicted results? So you have two columns, you have actual, you have predicted, let's say, okay, and you would be having the values like in actuals 1 or 0, or in output also the predicted also 1 or 0. So what are combinations that you can think of? So I'm just talking about, let me just give an example. So what I'm talking about, for example, one combination is that you predicted 1 and actually also it's 1. Okay, so it's actual predicted combination that I'm talking about. So that's a like 1-1 scenario. Okay, so you can just think of it as all combination you could have in terms of ACT or predicted. So can you just mention something like this, as we just talked about the actual is 1 and predicted is also 1. So like this, what all different combination that you could have, right? So you can have 4 different scenarios, correct? All right, so 4 different scenarios that we could have when we make any prediction for classification problem, right? So let's consider that the target variables that we're trying to predict is 1 0, right? So over here good means 1, bad means 0. Okay, over here if you see there are notations for the columns and something for rows. So for columns, if you see it's mentioned as predicted. For rows over here it has been mentioned as actual. So it's a like actual 1 0 is a predicted 1 0. So the first column, if you see, okay, so that is B and D together. Okay, so the first column it's mentioned as good, right? That means these are predicted 1. Okay, and then over here the second column, let's see, it's mentioned as predicted bad. Okay, so which is nothing but predicted 0. So column 1, so let me just type that in the chat box. So column 1 is predicted 1. So column 2 over here is predicted 0. Cool enough? Now over here, if you see row wise, okay, so these are mentioned as actual. So that means what actually happened, right? So we are saying the row 1, okay, so if you see it's mentioned as good, right? So that means these are actual 1, okay, and row 2 is then but actual 0. So so far so good. All right, so I'll consider there's no questions. Cool. So now let's look over here. Now when we are saying predicted 1, so now let's talk about the row column 1 only. Okay, so where we are saying these are predicted 1. Now when we are saying we predicted 1, the actual could be anything, right? So actual could be 1 or it could be 0 as well, correct? So when we have predicted 1 and it turned out to be actually also it was 1, okay, so we are calling it as true positive. So if you see column 1, it's mentioned as positive positive. That means these are predicted as 1s. This is how you could remember this jargons. Okay, so positive positive, when you see, it means they have been predicted as 1. Okay, now when we predicted correctly 1, okay, so that means we predicted 1 and actually also it was 1, which is, you see in the blue color, true positive, it has been mentioned. True we are mentioning because it's a correct prediction that we did. Okay, so we correctly predicted that it would be 1. So very first one that you see, true positive, that we can, I'm writing as TP, which is like predicted 1 and actually also it was 1. Cool enough? Next, it could be the scenario that we predicted 1, but it turned out to be an incorrect prediction. That means it turned out to be actually it was 0. So we predicted positive, but actually it's a incorrect prediction. So it's a false positive. So predicted 1, but it's incorrect prediction. So it is a false return. Okay. So this is like we predicted 1, but actually it was 0. Okay. So next over here, let's move on to column 2. Okay. Now column 2 is all predicted as zeros, right? So you can see that they are named as negative negative. That means they're predicted as zeros. Okay. Now again, when we are predicting 0, it actually it could be 1 or 0, correct? So the first one, if you see, it's mentioned as false negative, right? That means we predicted 0, but actually it was 1. Okay, so we are calling it as false negative. So again, false is mentioned because it's an incorrect prediction, right? So false negative means we predicted 0, but actually it was 1. Okay, and it could be also the scenario that we predicted 0 and actually also it was 0. So this is like correct prediction, right? So, and that's why it's mentioned as true negative, right? So it's a right prediction that we do. So now can you tell me that among all these 4 scenarios, which are the incorrect predictions we made? All right, so now let's start with understanding about the evolution metric. Okay, so we have a couple of evolution metrics for classification problems. All right, so the first one we'll talk about the accuracy. Okay, so accuracy is one metric for evaluating our classification models. So you could define accuracy as the fraction of your predictions that our model got it right. So that means it's nothing but the number of correct predictions divided by total number of predictions. Now the denominator is pretty simple, total number of predictions, that means all true positive, true negative, false positive, false negative all together. And what would be the numerator? So numerator, we are saying the correct prediction. So among these, which are the correct predictions? Yep, so absolutely. So that's a true positive and true negative. Okay, cool. So accuracy is nothing but true positive plus true negative divided by all the scenarios. Okay, so true positive plus true negative plus false positive plus false negative. Okay, so that is our accuracy metric. Over here we have a particular result of a model. Okay, now this is a data set of model prediction output. So for example, you have 100 tumor examples, out of which 91 are benign and 9 are malignant. Okay, so these are the actual information, like 91 benign and 9 malignant cases. Okay, so these are actual 1, actual 0, predicted 1, predicted 0. So over here, true positive, that means actually it was malignant and your model has also predicted as malignant. That is one case you have. Your model predicted malignant, but actually it was benign. That is one case you have. You predicted it's a benign, but actually it was malignant. There were 8 cases, and you predicted it's a benign and actually also it was benign. It's 90. Okay, so if you say it's 90 plus 8 plus 1 plus 1, you have total 100 cases. Out of 100 tumor examples, 91 are benign cases, right? That means out of 91 benign cases, 90 we predicted correctly, right? So over here, that is, if you see this 91 benign cases, 90 we predicted correctly. So for that, we have other metrics. Moving on to next, this is something at the very beginning we just talked about, right? The column 1 is predicted 1, column 2 is predicted 0. It's named over here, right? So predicted, and these are actual. Column 1, we are saying this. So which are predicted ones, right? When we're talking about actuals, we'll talk about the rows. When we're talking about the predicteds, we're talking about the columns. Column 1 is for predicted 1, column 2 is for predicted 0. Row 1 is for actual 1, row 2 is for actual 0. That's the first thing that you should be pretty much confident about. You could just look into this confusion matrix again, take some time and get comfortable with this. Okay, so I just wanted to know that among all of this, which one we predicted as 1, which is the column 1. So precision is another evaluation metric which tries to answer that what proportion of our predicted ones was actually correct. So which one is actually correct among the predicted ones? Right, so true positive, right? So this is the right prediction that we do. So precision says true positive divided by true positive plus false positive. Okay, so if your model produces no false positive, okay, that means 0 false positive, in that case your precision would be 1. For the business problems where the false positive is important, they would like to reduce the false positives. In that case, they will going for this precision metric, right? So actual 1 will be true positive and false negative, right? So D and C over here. So recall tries to answer the question that what proportion of actual positives was correctly identified. Okay, that means true positive divided by true positive plus false negative. Okay, so let me put that over here. So true positive divided by true positive plus false negative. Okay, so well, so we're calling the ROC curve, and AUC is the area under this ROC curve. Okay, so it's one of the very important evaluation metric for checking any classification model's performance. And the reason being over here, this is threshold invariant. Why this is quite popular? Irrespective, although we check any of these metrics like be it accuracy or precision or recall, but ROC, the AUC value is something which we typically check for any time for any classification problem. Okay, because this is more of like threshold limit. For every threshold we check for this particular metric. Okay, so now what is this ROC curve is that it's a performance measurement for classification problems at various threshold values. Okay, so it's a probability curve. This ROC we are calling as probability curve, and AUC we are representing it as the degree of separability. Okay, so it tells us how much the model is capable of distinguishing between the two classes. So higher the AUC, better the model is predicting 0 classes as 0 and the 1 classes as 1. Okay, so that means you could say higher the AUC, better the model is at distinguishing the customers who are likely to get churn and who won't be. Okay, so ROC curve is plotted between true positive rate against the false positive rate. Okay, so TPR is on the y-axis and the FPR is on the x-axis. Now the question is, what is TPR and what is FPR, right? So TPR is nothing but true positive rate, which is nothing but another name for your recall. Okay, or sometimes it's also called as sensitivity. So these are even just nothing but few more jargons. Okay, so TPR, recall, sensitivity, these are just various names for the same concept. So that is true positive divided by true positive plus your false negative. So which we just talked about the recall. And the false positive rate is nothing but, let me just mention FPR formula, false positive divided by true negative plus false positive. If you just look into your curve over here, if you see what we're saying, that so over here true negative plus false positive, which is nothing but your actual zeros, right? Among the actual zeros, how many you predicted incorrectly? That is false positive divided by true negative plus false positive. So we are calling it as FPR, the false positive rate. And the true positive rate is nothing but true positive plus false negative. Among the actual ones, how many we predicted correctly? So this is like D divided by D plus C, which is recall, and FPR, the false positive rate, is nothing but B divided by B plus C. Okay, so this is something which the curve is all about. Okay, so at various threshold values, we're finding this TPR versus FPR. So let's try to understand over here. So if you get the best value, like you're predicting all ones as ones and zeros as zeros, so you'll get AUC of 1. That means the curve would be like perpendicular, like this, straight alongside y-axis and parallel to x-axis. So this is like the whole area that will be getting AUC of 1, which is unlikely that you'd have. It's like 100% accuracy, no error. Now, for example, you get AUC of 0.7. So typically, I would say in real-time problem statement, AUC above 0.7 is considered very good for any production deployment purpose. Okay, so that means your model has 70% chance that the model will be able to distinguish between the two class, okay, 1 and 0s. And if you have a diagonal line, that is, you would say that in that case, AUC is equal to 0.5. Now, that is like the worst scenario that you could have. That means the model has no discrimination capacity, basically. That means to distinguish between your 1 and 0 class, okay? So that's the worst scenario typically that you have, or you won't be having all those 0.5. It's typically between the 0.5 to 1 that you'll be getting the values. But closer it's to 1, better the model is. And even you won't get anytime 0 also. So 0 is like just on top of x-axis the line and parallel to y-axis over here. So which is like your model is reciprocating the class. The model is predicting 0 as 1, 1 as 0. So which is also unlikely to happen anytime. So 1, 0.5 or 0 is unlikely to happen. Typically, you'd be getting all the values between 0.5 to 1 only. But yeah, the closer it's to 1, better the model is. Okay. Yep. So you can keep a note of this. So of this formula for the FPR. Okay. So the false positive rate. TPR is nothing but your recall, which we just talked about, and FPR is the false positive divided by the actual zeros that you have. All right, so these are the couple of evaluation metrics that we check for any classification problem. So ROC, this AUC value which we get from the ROC curve is the generic one, but among the others, be it accuracy, precision, or recall, we just typically check any one of. And that is something in R, you can get the confusion matrix from this from a particular package that we'll look into, and then from the confusion matrix itself, you can calculate using the formula that we have all discussed. Okay, for any of this accuracy, precision, or recall. So Babadita, yes, definitely. So that's a point, right? So that's why we are calculating AUC. So the farther it's from the false positive rate, the line, better it is. Closer it's to your y-axis, better it is. So eventually, you would like to you should have the curve closer to your true positive rate and farther away from your false positive rate. And that's how you would be having, in that case, high AUC value. This is the area under curve that we're talking about. All right, so cool. So let's try to look in next in our programming how we'll be doing this. Okay, so the first thing that you'd be willing to do is first split the data into train and test, right? Now, before doing that, over here, as the target variable is that we're trying to predict is churn. Okay, so it is not in the form of 1 and 0s. Okay, so what we'll be doing is as the probabilities we'll be getting as an output, and we'll be converting them to 1 and 0. So for the understanding of the confusion matrix as well, it's always good that you have the target variable as 1 and 0 zone. Okay. Over here, the target variable churn that we have, if you see the unique of customer churn $churn, so that is no and yes, and that is something we would like to convert it to 1 and 0. Okay. So the cool way is you could use, for example, a new column name, churn underscore new we are creating, let's say. You could create like this, or you could use the mutate function as well. Okay. You could just use if else function if customer churn $churn, if it is yes. Okay. So you'll mark it as 1, otherwise 0, right? And now if you check by default, when you're creating this new column, customer churn $churn new, so by default, it should be numeric, right? So we created 1, 0, but it's a categorical target variable that we're trying to predict, right? 1 is one category, 0 is another category. So we should convert this to factor. And this is the important step, that to make sure that for any classification problem, your target variable should be of factor type. Okay. So we would be just converting this data type from numeric to factor using as.factor function. So this is the first thing that we all would be doing. Okay. So just create this and we'll check the number of observations we have under each category. So which function that we could use to check the number of observations under each category, 1 and 0? So how many got churn and how many didn't get churn? Right. So table function we could use, right? So table customer churn $churn new, right? So that's 0 and 1. How about if you'd like to see it as in the form of relative frequency? So that means you would like to see what percentage of customer got churn and what percent of customer didn't get churn. You all recall? So talked about this, I believe, in the data visualization session. Right. So David, that's right. So prop.table, or even you could use like table and then you divide by the length of the column, like 7,040. That also could. Or you could use directly the prop.table, table customer churn $churn new. And there's something, if you just multiply by that 100, you get in percentage, right? Exactly. So we have like 73.46 who got churn and 26.5 who didn't get churn, right? Let's say that, let's take this table that we have created in the form of data frame. Okay. So let's create data.frame. Let's store this into df. Now, if you see df, this is by default, the column names will be created as var1 and frag. How can you change the column names? You could just mention column names of df. Both the column names, let's say, would like to change. So you can just mention names as churn, comma, the frequency. Let me keep it. Or frag is also fine. It works. I could try frequency. So if you see df, so we just rename the columns churn and frequency. Okay. And we might be interested to visualize it also. So you could use ggplot. So what is the first argument? So you can see that it's mentioned also data. That is our data frame df. And over here, aesthetics, we would be mentioning x and y both. Okay. So we have the absolute values calculated in this df data frame, right? 0, 5, 1, 7, 4, 1, 1, 8, 6, 9. We could do like that as well for bar chart. So x is equal to, let's say I'm mentioning churn, and y is equal to frequency. These are the column names that we have, right? So if you just look into the names of df, so we have churn and frequency. So if you see, if we just run this command, so this will just create the plot area for us, right? So no visualization. So to add visualization, we'd be using this geom layer, which we're using geom bar, and over geom bar by default stat is equal to frequency, right? The count, and that is something we would be changing stat is equal to identity. So we mentioned stat is equal to identity whenever we have the absolute frequencies already created. So we are mentioning x and y explicitly. Okay. So if we use customer churn, we could have directly used the churn new column on. Okay. But as we have explicitly mentioned the frequencies for each category, so we have to mention stat is equal to identity. And you could add the text also, like to show the frequencies. AES label is equal to the column name, that is frequency. Okay. And then we'll be just mentioning, for example, vjust, so which is the vertical adjust. You can keep any value. For example, I could give let's say 1.2. So positive means it would be inside, negative means it would be above. So, and then you could change the x-axis name, y-axis name, the title of the plot, which is not all the mandatory. You could add theme. So let's add theme BW. All right. So we have the chart over here where we could see that. So 5174. 169, you could see the numbers over here. You could add title over here plus GG title, customer churn distribution, or you'd like to add color code, you could add over here as fill is equal to Sublo 4. All right, so here we go. So I want of you to just first run all this set of commands. So first, just create this new column churn new. So somewhere you have to create churn new because, as I was mentioning, that the target variable has to be of 1 and 0. So we had yes and no, which we're converting that to 1 and 0 and making it as a factor type. So that you'd be having the actual also as 1 0, the breakdate also would be 1 0. All right, so once we have splitted the data, next is like we'll build the model, right? So let's name it as log mod. So we use GLM function for logistic regression. So the target variable we created is the churn new column, right? So that's our new column name. So churn underscore new. Okay, so make sure you mention the target variable correctly. Tilde followed by independent variables. Let's say we use independent variables as monthly charges. So we pick up another column as, let's say, internet service. So let's say these two columns we are trying to predict. The next we need to mention data, which is train one. And next we need to mention explicitly this argument family that we have. So in family, we need to mention we imports binomial. Okay. So as our logistic regression, it follows the target variable would be following a binomial distribution. This is the model that we're building. And over here, one more important thing that if you just do summary function, summary of log underscore mod. So this log underscore mod I've named is like logistic model. So I'm just giving a small name for that. Now, just like linear regression summary, it also shows us a couple of information like we have the p-values, which just shows that are they statistically significant or not. We see that 3 stars we have. Even if you had 1 star, 2 star, or 3 star, that means these are significant features worth to keep in our model. Okay. Now, over here, one important thing apart from these p-values that we also look into is AIC. Well, all of these are although not important for us. Okay, so it shows a couple of information in the output like null and residual deviance over here. So well, deviance of one observation is calculated as -2 times log of likelihood of that observation. Now this importance of deviance we further try to understand using this null and residual deviance. So null deviance is calculated from the model with no features, that means only including the intercept, and the null model. So basically it predicts the class via a constant probability, right? Whereas the residual deviance is calculated from the model having all the features. So if you try to compare the similar metrics on comparison with the linear regression, you can think residual deviance as the residual sum of squares and the null deviance as total sum of squares. Usually the metric is that larger the difference between null and residual difference, better the model. So we use this method like the difference between null and residual difference as for one model we get a value. Similarly, for multiple logistic regression model, if you build, we can compare with this metric. Okay, so even you can consider like any model which has lower null or residual difference than the other could be considered as better. But practically, we instead of looking into this metric, which is not much useful, we go for the AIC method. Okay, so AIC is typically given much preferences above deviance to evaluate any model field. All right, so over here, this AIC metric which we have, so AIC is called as Akaike information criteria. AIC, you can think of it as nothing but a counterpart of your adjusted R square. Okay, so it's important indicator saying that if you add an irrelevant feature, whether it would be penalizing for you adding those irrelevant feature or not. Okay, so if you add any feature which is not relevant for making prediction of a target variable, it will penalize for that. So it follows the rule of like smaller the AIC, better the model. Now the point is, I get this AIC of 4905.5. How do I know that it's small or big or whatever it is? Well, just by looking into one AIC metric of one model, it won't really help you. So it is more meaningful when you use it as a comparison between multiple models. For example, you build 2-3 logistic regression. Okay, so for example, let me just build a model using another feature. So for example, whether the customer is a partner or not. Okay. Now, if I use summary of log one, so you see that we have 4846.5 and also partner is significant. So if you see it's 4905 and this is 4846. So I would consider this is a better model than this one. We added another feature, it was significant and it just reduced your AIC value. Even before looking into any other metric, this just gives you first interpretation of your model results itself. Okay. So we didn't go for even accuracy metrics and all this. So this is like quick evaluation metrics that you could check and something you get in your summary model itself. Decision tree when we go for, so decision tree has a lot of certain advantages than any other even complex models also. So even if you compare it linear logistic, it's advanced, more advanced than that. Even if you try to compare that, it's a more advanced algorithms like random forest or any boosting algorithms like XGBoost and all. So this is still many attempts preferred ML model than simpler or even more complex models. Okay, now let's try to understand the reason that why it became so popular, or something that gets used so widely across all industries. Okay, so decision tree is something now which we could use to solve both the type of problem statements. Okay, be it regression or a classification problem. Okay, now although the method that it uses to solve regression or classification is different, so we call it as decision tree, but the approaches, like the underlying methodology, is different for solving the classification and regression. And moreover, when we are talking about decision tree, this is more of like generic term as we use decision tree, but there has been a lot of researchers who worked on developing different type of decision trees, and many papers have been published, although a couple of them become quite popular, which have been used in the industries over years. And recently, like the algorithms which we typically that we use in most of our problem statements, I could say, whenever we say that we are using decision tree, we by default go for the model called as CART algorithm. Okay, so which we call as classification and regression tree. So I'll talk about in some time about, well, even different popular algorithms we had, and we'll try to understand two popular methodologies. So although we use one of them, but we'll try to understand two popular methodologies that have been used to solve using decision trees. All right, so decision trees, why we do choose decision trees over any other algorithms is that decision trees often mimic the human level thinking, right? So it's very simple to understand the data and make some good interpretations, okay? And they actually make you see the logic for the data to interpret, okay? So not like typically any other black box algorithms. So if you see, it creates a structure like this, right? Tree-like structure. So it's nothing but, you can think of it like tree-like graphs for predicting the value of your target variable, okay, based on whatever independent variables that you provide as input, okay? And something as I was talking about, like it could be something that we could use for any type of problem set, be it regression or be it classification. Now, it picks up a particular variable, checks a condition. If it is true, come over here, we'll check another condition. If it's true, then this stuff, right? So there are a few jargons, although which we typically use in the form of the structure of this tree that you're seeing over here. So there are a few jargons that are cause like the various terminologies that get used, although we don't use this in the industries in general, like while at the workplace, but there's a kind of, I would say, again, good to know terminologies. Okay, so root node is something where the very first node from where starts all the splitting of the features. Again, this also is generally one of the independent features only, okay, and splits into two subnodes, okay, and this is the process we're calling the splitting, okay, dividing a node into two subnodes. And when a subnode further splits into two more subnodes, so that we are calling it as decision node. And this important, the final is the leaf node, okay. So leaf nodes are something which you can think that the nodes which do not further split, okay, that's like terminal or leaf node, we call them as, and that is the final results, like where the decision has been made, that all right, so if this has happened, the customer is not getting churn, and if this has happened, customer is getting churn. Now, based on different conditions, I could have different results, like in the end, right? So I could have 15 different features, and in the end, I could have, let's say, 8 different leaf nodes, right? Although my target variable is 2 only, but I could have 8 different leaf nodes, saying that if this happened, customer is not getting churn, and if this and that happens, customer is getting churn. Similarly, another stuff followed and say that, all right, so if this happened, customer is getting churn, otherwise it's not getting churn. Another thing in between splitted and further came into same conclusion that this happened, customer is getting churn, otherwise it's not. Okay, so the leaf nodes eventually all the time would be nothing but our end results, okay, which where the decision has been finally made. Now, there's one concept of pruning as well. Okay, so it's just the English definition of the pruning itself. Like when you just remove any particular subnodes of a decision node, we call that process as a pruning. Okay, so you have grown up the full tree and you're just cutting off certain section from your tree. Now the question comes that why is it even there in the first? Now this concept, which we'll discuss later in the session, where we'll talk about the concept of two challenges of any machine learning algorithm, of underfitting and overfitting challenges. And in those scenarios, we'll talk about this pruning concept as well. So decision trees sometimes might face the overfitting challenge, and because of which this pruning is a method which could reduce this overfitting issue of any decision trees. Okay, so it's like methodology to take care of the overfitting issue of decision trees. Now, right now, you could just note this particular portion as I talked about overfitting, because so once we cover understanding about the how decision tree works and all everything, and then we'll come into that concept of understanding about the overfitting and underfitting. All right, so these are a few terminologies that we have, so you could know this as well. It's not much necessary. Now, as we talk about decision trees, we have two categories, like regression tree or classification tree, right? Now, in classification tree as well, it could be used to solve any type of problem, even if we have multi-class classification problem, like the target variable is 3 categories. It would be able to predict, even if it is just typical binary classification, still it would be able to predict. In general, in the industries, we always do have majorly classification problem, binary classification problem only. It could be used to solve regression tree as well. Well, over here, for example, you see one thing is mentioned like C4.5 implementation, right? So this is one of the algorithm name. Okay, so one of the decision tree. So there are a couple of popular decision tree which I'll talk about. So this is nothing but where we are saying about the different types of the trees, right? So regression or the classification tree. Although these are, I would say, like the first couple of slides, these are all few theoretical stuff, which is good as a kind of knowledge, but nothing something which we use these jargons quite often in the workplace. Okay, because for example, the reason that why we don't use these jargons much, the genuine reason, let's say you have a classification problem, cool, and you're saying that, all right, so let's use decision tree to solve the classification problem. Now, definitely that means that you'll be using classification tree on, right? So you won't be using regression tree to solve the classification problem statement. So, and even the algorithm, the function name is also just the same itself. So it does make sense whenever having a classification problem and we are saying that we're going to use decision tree to solve it, it by default signifies that we are leveraging classification tree to solve it. Okay. Now, so what happens in the regression, in the case of regression tree, the value that is obtained by our terminal nodes, that is our leaf node in our training data, it is nothing but the average response of all the observations falling in that particular node. Okay, so if any unseen data observation falls in that particular leaf node, so make the prediction using its mean value. And in the case of classification tree, the value, or let's say the class that we get by the terminal node in the training data, it is nothing but the mode of the observation, okay, falling in that region. So for example, it won't be a scenario that if this happened, I have now 500 customers. That means it does not mean that all 500 are belonging to the same category, like all 500 are getting churned. You won't be having that scenario as well, right? That is like 100% accuracy, no error on. So it would be like, for example, in total 500 customers are there, 450 are getting churn and 50 are not getting. So you take the majority and say that, all right, so if this happened, the customer are getting churn because majority of them are getting churn, right? So over here in classification tree, so the leaf node we consider as whichever is the mode, we consider that leaf node is falling under that particular category. So that means if any new data set comes and falls in that particular node, leaf node, we'll say that, all right, so this customer is getting churn. So both the type of trees basically they divide all the independent variables into some distinct and some non-overlapping regions. Okay, so you can think of it as more of like regions as the high dimensional boxes type of. Okay, so perpendicular boxes it creates to separate the different categories. Okay, so the different feature wise that we have. Finally, the leaf node, it represents the actual output or the class leaf. And one more important thing is that it also helps to map the nonlinear relationships in the data set. That makes another great important point, because earlier the algorithms which we talked about, these are only used for the scenarios where they follow such kind of assumptions that they would be having linear patterns, right? So these tree-based models, they do have high accuracy, stability, ease of interpretation, and unlike linear models, they also map the nonlinear relationships as well quite good. Okay, so these are a couple of very important advantages of decision trees. So the first one, if we talk about the advantage, that's easy to understand for even for the people from any non-analytical background, because if you see that any particular data, okay, so for example, let me just show you over here. For example, this is just an example to show that this is data where in the end eventually someone is saying that any particular organization, or someone would be purchasing a computer or not. Okay, it looks into age, if it's young, and if it's student, yes, you're gonna buy. Otherwise, no. Middle age, yes. Credit rating, senior, go for credit rating check. If it's excellent, he or she would purchase. Otherwise, no. If we say to interpret the results finally from the decision tree, it's very simple, and anyone given this kind of tree-like structure would be easier for him to also understand, to compare with his own hypothesis, saying that, all right, so expect is this something like this, and something different is happening over here, and or something similar is happening in this case. And it could be very useful for anyone to understand that how finally the decisions has been made. So which are those customers who are getting final churn? They could know the whole rule from top to bottom, right? How exactly the rules have been defined. And these are something which we call them as classification rules. And as I was saying, that one major advantage about its non-parametric method, where you could say that the decision trees have no assumptions about the space distribution and the classified structure as well. You are categorizing it major. If you like to define it as like, eventually you would like to understand what is the criteria saying that, all right, so if this happened, the customer is getting churned. Does not happen, the customer won't get churned. Right? It's more of like filtering out, as you mentioned, about based on certain criteria. And those criteria is something your decision tree is telling you that what are those criteria, how you'd be categorizing them. So you can understand that how useful it could be for any business stakeholders as well. So because of which, like specifically in the financial institutions, these are such a popular algorithm that even for a lot of banks, even right now, it's like they by default go for decision tree algorithms. Although this is not something very good practice, but still I've seen in major banks working with them. In most of the problems, they try to prefer going for decision trees, although over the years they have been following the statistical methods like all this linear and logistic regression, but eventually coming to machine learning algorithms, they always prefer decision trees because of its interpretability factor. And because of a lot of regulators issues that you have in the banks, they always try to prefer to have interpretability factor of the models, even if any machine learning algorithms are used. And decision trees are the best for the interpretability factor because they could know that, all right, so if I'm saying that I'm not giving a loan to this particular customer, I'm giving them the reason that, all right, so if this happened, and because of which we won't be providing loan to this customer, thinking of that, right? So because the probability of default is pretty high for this customer, right? So you get to understand the criteria as well. But over here, the major question now, we talked about at a very high level, 1,000 feet overview of the decision tree. But now if you just try to deep dive to understand how exactly it builds up the tree, right? Let's try to get into this few core concepts of decision tree. How exactly it decides on where exactly to split, or how exactly it would split the features. Because let's say I do have 15 features, how it decides that at the very first stage, feature 1 will be there, in the next stage feature 5 will be there, in the third stage feature 2 would be there, correct? And it could be also this scenario that one feature occurring twice or thrice as well in one decision tree. Okay, so no one is stopping him from occurring multiple times. So how exactly structure it up? So for any decision trees, okay, so as we talked about, like I've just mentioned one of them, C4.5. I'll just show you another slide where I've named multiple models, model names as well. So any of the models, whoever have been researching on this and developed different type of decision tree, they all have to follow this particular strict rule of structuring this decision tree. Okay, so in the end, if you see, the end objective is to create a model which would give you high accuracy, right? You won't be willing to create a decision tree where, for example, in a lift node, for example, there's one lift node, you're saying that, right, so anyone falling under this node, they are getting churned. Okay, so let's say you have 500 customers over here. You won't be willing to have node finally 250 churn and 250 didn't churn. That is the worst thing to have, right? So if any new customer also falls in that, you won't be able to know that, all right, so whether he's getting churned or not, because it's like 50% belonging to each one of these categories, right? And that's the worst thing that could have been possible. So typically, whenever we would like to split any decision tree, so what it tries to follow is a very simple structure where it wants to split, it is split off whichever column it decides. It would try to split in such a way that eventually my splitting process would increase the homogeneity of my target variable in the leaf node. Okay, any resultant subnodes at every stage as we keep on splitting, it will check on that is my splitting criteria is improvising my homogeneity of the resultant sub. So homogeneity, when you're saying, so it's always considered with respect to your target variable. That means churn, if I do have in my target variable, so the homogeneity would be always considered with respect to that churn call. Okay, so that is nothing but what you can think of it as we are using this splitting method such that the leaf node should be as homogeneous as possible. Okay, that means if I do have 500, I should have closer to 500 out of 500. I'm saying that these are getting churned. So at least if 500 customers are there, most of it should be getting churned. Okay, so if it is 499, 498, that's the best scenario. It's like almost all of them are getting churned. So that's how it keeps on splitting. Okay, so it tries to follow whatever technique you use, but it should be more homogeneous as it keep on growing the tree. So decision tree splits the nodes on all the possible values. That means possible values means all the possible features that you have. That means all the available features. And then it will select the split which would result in the most homogeneous sub. Right, so you have all these points mentioned all over here. So the creation of subnodes increases the homogeneity of resultant subnodes. So you could say that the purity of the nodes increases with respect to your target variable. And the decision tree splits the nodes on all the available variables, that means all the independent variables, and then it selects the split which results in the most homogeneous sub. Okay, and this would be more clearer when we try to understand the algorithm. Okay, so we'll consider two algorithms to understand detail. So just mention a few of them which are over the period of time which became popular. Well, although right now in the industry, as I was mentioning, we use the fourth algorithm that I've named as CART algorithm. Okay, now what happened? Let me just talk a few minutes about just the history of this. Again, some theoretical stuff which is not much important, but good to know. So start off with the ID3 iterative dactymizer, which was the first of the 3 decision trees which was implemented by researcher Ross Quinlan. Okay, so he built this decision tree at the very first stage where he considered only categorical columns even for independent variables and tried to predict whether, so for a binary classification problem for a 1-0 target variable. Okay, but the major disadvantage that it was that it could only use just the categorical input data, and he found that all right, so it cannot handle numeric attributes, or even if the data has missing values, it cannot handle them. Something in real-time data, it can't be worked in large extent because there would be missing values in the data, or there would be numeric columns which could have a significant input to the output, right? So he moved on to develop one more model, which he named it as C4.5. Okay, so C4.5 is just extension of his earlier ID3 algorithm. Okay, and that again he tried to solve it for classification only, and it had number of improvements on top of the ID3. Okay, so it could now handle both continuous and discrete features. So to handle the continuous feature, it created a threshold. So it will create a threshold and then splits the list into those who are above the threshold and those who are less than or equal to it. Okay, and even for missing value attribute, it by default it created another category only for the missing values. Okay, so took care of both the disadvantage that he had in ID3 algorithm. Okay, but over the years he moved on to build one more algorithm which he named as C5.0. Again, the same researchers, Quinlan himself, he built this, and this basically again offered a couple of improvements on top of C4.5, and that was specifically on the performance side. So speed wise, so if you consider C5.0 was significantly faster than C4.5, and even it was much more memory efficient than C4.5. And moreover, like even C5.0 gets similar results to C4.5, even with some smaller decision trees as well. So these are a couple of advantages that he made on C5.0 and which became popular as well. And yeah, so C5.0 has been used over the years for a lot of time, but again, after which the CART algorithm has been developed, and that became another huge popularity in the industries, and something which right now also we do use by default always CART algorithm. And as the name itself is, if you see, it's mentioned as classification regression, right? So this CART algorithm could be used to solve both the type of problem statements. Okay, so the regression as well as classification problem, and it could handle again, both numeric categorical independent variables. And this algorithm could also handle the outliers as well if you do have in the data. Okay, so what it would do is just create some another leaf node with some, even if you have very few data points in that node. Okay. All right. So it typically actually won't be getting impacted with outliers in the data as well, especially the CART algorithm. But if you see the models like linear or logistic regression, both the algorithms, both the linear models which we discussed till now, so both of them gets quite impacted with the outliers in the data, right? So because the whole structure methodology itself, which gets used to find the best line of fit, right, gets impacted with all the values that you provide as input, right? And if even if you have single big outlier, it would drastically impact those coefficients. And the child algorithm is also only specific for classification, and because of which again this didn't become much popular. So I would say card algorithm is the only thing which you could work on and something that you could know. But as a knowledge understanding purpose, I would explain the working of like how exactly the methodology gets used for C5.2 and CARD. Although the methodology of C5.2 gets used in has been used in all three methods, okay, for I3, C4.5, or C5.2. All right, so well, this is a very popular example from many books that you can find that this is the day of, for example, let's say you'd like to play badminton day, and let's say on Sunday today you wanted to play, or let's say tomorrow you'd like to play badminton, and you'll decide whether to play or not by, let's say you go out and check if it is hot or cold, check the speed of the wind and the humidity, how the weather is, whether it's sunny, cloudy, or rainy, and then taking consideration of all the factors, you decide whether you want to play or not. Okay, this is the data that you have from the historical last 10 days information. Now, you may use this table to decide whether to play or not, but what if the weather pattern on the Saturday, Sunday, or any next day that you'd like to check for does not match with any of the rules in your table, right? And that could be a problem for you, right? And Regression Tree could be a very great way to represent the data in the in the tree-like structure, because it takes into account of all the possible paths that could help you to make the final decision. So you check for weather if it's sunny, you check for humidity if it's normal, you're gonna play. If it's cloudy, you're gonna play. If it's rainy, check for the wind. If it is strong, you're gonna play. If it's weak, so you're gonna play. So and in case if you have any numeric features, it gets decided based on particular threshold value. Okay. For example, if it is less than equal to 75%, you're gonna play. Otherwise, you're not. Similarly, for if it is rainy, you check for wind velocity, and based on that, you decide whether you're going to play. And this is just a simple example, just a visualization to understand more about how the structure looks like. But more interesting would be for us now to understand how exactly the logic happens. Okay, so this algorithm, as we talked about, how it finds out the best feature on which how it could be splitting. So a typical structure is this: that the first step is we pick the best feature. The best feature, that means the one which splits in the most optimal way. That means it would create it will generate more homogeneous subnodes. Okay, that's the best split we are talking about. Ask the relevant question means we're talking about the feature. We are asking a particular question. It would have certain answer, like if it happens, what would happen? Otherwise, what would happen? And then based on the result, you'll be having one more feature that you'll be choosing again. So it's more of an iterative step that you see, right? Every time it's going to do the same task till it reaches to the final leaf node, which is like the output, the class label that you have. All right. Now we'll talk about next now the features. So that means the methods, that how exactly this two methods. So we have one, we talked about the cart, and there is C5.2. So the cart algorithm, which we talked about, it uses this Gini Index method to split the tree. Okay, so how it finds that on which feature we're going to split it, okay, in any particular stage. The another method like C5.2, it uses information gain methodology, the entropy concept, to identify based on which feature will be splitting. Actually, in the real-time scenario, as Soumya, as you mentioned that in Python, for example, if it was not interested, like by default, we go for the cart algorithm only, which use this Gini Index. And typically, it really does not matter much for us. But although I would be going to discussing about this in detail, but whenever we build any decision trees, so we majorly build only one decision tree. Okay, so unlike we say that when we say that we are developing machine learning algorithms, we try multiple different algorithms, right? Let's say logistic regression, decision tree, and forest, and we get the results, prediction results of all of them, and then we see that whichever is giving us the best result, we go for that model. But when we're saying decision tree, now, for example, I could build one decision tree using cart algorithm, and the decision tree I can build, for example, using C5.2. Okay, but in general, we don't do this method because both eventually results pretty similar result. Okay, pretty same. Like you won't find that, all right, so if I use C5.0, I got 90%, and if I use cart algorithm, I got 95%. Okay, you won't have that any such kind of differences. It will be very, very small difference result in the results. And that's the reason that why we typically just go for one approach only, which we call it the cart algorithm, okay, which uses this Gini index method to split the tree. Now, next is something this which we'll try to understand this methodology, the underlying mathematics, that how it splits the tree. So let's start talking about the first metric, the Gini index. This is something which I was mentioning before the break, that for the cart algorithm, the classification and regression tree, for the classification part of this cart algorithm, we use this Gini index approach. Okay, so it works for classification target variable. That means 1,0 target variable when we have. So it follows the simple notion that higher the value of Gini, higher the homogeneity, right? So what exactly the Gini is? So the Gini index. So we calculate this Gini basically at first for the subnodes. For example, we have two categories, male, female. So for male, we calculate the Gini. For female, we calculate the Gini score. And then for the whole column, at a column level, we'll create the Gini score, right? So we calculate the weighted Gini score finally of each node of that split, and that weighted Gini score is something that which we compare for across all the features. Okay, so the formula for Gini score is like p squared plus q squared, such that p is the probability of success and q is the probability of failure. So let's do one thing. We'll take an example to understand this analysis. Okay, so let's say we are given with a particular data set where you have 30 rows, that means 30 student information, and you have information like gender, boy or girl, which standard he or she is in, +9 or +10 in his high school, and the height 5 to 6 feet. Okay, and the target was like would be playing cricket in their leisure time. Okay, so 15 out of 30 they play cricket in the leisure time, and you have the distribution of their information. Okay, so based on whatever the data, the raw data that you have of the 30 rows, let's say we're creating this simple splitting of the data. Okay, so 30 students, out of which 15 are playing. If we try to split with respect to gender, so male and female, two categories, 20 male students we have, 10 female. So 13 out of 20 they play cricket in the leisure time. 2 out of 10 female they play cricket in the leisure time. Similarly for height and class, these are the data that we have. Okay, so these are the known factors for us. So let's consider these two scenarios, like the split on gender and the split on class, to understand that which feature we'll now consider for splitting. Okay, so are we considering gender or class? And that we'd be doing based on considering what is the final Gini score for gender and what is the final Gini score for class. And then we'll see that whichever is providing the higher Gini value, right? That is something which will be considered for splitting purpose. So to know the Gini score for the gender, we'll be first calculating the Gini score for male, and then then we'll be calculating the Gini score for female, and then we'll be taking the weighted average of this, right? So weighted Gini score. So for male, 13 out of 20 are playing cricket. So, right. So what is the probability of success over here? That someone would be playing cricket in their leisure time. So P over here, if you see P is 0.56 and P over here 0.43, right? So if you see for both, it would be 0.51 only, correct? And when we calculate the weighted Gini score, that also would be turned out to be 0.5. Now, if you just compare both the Gini score, so we have 0.59, we have 0.51. So definitely the split will be happening with respect to the gender at first, right? Because the Gini score for gender was higher than the class. The next one, all right? So let's consider information gain methodology. Okay, now information gain, this is absolutely based on the concept like the less impure node requires less information to describe it, and more impure node would require more information. So information theory is just a measure to define this degree of disorganization. Okay, so in a system which we're calling it as entropy. Okay, so if the sample is completely homogeneous, you could say the entropy is 0. And if the sample is equally divided, like we have 50-50% from both the categories, the entropy would be 1. Okay, so information gain typically we do calculate from the entropy itself, like 1 minus entropy could be called as information gain. So typically you could find somewhere it mentions as entropy measure or as somewhere as information gain. So it's just the negation of each other. For example, if you talk about entropy wise, entropy is nothing but the impurity wise that we're talking. Okay, so you could say that when we are talking about information gain, we would go for high information. All right, so high information gain means, for example, in this case, just 2 misclassification we have, right? And in the low information gain, it's like, let's say we have equal observation. So it's like 50%. It's a worst scenario that you could have. Now, same thing if you go for entropy wise, when we're talking about entropy, we're talking about the impurity, right? So for example, if it's completely homogeneous, okay, so all the observation belong to the same category, then that is like entropy is equal to 0, right? So no error. The worst case would be the 50-50%, right? 50% belonging to one category and 50% belonging to other. So entropy we calculate using the formula like minus P log P minus Q log Q. Okay, so over here we have the formula written. So if you try to plot this, okay, so the curve would look something like this. Okay, so the probability and the entropy wise. So if you see, for example, let's say all the observation over here, let's say belonging to the same category, right? So that's like entropy is 0. Okay, so there's no mistake. So this is like 0 category, this is the 1 category. So if it all belongs to the same 1 category, so it's entropy 0. All the observation belongs to the 0 category, it's like 0. Like again, entropy is equal to 0, right? And then it keeps on increasing till your p is equal to 0.5. So that is, for example, this one. Let's consider that I'm not counting over here right now, but let's consider that you have equal number of, let's say you have 20 circles, 20 plus sec. So it's like equal number of observations from both the categories, right? And that is like, you could say that this is the entropy of 1. Then there could be scenario like the less entropy. So these are the scenario like this. If you have probability less than 0.2, it's fine. It won't be having much entropy. Similarly, greater than 0.8, these are also good. But if you see the ranges between actually 0 to 0.4 to 0.6, these are the actually not so good ones, because it's almost like 50% belonging to one other category, right? So 0.4 means 40% probability is there that the customer is getting churned, right? So which is not so great, again, because you have 60-40 split. Similarly, again, over here 0.6, when you're saying like 60% probability is that you'd be getting churned, again, like it's 60-40 ratio that you have, right? So these are not, again, the good, I would say, the class labels that you could expect in the end, okay? Because these are, although you'd be having, let's say when we are saying 60%, 40%, you'd be having one mode and it will be marked as 1, but still it's not a good predicted results that you'd be getting, right? Whereas if you get something like 0.9, you could say that, all right, so 90% probability is that the customer is getting churned. So taking the same example, okay, so over here we're just mentioning as information gain is number 1 as entropy. So if you talk about the information gain wise, we'll go for whichever nodes are giving us high information gain, that we'll be choosing. If we go for entropy wise, we'll be choosing whichever is giving us the lowest entropy. So at the overall level is 1, that means minus 15 out of 30 are being cricket. So minus p log p and q log is 1. And now the next thing we'll go for the weighted entropy for gender. Similarly, the weighted entropy for class. Okay, so this is minus p log p minus q log q. So 2 out of 10 were being cricket, probability of success, and probability of failure would be 8 by 10, which is 0.72. So over here also there will be minus, actually it's not written correctly. So minus p log p minus q log q, that is 0.92. And when we take the weighted entropy, it turned out to be 0.86. Now, if we consider for class wise, over here also minus has been missed. So minus p log p minus q log q is 0.99. Similarly, over here minus p log p minus q log q would be 0.9. Weighted entropy also would remain the same. Now, in this case, entropy wise, when we compare 0.99 versus 0.86, definitely we are going to choose the one which is giving us the lowest entropy, right? And in this case, it's the gender again. Now, if you just try to compare the previous method where we came into the conclusion that the split would happen with respect to gender. And the same thing we are also able to see over here as well, like with respect to entropy wise also when we try to find out. So it also came to the same conclusion that we'll be splitting on gender on, which I was saying in the beginning as well, that in general, even in the end, when we talk about the accuracy, so we try on the different projects as well, that it actually does not impact much. Okay, so much means it's in fact very less. The results, even the decision tree structure also becomes pretty similar when we use beat C5.0 or even the CART algorithm. So this is how basically these two algorithms work, the C5.0 and the CART algorithm. So if C5.0 uses this information gain approach and the CART algorithm uses Gini Index approach. Now, as we talked about this method, the decision tree could also be used for the regression problem, right? So this method, which we are talking about, the CART algorithm, it also uses another approach for solving the regression. Now that is way simpler than the classification version. So although the function that we use in R Python is just the same only for both regression as well as classification. So over here, the approach that it uses is, so over here, for example, let's say we want to predict the target variable, let's say beat sales or something, which is numeric in nature. All right, so let's try to understand what's the idea, like how exactly it decides on the splitting. Okay, so the basic regression tree, what it tries to do is partition the data into some smaller subgroups. Okay, and then it fit a simple constant for each observation in the sub. Okay, and the partitioning is basically done by successive binary partitions. So when we're talking about binary partitions, or something which we call it is also recursive partition. Okay, so based on different independent variables. So you can think of it as that the constant to predict is nothing but the average response of the values for all the observations that fall in that particular subgroup. Now, how exactly decides on the splits? So it's important that to understand that this partitioning of the variables are typically done in the top-down greedy fashion. So that means that the partition done earlier in the tree will not change based on the later partitions. How these partitions are made? So the model begins with the entire data set, and then it searches for every distinct value of the every input variable, okay, to find the independent variable and the split value that would partition the data into two regions. Let's say you call it as R1 and R2 two regions, in such a way that the overall sum of squares error, okay, the SSE or beat even MSE also, anything that is minimized. So like split into regions, and then you calculate the sum of the square errors or even the mean square error, and that is something we find that whichever is giving us the least MSE or SSE is something which will be chosen for the best split. And so this is the having found the best split, we partition data into two resulting regions, and we repeat the splitting process on each of the two regions. So this process is something we continue until some stopping criteria is particularly reached. Okay, so stopping criteria is something which we could explicitly mention in while developing an decision tree. Okay, so I'll come back to this stopping criteria again later. So as we'll talk about now about this particular concept of the underfitting and overfitting. Okay, and because of which we many times might be inclined to provide such any stopping criteria for decision tree as well. Okay, so we might not be interested to grow fully a particular decision tree, be it a classification or even a regression tree. Okay, and what exactly is the stopping criteria? That is something we'll see when we'll try to execute in the R programming. Okay, now, but let's try to understand this concept clearly. And this is a pretty important concept again. Over here, till now, the concepts that we have discussed so far, the prediction. So can you tell me that when we talked about making the predictions, right? So we try to make the predictions specifically in the train data, like the training in the train data, and the performance we check in the test data set. This is typically the generic process. Now, and the prediction on which we make the decision that whether we'll be using this model or not, that also we typically decide based on the understanding of the test data set performance, right? How well it performed in the train and how well it performed in the test data set. But one more important concept that we need to understand while developing any decision tree is that any machine learning model is to understand about this error. Okay, now whenever we are developing any model, okay, so we have three types of error. One is bias error, okay, and there is variance error, and another is something which we could call it as irreducible error. Okay, and that is something which happens because of some noise in the data set itself, right? And something which perhaps could not be reduced. Okay, but this bias and the variance error that we have, that is something which can be mitigated. Okay, and there's always typically that we find that there's some kind of trade-off in this bias and variance errors. If we like to reduce bias error, the variance error increases. If we try to decrease the variance error, the bias error increases. Okay, but we'll try to find the optimized value such that it minimizes both bias and variance. Okay, so let's try to understand this about this error scale. Like, what are these two types of error, like bias error and the variance error? So bias is nothing but the difference between the average prediction of our model and the actual value which we are trying to predict. Okay, so the model which with very high bias, they pays very little attention to the training data. Okay, and they try to oversimplify the model. So that always leads to very high error on your both training as well as your test data. So typically the predictions that we make, okay, so we try to make the prediction on both train as well as test. Till now we made the prediction on test only, but once we build the model, like we train the model on training data, it's always a good practice that we make the prediction on both train as well as test. Okay, now for example, we made a model and we got, let's say, 45% accuracy in train and 41%. So, and let's say talk about, we are talking about over here accuracy. Okay, so, and let's consider that accuracy is the, not getting into accuracy patient recall, let's say the accuracy is the best metric for the problem statement, and we are saying that 45% accuracy we got in train and 41% accuracy in test data. Now, can you tell me that whether it's a good model or not? All right, so one thing I would say that Krishna, that you mentioned, good model is one which has around 90% accuracy. Soumya has, for example, mentioned the no as accuracy is less. That's fine. It's generic statement saying that accuracy is less. But Krishna, you can't make. It's better not to make statement like this saying that around 90% accuracy is good, because you could typically never make any such kind of statements. Okay, so this accuracy factor is very much dependent on the data set and the problem statement. Okay, for certain, as I was mentioning earlier, that for certain problem statement 90% also could be less. Okay, because even the domain expertise are guys are getting 95% accuracy in the problem, and if your model is 90% accuracy, perhaps they might not be happy as well. Even if you're making automating the system, still the expectation could be higher. In certain problem statement 90% reaching is next to impossible. Even they are trying their best for getting 70% accuracy. Okay, so in general, that's something you can't say, but yes, definitely 50% accuracy, 40% accuracy is very low. Okay, in this case, yes, you could say that 41% accuracy, it's too low for deploying any production environment. But yeah, Krishna, as I was mentioning, so you could keep it generic saying that it's not high, but only saying that around 90% is only good, that is not so good to say. Okay, all right, so Shubhangi, this is the similar point to that. This is not so correct statement to say the accuracy have to be close to 100%. That is, as I was saying, again, it's very much dependent on problem. Real-time problem statement, you'd hardly, I would say, you'd find any real-time problem statement where you can get the accuracy close to 100%. Okay, so 95%, 98% accuracy is like literally tough to find in hundreds of business problem statements. If you see, there could be very few, less than 5% problem statements that you could see that would have percentage higher than 95% as well. Okay, so typically it's you should not be saying such kind of statement. Okay, so the real-time problem statements getting even 80% accuracy is very decent enough for any production deployment purpose. Okay, and in many problem statement, even 70% is considered very decent for any production deployment. All right, so now over here in this case, so training we got 45% accuracy, which itself was not good, and test again we got 41% accuracy, which is not definitely again decent enough. So if you see, this is something which we call it as high bias error. Okay, even your trained model could not perform well on the same data set, because it could be the scenario that over here that the data is pretty complex. Okay, there is not following even a linear pattern, and you're trying to fit a model which is taking an assumption about the data itself and not able to understand the data itself, which is, you could say that it's oversimplifying, right? So, and that leads to high error on both of your training as well as test data set. So this is high bias, and something which we are calling it as underfitting. All right, so over here, if you see, this is something which we are calling as the high variance. So the variance is the variability of the model prediction for any given data point, okay, which tells us the speed of our data. Okay, so model with high variance, basically they pay a lot of attention to training data, does not generalize on the data which it has not seen before. Okay, so that means this is the model which performs pretty well on the historical data. That means on the trained data on which it has learned. But in the unseen data, it could not perform well. Okay, so this is something which we call it as high bias, high variance error, and something which we call as the overfitting issue. Okay, so this is so Krishna, as you mentioned, for example, yes for trained data and no for test data. So in the end, if you see, although we care about the performance of test data, right? So when you go for deployment in the production environment, you try to see what is the performance of test data, right? You really don't care about what happened in the training data, right? So whether it's, even if it is 99%, 99.9% accuracy, you don't care, because all you do care about, you do care about is how it would be performing in the future data. Let's take an analogy to this concept. Okay, let's think of it that you are preparing. So Mr. X is preparing for a particular examination. Let's consider GMAT examination for applying for a particular B school, and he prepare while he's doing his preparation, he in his mock test, optional mock test paper, let's say that we call it as similar to our training data performance. So this Mr. X, who tries to memorize each and every pattern of the question for the mock test, and understood that, all right, so if this type of question comes, this will be the answer, and based on all the values, everything, he tries to almost memorize each and everything, and because of which in his mock test he got very good result. Rather than understanding the concept, the logic, he tried to memorize each and every pattern of the questions and answers. So he got 98% accuracy in his mock test. But when it comes to the real day, the final day examination, the question patterns were different, although the topic was same, but they have been asked the questions in different manner, with the different, perhaps in different language as well. And because of which the Mr. X could not identify that how exactly to solve the problem, because he rather didn't follow the logic itself for solving the problem. And he scored 35% in the final GMAT examination, let's say 35%. And if you see, if you think about like in our case, like deployment of the production environment for a model, similarly for, let's say, the B schools, they would be looking for their final GMAT examination result only, right? They won't care that how well or how bad they have scored in their mock test, right? So similar to that over here as well, irrespective of whether, so this is an example of overfitting, okay? So where the model performed pretty well in the historical data because it tries to memorize each and every pattern of the data, and because of which it performed quite well in the historical training data set, but in the new data, it could not perform pretty well, okay? And you see that there would be huge difference in the training performance and the test performance, okay? There's something we are calling this overfitting issue, and where you could say that's high variance set. And then on the other hand, let's say there's another student, Mr. Y, who don't love studying, and he really is not much sincere for his examination. He didn't prepare well, and he gave the mock test where he got 35% result. He went for the real day examination and he got 33%. And that was expected, right? He couldn't do well in his mock test, even in the final day examination also he won't be able to do well. All right, so and that is like high bias, the underfitting. Okay, so the linear models sometimes might lead to underfitting. Could be said that as they take certain assumptions about the data. So typically the linear models like linear regression or logistic regression algorithms. So this algorithm could lead to typically high bias or underfitting issues. So over here, you could consider decision trees sometimes might lead to overfitting issues as well. Now, for linear regression, for example, it could be that considering the right factor, it could be said that you are missing out certain signals, certain important features for the model that you could include in the model to improve the performance. Or it could be said that you could add more data in your training data set to improvise the performance. Or otherwise, still, if it's not improving, it's like you could just change the model itself. Like you have to capture the data is pretty complex for your linear regression model. So you go for, let's say, other models like Decision Tree or Random Forest. Now, in Decision Tree, if it goes for, or if you see that there's overfitting issue, in that case, you might go ahead with removing definitely the irrelevant features if you do have. And then again, you could put certain stopping criteria as well. Like, for example, you could mention that how many number of observations, let's say, you must have in your leaf. Let's say you could mention, let's say, I need at least 100 observations in my leaf node. Okay, so it could have been the scenario that if it keeps on growing the tree for the most homogeneous leaf node, In that case, it could have been reached till just 30 observation. But you don't want to go till 30 because that might lead to overfitting of the data. Okay, so you may say that, all right, so stop whenever you see that 100 observation is there in a particular. Okay, so it should not further split on if it has already 100 observation. There's like certain stopping criteria that could be put, but it's not mandatory that always we have to do those. But if you see that without giving any criteria, like how's the performance in training test, if it's working well, good enough. If it is not, in that case, you might be willing to use such kind of stopping criteria to reduce the overfitting issues of the model. But still, you might go ahead with using the models like random forest as well, which takes care of this overfitting issue. Now, random forest is also a pretty simple model because it leverages the decision tree only to build the model, which we'll talk about. So it's a very simple thing. As we understand the decision tree, there's a building block for random forest, because once you understand the decision tree, it becomes quite simple for you to understand the random forest as well. Right. So do you all remember that how could we find, for example, let's say we'll be working with a data set called as IDs, which is again from the data sets default data that we have. So you could just load it as IDs equal to IDs. Okay.
So here what I'm doing is I am mapping the LSTAT column onto the x-axis and the MEDV column onto the y-axis. And I will give the label of the x-axis as LSTAT and the label of the y-axis as MEDV. And finally, I'll show this graph which I've built. So what I've built is basically a scatter plot where MEDV is on the y-axis and LSTAT is on the x-axis. So you see that as LSTAT increases, MEDV decreases. So there is an inverse relationship between MEDV and LSTAT. So again, I'm reiterating it. As LSTAT increases, MEDV decreases. So this tells us that there is an inverse relationship between MEDV and LSTAT columns. Now, to build the model, we are supposed to separate the independent variable and dependent variable into two separate objects. So I'll take this LSTAT column from data1 and store it into X object. Similarly, I'll take this MEDV column from data1 object and store it in Y object over here. So X consists of my independent variable and Y consists of my dependent variable. Now it's time to divide the data set into training and test sets. So we have this train test split function from sklearn.model_selection. I'll go ahead and load that function. And this function over here takes these three parameters. So X and Y are basically the dependent variable and the independent variable. And then we have test size is equal to 0.2. So this states that 80% of the records would be in the training set and 20% of the records would be in the testing set. So it's a 80-20 split. And this random state which you see, so this is basically a seed value, so that if I want to get the same values again, I can set the same random state to get the same values. And I am storing these values in xtrain, xtest, ytrain and ytest. So xtrain contains all of the train values for that independent variable. Xtest contains all of the test values for the independent variable. Similarly, ytrain contains all of the train values for the dependent variable, and ytest contains all of the test values for the dependent variable. So now that we have xtrain, xtest, ytrain and ytest, it's finally time to build the model. So I'll go ahead and load the linear regression model from sklearn.linear model, and then I'll fit the model. So first I'll create an instance of this. So linear regression, and I'll create an instance and I'll name that instance to be regressor. And with the help of this instance, I'll fit the model on top of the training set. So regressor dot fit, and I will pass in xtrain and ytrain. So to sum it up, what I'm basically doing is building the linear regression model on top of the training set, which basically comprises of the independent variable and the dependent variable. I'll click on run. Now let me have a glance at the intercept and the m value of it. So linear regression is nothing but y equals mx plus c. And that c is nothing but the intercept. So you see that the intercept is 34.12. And m, which you see, this is the coefficient. This coefficient is nothing but the slope. And you see that the coefficient is minus 0.91. So there is a negative value associated with the coefficient because there is an inverse relationship between the dependent variable and the independent variable as we saw over here. So as LSTAT increases, MEDV decreases. And that is the reason this coefficient is associated with a negative value. So now that we've built the model, it's time to predict the values on top of the test set. So again, I'll use this instance and I will use the predict function with the help of this instance. So regressor.predict, and I will pass in this xTest object inside this function, and I'll store this in the ypred object. So we've built the model and we've also predicted the values. Now let me have a glance at the number of rows and columns of the actual values and the predicted values. So we see that both the predicted values and the actual values comprises of 102 records in total. So now that we've predicted the values, we'll go ahead and calculate some metrics. So we'll find out the mean absolute error, the mean squared error, and the root mean squared error. I'll click on run. So see that the mean absolute error for this model is 4.69, the mean squared error is 43, and the root mean squared error is 6.62. So again, the lower the values of these three, it means the better the model is. So let's say if we are comparing these values with some other model, and if these values are less than that second model, then the first model would be better than the second model. So that was implementing simple linear regression in Python. Now we have our next question over here. So the question is, what do you understand by logistic regression? Well, logistic regression is actually a classification algorithm which can be used when the dependent variable is binary. So let's take this example. So here we are trying to determine whether it will rain or not on the basis of temperature and humidity. That is, temperature and humidity are the independent variables and rain would be our dependent variable. That is, we're trying to understand whether it will rain or not on the basis of the temperature and the humidity. And again, logistic regression algorithm, it actually produces an S-curve. So let's say x-axis over here, it represents the number of runs scored by Virat Kohli, and the y-axis represents the probability of Team India winning the match. So let's say this point over here, it denotes 50 runs. So what we can see from this graph is, so if Virat Kohli scores more than 50 runs, then there is a greater probability for Team India to win the match. And similarly, if Virat Kohli scores less than 50 runs, then the probability of Team India winning the match is less than 50%. So let's take this value over here. So let's say the number of runs scored by Virat Kohli is around 60. So if the number of runs scored by Virat Kohli is around 60, then the probability of Team India winning the match would be, let's say, around 65% or so. Again, let's take this value over here. So let's say this is around 97 runs or 95 runs. And if Virat Kohli scores 95 or 97 runs, then the probability of Team India winning the match is 1, which is 100%, isn't it? So similarly, this value over here. So let's say this is around 5 runs or 10 runs. So if Virat Kohli scores 5 or 10 runs, then the probability of Team India winning the match is 0. So basically in logistic regression, the y value lies within 0 and 1 range. And this is how logistic regression works. So now we are supposed to implement logistic regression on this hard data set where the dependent variable is this target column and the independent variable is the age column. So let's go ahead and implement logistic regression. So let me start off by loading this data set first. I'll use the read.csv function. Now let me have a glance at this dataset, view of heart. So this is our entire data frame, and this target which you see, this is our dependent variable, and we have the age column over here, and this is the independent variable. So we are actually supposed to rename this. So we see that the column name is incorrect over here. So our first task could be to rename this column. Let me go ahead and do that. So I'll use the column names function, and I'll pass in this data frame which is heart, and I am supposed to rename the first column. So I'll give in 1 inside the parenthesis, and I will rename this to be age. So now again, let me have a glance at this modified data frame. So it'll be view of heart. So see that we have successfully renamed this column from IH to age. Now let me have a structure of this data frame. So structure of heart. So you see that most of these are integers. But then again, since we are building a logistic regression model on top of this data set, this final target column is supposed to be categorical. It cannot be an integer. So we'll go ahead and convert this into a factor. So I'll use the as.factor function and convert this integer value into a categorical value. So as.factor, and I'll pass in this column over here, which is hard $target, and I'll store the result back to hard $target. Now again, let me have a glance at the structure. So that will be structure of hard $target. So initially it was integer. Now we have converted that integer column into a categorical value, which has two levels, which are 0 and 1. So now I'll actually build a simple logistic regression model, and I'll not divide this data set into training and testing sets. So we'll do this and we'll see what are the different probability values for the person to have heart disease on the basis of the different age values. And to build the logistic regression model, we'll be using the GLM function. So again, this takes in 3 parameters over here. First parameter is the formula. So here target $age is the formula, which basically indicates that target is our dependent variable and age is our independent variable. And we are building this model on top of the entire data frame, and family is equal to binomial. So when we state family is equal to binomial, we are basically telling R that this is a logistic regression model.
Just a quick info, guys. Test your knowledge of Python by answering this question. What do we use to define a block of code in Python language? A. Key. B. Brackets. C. Indentation. D. None of these. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
And I'll store the result in log mod 1. So now let me have a glance at the summary of the model which we've just built. So summary of log mod 1. So we have this p-value over here, and we see that there are 3 stars associated with this p-value. So this basically means that we can reject the null hypothesis. That is, the null hypothesis states that there is no relationship between the age and the target columns. But since we have 3 stars over here, this states that the null hypothesis can be rejected and there is a strong relationship between the age column and the target column. Now again, we have other parameters over here. So we have something known as null deviance and residual deviance. So simply put, the lower the deviance value, the better the model. So this null deviance basically tells us the deviance of the model when we don't have any independent variables. That is, when we are trying to predict the value of the target column with only the intercept. So if that's the case, then null deviance is 417.64. And residual deviance is that deviance when we include the independent variables and try to predict the target column. So when we include the independent variable, which is age, we see that the residual deviance drops. So initially when there were no independent variables, the null deviance was 417. After we included the age column, we see that the null deviance has reduced to 401. So this basically means that there is a strong relationship between the age column and the target column, and that is why the deviance has reduced. So now that we've built the model, we will go ahead and predict some values. So now I want to know the probability of the person not having heart disease when his age is equal to 30. So now let me actually head back to this data frame over here. So the values in this target column, it is 0 and 1. So when we predict the values, we get the prediction for 0. That is the person not having heart disease. So when the person's age is 30, we see that the probability of the person not having heart disease is 81.2%. Now similarly, I'll predict the probability of the person not having heart disease when the age is 50. So when the age is 50, we see that the person not having heart disease, the probability, it comes down to 60%. Now what I'll do is, I'll predict the values for a set of age values. So this time the age value, it starts at 29 and it goes on till 77. So I'll get a set of predictions starting from 29 to 77. So you see that when the age is 29, the probability of the person not having heart disease is 82%. Similarly, when the age of the person is 30, the probability of the person not having heart disease is 81%. So as the age increases from 29 to 77, the probability of the person not having heart disease decreases. So this is the final case over here when the age of the person is 77. So when the age of the person is 77, the probability that the person does not have a heart disease is 26%. So this is quite an interesting relationship, isn't it? So we see that as the age of the person increases, there is more likelihood that the person would have heart disease. So this model we built on top of the entire data set. Now what we'll do is, we'll divide this data set into train and test sets and build the model on top of the train set and predict the values on top of the test set. So again, for that purpose, I would require this caret package. So library of caret. Again, this caret package comprises of the create data partition function. So this takes in these parameters over here. So this is the split criteria, which is hard $target. That is, I want to split this data frame with respect to this target column. And the split ratio, which I'm stating over here, is 0.7. That is, 70% of the records would have the true label associated with them, and the rest 30% records would have the false label associated with them. And the final result, I am storing it in split tag. Now, what I'll do is, from the entire hard data frame, whichever records have the true label associated with them in the split tag, I'll take all of those records and I'll store them in the training set. Similarly, from the entire hard data frame, wherever the split tag value is equal to false, I'll take all of them and I will store them in the test set. So I have my training and my testing sets ready. Now let me have a glance at the number of rows of the training and testing set. So n row of train, there are 213 rows, and n row of test, there are 90 rows. So now that we have the training and testing sets ready, let me go ahead and build the model on top of the training set. So again, we'll use this GLM function and build the model. So this time the formula is the same, which is basically target tilde symbol age. So target is the dependent variable, age is the independent variable, and we're trying to determine the probability of the patient having heart disease with respect to his age. And we are building this model on top of the train set. And since this is a logistic regression model, the family would be equal to binomial, and I'll store this result in log mod 2. Now that we've built the model, it's time to predict the values. So I'll use the predict function, and this again takes in these three parameters. First is the model which we've just built, and then second parameter is the object on which we want to predict the values. So we want to predict the values on top of the test set. And finally, we'll set the type to be equal to response, which will basically give us probabilities for these predictions, and I'll store the result in pred heart. So let me have a look at the range of the predicted values. So we see that the range of the predicted values of the heart disease, it varies from 0.21 to 0.86. That is, the probability of the patient having heart disease, it varies from 21% to 86%. And this is how we can build a simple logistic regression model on top of this heart disease dataset. Now let's head on to the next question. So what is a confusion matrix? So confusion matrix is actually a table which is used to estimate the performance of a model. It tabulates actual values and the predicted values in a 2x2 matrix. So these are the actual values and these are the predicted values. So this what you see, true positives. So this denotes all of those records where the actual values were true and the predicted values were also true. So these denote all of the true positives. After that, we have the false negatives. So false negatives denotes all of those records where the actual values were true, but the predicted value was false. So where the actual value is true, but the predicted value is false, that is known as a false negative. Then we have false positives. So in false positive, the actual value is false, but the predicted value is true. And such values are known as false positives. And finally, we have the true negatives where the actual values are false and the predicted values are also false. So if we want to get the correct values, then correct values should basically represent all of the true positives and the true negatives. And this is how confusion matrix actually works. So now we are supposed to build a confusion matrix for the model which we built. where the threshold value for the probability of predicted values is 0.6, and then we have to find the accuracy of the model. So as I've already stated, accuracy is basically true positives plus true negatives upon all of the values. So this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been incorrectly classified. So when we divide the left diagonal with all of the values, that is when we'll get the accuracy of the model. So let's go to RStudio and find out the accuracy of the model which we built. So to build a confusion matrix in R, we'll be using the table function, and inside the table function, first we'll give in the actual values and then we'll give the predicted values. So the actual values are stored in this target column of the test set, and the predicted values are stored in the pred heart object which we had created. And then we saw that the range of the probabilities, it was from 0.2 to 0.8. So from that range of 0.2 to 0.8, I am setting a probability threshold of 0.6. That is, wherever the probability is greater than 0.6, it will be classified as 0. Or in other words, it will be classified that the person does not have heart disease. And similarly, wherever the probability is less than 0.6, it will be classified as 1. Or in other words, that the patient has heart disease. So I'm reiterating it again. So wherever the probability of pred heart is greater than 0.6, it will be classified as 0. And wherever the probability of pred heart is less than 0.6, it will be classified as 1. So let's go ahead and build a confusion matrix. So see that this is our confusion matrix, and this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been incorrectly classified. And if you want to find the accuracy, all we have to do is divide this left diagonal with all of the values. So that'll be 31 plus 17 divided by 31 plus 17 plus 10 plus 32. So you see that we get an overall accuracy of 53% for this model which we built. Now let's head on to the next question. So what do you understand by true positive rate and false positive rate? So let's start with true positive rate. So in machine learning, true positive rate, which is also referred to as sensitivity or recall, is used to measure the percentage of actual positives which are correctly identified. So the formula for true positive rate is true positives divided by all the positives. So I am stating it again. True positive rate is basically the measure of the percentage of actual positives which have been correctly identified. Now let's look at false positive rate. So false positive rate is basically the probability of falsely rejecting the null hypothesis for a particular test. So the false positive rate is calculated as the ratio between the number of negative events wrongly categorized as positive, that is all of the false positives, upon the total number of actual events. So this is how we can calculate true positive rate and false positive rate. Now we have the next question, and we're supposed to explain what is ROC curve. So ROC curve, which actually stands for receiver operating characteristic, is basically a plot between the true positive rate and the false positive rate. And it helps us to find out the right trade-off between the true positive rate and the false positive rate for different probability thresholds of the predicted values. So the closer the curve is to the upper left corner, the better the model is. Or in other words, whichever curve has greater area under it, that would be the better model. So let's say we have this curve over here, and let's say there is another curve which goes like this, which is nearer to this upper left corner. Then in that case, since the second curve covers greater area under it, that would be a better model than the first model. So this ROC curve helps us to find out the area under the curve as well as the right trade-off between the true positive rate and the false positive rate. Now we are supposed to build the ROC curve on top of the logistic regression model which we've built. So let's head back to RStudio and do that. So to build the ROC curve, we would have to load the ROCR package. So I'll use the library function and load up the ROCR package. Now, this ROCR package comprises of the prediction function, which would give me a prediction object. So this takes in two parameters. first parameter is all of the predicted values. So this spread hat comprises of all of the predicted probabilities for the target column. And the second parameter is the labels of the dependent variable. So test $target has all of the labels of the dependent variable, and I will store this result of the prediction object in ROC pred hat. So now that we've created the prediction object, we can go ahead and build the ROC curve. And to build the ROC curve, we'll use the performance function, which is again a part of the ROCR package. So this over here takes in 3 parameters. First is the prediction object, which you built. So the name of the object was ROC pred hat. After that, we will just give in TPR and FPR. So TPR and FPR stands for true positive rate and false positive rate. So for this prediction object which we built, we are basically trying to find out the right trade-off between the true positive rate and the false positive rate, and I'm storing the result in ROC curve. Now let me go ahead and plot this ROC curve which I've just built. So this is our ROC curve over here. Let me zoom this. So we have this curve for different probability values over here. So this what you see are the different probability values. And our ideal curve should be something like this, where we have more of true positives and less of false positives. And this green color which you see, so this green color actually represents the ideal threshold value. So the ideal threshold value over here would be somewhere between 0.48 and 0.62. So this is where we would have the ideal threshold value of the probability. And this is somewhere where we can get the right trade-off between the true positive rate and the false positive rate. So maybe it could be this over here. So this point which we see, so the probability would be somewhere around 0.5 or somewhere around 0.55. So this is where we could get the right trade-off between the true positive rate and the false positive rate. So now that we've built a logistic regression model in R, again we need to know how to build a logistic regression model in Python. So this time we are supposed to build this logistic regression model on top of this customer churn data frame, where the dependent variable is this churn column and the independent variable is this monthly charges column. And after that, we are supposed to find out the log loss of the model. So we are basically trying to determine whether the customer would churn or not on the basis of this monthly charges column. So again, I'll start off by loading the pandas data frame and also load the customer churn.csv file. And for that purpose, I'll be using the pd.readcsv function. Right, so we have successfully loaded the file. Now it's time to have a glance at the head of this data set. So these are the different columns which we have. So we have this customer ID, then we have the gender of the customer, we have the senior citizen column, which tells us whether the customer is a senior citizen or not. This column tells us whether the customer has a partner or not. This column tells us if the customer has any dependents or not, the tenure of the customer, whether the customer has phone service or not, and so on. Sort of all of these columns, the columns which are of our concern would be the monthly charges column and churn column. So this monthly charges column basically tells us the monthly charges incurred by the customer in dollars, and this churn column tells us whether the customer would churn or not. So now since we have our data the data set with us, let me go ahead and separate the dependent variable and the independent variable into two separate objects. So I'll store this monthly charges column from this customer churn data frame in the X object. Similarly, I'll store this churn column from the customer churn data frame in the Y object. So we have our dependent variable and independent variable to be separate. Now I'll go ahead and divide this model into training and testing set. And for that purpose, I would require this train test split function, which is part of the sklearn.model selection package. Now I'll use this train test split function, and this takes in these parameters. First are basically the independent variable and the dependent variable. So the independent variable is stored in X and the dependent variable is stored in Y. After that, I'll set the test size to be equal to 0.3. So this basically states that 70% of the records would be in the training set and the rest 30% of the records would be in the test set. And again, I'll set a random state value so that I can use these same values again if I want to. And I am storing all of these values into xtrain, xtest, ytrain and ytest. So xtrain comprises of the training set of the independent variable. Similarly, xtest comprises of the test set for the independent variables, After that, we have ytrain, which comprises of training set for the dependent variable. And then we have ytest, which is the test set for the dependent variable. So now we have xtrain, xtest, ytrain, and ytest. It's time to build the model, predict the values, and get the log loss value. So first I will import this logistic regression function from this sklearn.linear model package, and I'll create an instance of logistic regression. I'll store it in L, and then I'll fit the model on top of the training set. So L.fit, and I'm fitting the model on top of xtrain and ytrain. After that, I'll predict the probabilities on top of the test set. So L.predict_proba, and I'll pass in x_test, and I'll store the predicted probabilities in y_pred. So now that we've fit the model and also predicted the probabilities, it's time to look at the metrics. So the question stated that we were supposed to find out the log loss. So I'll just import the log loss from sklearn.metrics, and inside this log loss function, I will pass in the actual values and the predicted values. So actual values are stored in ytest and predicted values are stored in ypred. So we get a log loss value of 0.55. Now again, similar to RMSE, the lower the value of log loss, the better the model is. So again, let's say if there is another model and the log loss value of that second model is less than this, then that second model would be better than this model. Now we'll head on to the next question. So what do you understand by decision tree? So decision tree is a supervised learning algorithm which is used for both classification and regression. Right. So decision tree can be used for both classification purpose as well as regression purpose. So in this case, the dependent variable can be both a numerical value as well as a categorical value. So there is a flowchart like structure where the topmost node is known as the root node, the internal nodes with children are known as the branch nodes, and the final nodes without children are known as the leaf nodes. So here, each node actually denotes a test on an attribute, and each edge represents an outcome of the test, and each leaf node holds a class label. So let's say this first node over here, we are trying to determine the age of the patient. So let's say if the age of the patient is greater than 50. If the condition is true, we'll come here. If the condition is false, then we'll come here. After that, over here, we'll check if the person smokes or not. And if that person smokes, we'll come here. If that person doesn't smoke, we'll come here. Similarly, over here, the test condition could be whether the patient has any children or not. If the condition is true, we'll come here. If the condition is false, we'll come here. So this is how the decision tree works. And finally, we'll have class labels over here. So these would represent individual class labels. So let's say this represents that the person has cancer. This represents that the person does not have cancer. Similarly, this would represent that the person has cancer. And again, this would represent that the person does not have cancer. So in decision tree, we basically have a series of test conditions which would give us the final class labels. Right. So now we have to build a decision tree model on top of this iris data set, where the dependent variable is the species column and all other columns are independent variables.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.